Good morning, everyone. Good morning from UK. Distinguished participants, ladies and gentlemen. My dear friends of science, technology, innovations, and all the early researchers. I'm pleased to welcome you once again to the 2 days virtual international conference on solar and energy materials and technology, in short, ICSEMT 2022. I'm sure we are all reaching out to many colleagues and friends, academics, technologists, innovators, business professionals, and civil society representatives throughout our conference. A warm welcome, all of you. Dear colleagues, we all understand the importance of science, technology, and innovation in our day-to-day life and how they transform the world. The speakers in the program are uniquely placed to debate, discuss, and highlight the key points, trends, and reforms in the system for the audience. It will be great to hear from our plenary, ECRs, and industrial speakers and expertise about the influence, priorities, development, and comparison to international standards in the same field. We have arranged a panel discussions and many opportunities of collaborations, so don't miss that in the afternoon and throughout the day even. For our delegates to put forward their reforming thoughts in this vast area of solar energy and related technology field. Today, we will have sessions, debate, and discussion, as I mentioned, on different topics. It's from the academic part to the ECR sessions. So we will have a vast of related topics that can be explored throughout the day. We can have a privilege to listen some expertise in the field of photocatalyst, photothermal, and green fuel production. We will discuss the impact on the present and how determinal it can be in the future. A vivid discussion on methods and suggestion for reducing the same at various levels will be discussed. We are also eager to hear our delegates about their ideas, innovations in reducing climate change. If this was not clear earlier, it is blindingly apparent now in the time of the COVID-19 pandemic. Science, technology, and innovation are indispensable for our response to and recovery from the COVID-19 crisis. Equally important is our collaboration in this great effort. Ladies and gentlemen, I believe that by participating in this conference, we are in the right place and the right time. Together, let us accelerate the exchange of ideas and scaling up of good practices. I'm especially pleased that the discussions and activities from yesterday's session will inform the high-level solar and materials energy research. At the same time, I'm also confident that you will find new ideas, fresh energy, and novel partnerships to sustain your effort in support of the United Nations Sustainable Development Goals through science, technology, and innovation. I would like to thank my audience, the audiences across the globe, for being present here today. Thank you so much for joining us. Before we begin with our today's session, please allow me to deliver a short speech of warm up everyone regarding today's to be discussed, the key points or the key topics. One of today's major topics was perovskite solar cells and battery research. So it is a great opportunity to listen some exotic, some one of the best speaker or researcher in the world who are dealing with in those two emerging topic of energy field. We have some industrial speakers as well, so they will also try to shine how the solar energy can be a technological idea to implement it for the society. At the same time, I'm sure our experts must have done their bit of studying around the topic, and so did our audience. This is a topic that each one of us can relate to, particularly the working class. Our future depends on our ability to utilize solar and other renewable energy resources. Expanding technologies, tax incentives, and utility companies adapting to solar customers are all encouraging developments in solar energy and energy storage related fields. We believe in knowledge, research, and technology for all people, minorities, and people with disabilities to help anyone, no matter how much we can accomplish by ourselves. Whether research or development, it is never sufficient in this world of knowledge. Therefore, the focal drive of this conference is to exchange ideas. By participating in this exchange, it is hoped that all parties who may benefit from the conference can apply in merging and managing activities in their areas. It is pleasing to note that the agenda of this conference covers a wide range of exciting topics, as I mentioned, related to all the theoretical and practical aspects, but not limited to traditional energy research and laboratory limited. We are here and we are very happy and grateful to have the invited speaker to enrich the discussion on their related topics. Although we cannot greet each other in our usual way, we still have another way to interact, discuss, share insights, and enhance our minds with other researchers, colleagues, industrialists from various perspectives. We do hope you find this event fruitful for your future career, for sake of knowledge, and also for the benefit of humankind. Today, we have an exciting program at this conference that will allow members to reflect upon and celebrate our past accomplishment, renew friendships, and extend our network, and jointly explore current and future research directions. We hope that you will have a productive and fun-filled time throughout the conference today. As a reminder that we are recording this event and the live streaming, which is currently going live to the ESI Facebook page. So your camera is turned off and you are on mute, so you will not be seen or heard. But if you would like to prefer to be completely anonymous, you can change your name on the screen. I wish you all a very successful conference, and thank you so much for joining us in this morning. So before I turn over the conference to today's our first plenary speaker, Professor Pankaj Yadav from Pandit Deen Dayal Energy University from India, I would like to shortly introduce him. Before joining Pandit Deen Dayal Energy University, Professor Yadav worked as a Swiss Excellent Fellow with Professor Michael Gratzel at EPFL Switzerland. At Pandit Deen Dayal University, he explores the application of different materials for a range of energy harvesting and energy storage devices. He has received many prestigious awards, including a Fulbright Scholarship, Swiss Excellent Fellowship, and overseas postdoctoral fellowship programs. His current research interests range from thin film devices, solar photovoltaic, perovskite solar cells, hydrogen generation, fuel cells, energy generation, and storage devices. As well as he is a very well expertise in electroanalytical characterization. He is also the General Secretary of the Perovskite Society of India. So with this, I would like to welcome on board Professor Yadav. Over to you.
Thank you, Anurag. As I am visible. Hello, is I am audible?
Yes, you are visible, but not your screen.
Not my screen. Yeah, share. I will share this. Is it fine?
Yes, it's coming. Could you mind to go for slideshow or?
Yeah, it is on slideshow.
We can't see the slideshow version. We can see all the slides coming one by one. Means once we open the presentation like that.
Okay.
But if you are happy with the present like this way, yeah, no problem.
This is fine to me. If it is okay to all.
Yeah, it's okay for us, I think. Yeah, no problem. Please, thank you.
Thank you, Anurag, for your kind words and to invitation for this conference. Good morning to everyone. I am Dr. Pankaj Yadav. I am working as an assistant professor in Department of Solar Energy at Pandit Deendayal Energy University. My today's topic will be on the redefining the stability of the perovskite solar cells. Outline for the presentation will be, we'll discuss some about what is the perovskite solar cell, its basic structure. I guess in previous lectures already been covered this. Then my focus will be on the stability issues of the perovskite. So we'll take on the ETL role, the role of the perovskite composition or the perovskite layer, and the role of the HTL. And we will touch about some topics which are very new to the perovskite community also. That's our machine learning to understand the perovskite solar cell. So here also will be focus upon the stability of the perovskite with the machine learning. So we start here as, so this is the basic configuration of the perovskite solar cell. So basically this solar cell consists of multiple layers, which consist of TCO, your transparent conducting oxide. You will have one ETL layer, that is your electron transport layer, and normally we use TiO2, SNO, and ZNO are the most common one. And then we'll have the perovskite layer. So in the perovskite layer, we will come up with the MAPBI3, the very general one. Then you have famous 2 cation, 3 cations. And nowadays, most of the research is coming with the 2D and the 3D kind of the layers. And the next we'll have the HTL, that's a whole transport layer. And in the whole transport layer, most the famous one, we will find out the spiro material. And then you will use the electrodes. So in the electrodes, for the collection of your holes, we will use the gold or the silver material, but gold is the most famous one. So in this structure, researchers were trying to introduce the layers in between TCO or ETL, or between the ETL and perovskite, or between the perovskite HTL and the electrodes. The main aim of the introduction of these so many layers in this structure is either to improve the efficiency or to improve the stability of the solar cell. Just for the knowledge, the current efficiency of the perovskite solar cells recorded is about 26%. So most of the work is in the direction of efficiency, but we will be focused upon the stability of these solar cells. So focusing on the stability of the perovskite solar cell, the literature of perovskite solar cell says about moisture, the stability is affected with the moisture as the oxygen content. So in this layered structure, if I will look into the layer which is mostly hampered by the moisture and the oxygen, on the priority first will be your perovskite layer. It is found that under the moisture or the oxygen, your perovskite will absorb this and it will change its composition. Also your spiro layer, which is the the most common one, is also found to be moisture and the oxygen content. Chemical instability, again the perovskite is on the top, mostly instability most of the time found. Thermal stability when it is come, so your HTL and the perovskite layer, both of them are found to be thermally unstable. We need to find out the new materials. Structural transformation, if we talk, so perovskite layer, it is on the top. UV exposure and the sealing, these are on the device level. UV exposure, mostly it's come from the ETL layer. So you will see that we have lots of opportunity to work on this one from almost all of the layers, but majority on the perovskite or on the HTL side. So in the next slide, we'll be focused or we'll try to understand what is the role of this layer and how the stability of these solar cells are affected. So this is the first work in our group. So we had first tried to understand the role of the ETL. So in the ETL, as told, so normal structure is this, the first one. You use a compact TiO2 layer. It's a very thin layer, around to 30 to 40 nanometers. And then you use a mesoporous structure of TiO2. And above the TiO2, you develop your perovskite layer that can be of MAPBI3 double or the triple cation based or 2D, 3D structures. And then we use here PTA, may go for the spiro, and then you'll have the contacts. But just to know about the role of this ETL, we have used here ALT deposition for the ZNS layer. And we have deposited this ZNS layer below your compact layer. So this one is here with the compact layer, ZNS layer, and on the top of the mesoporous layer. So you'll have the ZNS in two places at around the ZNS in your compact layer as well as for the mesoporous layer. The next photovoltaic parameters we found that as compared to the reference devices, which was giving us a good number around to be 17.90 efficiency, VOC was 1.095 volts. But when we introduced the ZNS layer with compact layer as well as with the mesoporous layer, we found that VOC is significantly increased. Although current JSC for all of the devices were the same, fill factor is being improved with the utilization of the double ETL ZNS, and efficiency is also improved, but that was not something significantly. But yes, VOC you will find significantly improved. And these are the same images. So A1 is for your reference devices, and B and C when you utilize the double electrode, double ETL structures. So we found this structure, or from this study, we can conclude that either where you can put your ZNS layer with the compact one or above the TiO2 layer, the role is almost same. Even the morphologically it is same. Even on the VOC point of view, it's not that significantly changes, but yes, around to be 10 millivolt difference you are getting here, and somewhat 1% change in the fill factor here. Apart from that, efficiency is also same. So we conclude that we take it both the structure as the same one. Forward this study, next we have went towards in the same structure we have tried TIN layer as a layer between the mesoporous and the perovskite structure, and we have checked about the same images and then found okay, this structure or the intermediate layer between the mesoporous and the perovskite helped in the growth of the perovskite structure also, as the gray boundaries were less, bigger size of the perovskites being formed. And with some of the studies, we found out the band structure and found that with the help of the TIN layer in between, it helps something to the better transport of the excited electrons from the perovskite to the or towards your FTO side. As you see that here, the matching between these levels are much better as compared to the TiO2 one. But as we focus on the stability issue, it's fine with the efficiency, with the different layer of the TIN, you found the increase in the your power conversion efficiency, and then decrease at a higher thickness might be because of the higher series resistance is being offered. Yes, the another advantage we find out to be that the hysteresis was lower. So we'll be talk about hysteresis in next few slides, but maybe who are in the perovskite, they might know about the hysteresis. It's important to be noted here is when we have modified the ETL structure, just look into the EQE, especially for the lower wavelength, less than 500, 600, you will find that EQE percentage is increases. Whereas on a backside, on a higher wavelength, close to 600 to the 700, it's almost same. So the current difference what we are getting in our devices will lead to the higher efficiency is come up from the lower wavelength. That means this wavelength is going to be absorbed maybe around close to your interface between TiO2 and the perovskite, maybe around 300, 400 nanometers in a proper calculation if you do. So you can see that In this region, when you have used TIN layer, it improves your current. Whereas the bulk property, although in the same image, we found that grains are improved, but these grain will not help to increase the extra current. So the extra current we are getting only from the lower wavelength region. And yes, when we check about the stability, these devices give a decent efficiency or the stability behavior up to 500 hours as compared to the conventional TiO2 structure. And this one stability data we have taken not a continuous under the illumination, just take one time the measurement, keep the devices under the nitrogen or the glow box condition, take out for the next day measurement. So in this way we have taken. So this was the old data, then slowly we have improved and then continuous measurement we went on. Yeah. So after establishment of that, okay, we have double layer ETL we use, so that will have a beneficial effect not only in the efficiency but the stability. The next topic we have taken about, along with the modification of the ETL, just look into how we can modify the interface between perovskite and the HTL also. So the material by choice at the time we have taken the ZNO ETL, but already know that ZNO is a tricky material, especially for the perovskite. When you deposit perovskite on the top of the ZNO, mostly due to the hygroscopic nature of the ZNO, pure form of the perovskite is not been formed. So you will find on the top or in between lots of PbI2 residue is there. And these residue will limit your efficiency or proper conversion efficiency you will not find. So what we have done is, when we have introduced the ZNO, your graphene layer in between the ZNO and the PbI2, a significant performance we get, not only on the photovoltaic, but on the morphological point of view. We find that grains are much bigger in the size. They are very compact in the nature. A pure perovskite phase has been formed. No residue of the PbI2 we have found it. Yeah. And the next what we have done, we have put a one small molecule of the PFPA molecule on the top of the perovskite before depositing your HTL layer. So we have, these are the photovoltaic parameter. When you look into the ZNO only, this in the red color lines. So this is your photovoltaic parameters, IV measurement. So when we have gone up with the this your ZNO layer with the graphene layer, you will find in the green in color a significant improvement, not only with the current or overall response has been improved. And when we have put this PFPA molecule in between the HTM, further significant improvement is get. So these are the PCE for the 60-second we have measured. A significant difference you can find it out here. As in my previous slide, if you remember, I have told about EQE. When we have used the TIN, only in the lower wavelength segment, we have found improvement in the current or the improvement in the EQE response. But look at here, it is the overall response has been improved. Even though if I will check or if I will compare only with the ZNO with graphene and the PA, even all the wavelength response has been improved. So that means it's not only going to be change the interfacial property, but also the bulk property of the perovskite structure has been changed in this work. Just coming up the limitations of the ZNO layer. In the next work, we have focused upon the ZNO material. Even in the literature of the ZNO, if you see, it is found not a proper or an appropriate candidate if you are talking about the stability. So here is, we have addressed a new material. It's a new organometallic approach for the development of the ZNO quantum dots. So as compared to the conventional approach, which you have you take the organic materials coated with the ZNO and do the spin coating, evaporate. At the end, you found that your efficiency is been limited due to the contamination by the carbon or the organic residue which remain in your field. Whereas in case of our, with the newly organometallic approach we have used, it has been a core shell structure has been formed, but when you make a film of it and then anneal, the thin film deprived of the carbonic organic residues. So it's a free of it. So this is the recent work. Maybe if you are interested, you can look into it. Yeah. Coming into the UV visible part, so we have characterized all the aspects because some of the photovoltaic parameters are interesting. So we have put it here, the UV visible. So just want audience to focus here on the UV. Almost all same kind of the UV you can expect from the ZNO and this triple cation perovskite we used. Not a significant difference. So we expect that current as a photovoltaic device, when we get from this structure will also be the same. And these are the same morphology. Yes, as I told you that the organic residue when remains in your ZNO, when you heat it up, so this kind of hole formation will be there, was there. Whereas in case of the our new approach organometallic, we found that grains or something, this ZNO content dot, they help to the crystallization of the perovskite, bigger grains, lesser the grain boundaries, and whole free film structure has been found. When you check about the IV characterization, again you can look, we got a EQV response improvement throughout the wavelength region, not only specifically for the lower wavelength region or the higher. So again, the same conclusion it came up that these new kind of the ZNO what we have synthesized not only change the interface property, but also lead to change the overall perovskite composition or perovskite morphology that leads to a better absorption of the light and conversion into the current form. And yes, when you look into the voltage, although these devices depict the higher voltage and find out the recombination, but obvious in these devices we expect a lower recombination as of the better grain boundaries. But surprisingly, we found that the stability of these devices, again for 500 hours, not a continuous illumination we have done, but yes, in a day-wise illumination for 500 hours we have done, and found that the modified ZNO will give a better efficiency stability as compared to the conventional one. So establishing that the ETL modification not only at the interface level, but also can lead to change on the perovskite structural properties also. We have taken a new task, let to change out the perovskite structure with help of the material configuration. So in this one, normal our MPBI3 structure, instead of whether it will be work for the triple cation, single cation, we have used MaCl. The role of the chlorine is well reported in the literature of the perovskite. It's been stated that this chlorine will help for a better grain or the crystallization effect that can lead to a higher grain morphology that will lead to a better VOC and the current new devices. But what we found that when we heated up this material at annealing temperature, this chlorine will leave the spaces and create the defect in your structure. And this we find the new lag point where we can do something else. So what we have done the iodine passivation. So in a CVD structure, CVD growth, you can go and then we, with the help of the iodine vapors, we have introduced the iodine. So in the vacant space of the chlorine which was left out is filled up by the iodine, and along with the efficiency, we have found very better efficiency retention in the 20-degree and the different temperatures we have studied. This is the continuous data measurement we have done. And after the 500 hours, we keep this device in the glow box. And then the next day when we measure it, found that it sustained their original efficiency. But when you compare the efficiency plot here, what we have taken as a temperature studies, it is not that all the time you'll get 100%. But yes, when you make a solar cell and test it for the real application, as your module can take a stress of maybe from the normal temperature from 25 up to go to the 65. So you will find that significant difference in the efficiencies is, or the stability is to be reported here. We thought this is the lag space. We can have to be something so that this variation can be suppressed further. So summary of up to these approaches where we have discussed about the ETL, modification of the ETL, either double ETL or ZNO, everything, or with the perovskite structure, stability of perovskite is affected by all of these parameters. So still the problem or the question is remain the same, whether we reach to another some conclusion or not. So now the question is measuring the JV, like the stability measurement or the JV, what we have done for different is enough to define the stability of the perovskite, or some new mechanism or some new testing condition is needed. So taking this question ahead, we have adopted another approaches. So this has been reported in the materials today. So this was the work previously we have done. So if interested candidates, they can go into the paper and then look a more detailed version of it. But some of the key points I will be highlighting here. So this study is being, as the previous open question, we are trying to address here. So before to go into this study, I would like to introduce the concept of the hysteresis to the audience, which are new for the perovskite community. So hysteresis is the phenomenon like for the IV measurement you get when you measure the current voltage response of your solar cell in the forward and the backward direction. Ideally, let's take the example of the silicon solar cell, CZTS solar cell, all the conventional solar cell. You will find this forward and the reverse can always be the same. However, in case of the perovskite, you will not find this curve are same in the forward and the reverse scan. You will find some kind of structure or not overlapping structure. So what will be the reason for this hysteresis? So in literature, it has been found that ions along with the electronic conduction mechanism is also been there. And this ionic motion with respect to the bias or chemical composition is going to be changed. And these ions will be responsible for this kind of curve. And then perovskite community take this challenge also, and along with the efficiency, stability, they are focusing on reduce the hysteresis in their devices. Yeah. So moving ahead, taking into the perovskite measurements or the stability, we have taken a very conventional MAPBI3 structure, although data for the cesium MAFA, which is the most stable structure, is there. So that is also, that one also you will find inside the manuscript, but we have focused more on the MAPBI3. In the literature, it's been established that MAPBI3 is the weakest structure of the perovskite, which is very easily dissociated when it is in the atmosphere or in the oxygen concentration high is there, or the moisture content is there, or under the high thermal stress. So we had tried to identify what's the scenario with the MAPBI3. So we have developed this structure, a conventional one, where you'll have a FTO structure, then you have a compact one, then mesoporous TiO2 and MAPBI3 structure. And then instead of the Spiro, we have taken the PTA. Now one might ask a question, why when the conventional structure used the Spiro when we went to the PTA? Although we have shown the data for the Spiro also that Spiro leads to a higher efficiency, but going for the thermal stability, find that PTA is the much better one as compared to the Spiro when we talk about the oxidation processes in the Spiro and gold migration from your contact. So we have went not for the higher efficiency, but we went for the stability of the devices. So this was the basic of the study we have formulated. Yeah, so this is the stability we have done. So all the stability data here we have measured under the continuous illumination. Yes, we have provided the ideal conditions for the solar cell measurement. We have not done in the open atmospheric condition, in the proper glow box condition we have done. So we have taken the data here at a different temperatures. So we had started with the 20 degree, 50, 65 and 95. If you look into the 20-degree data when we have taken, so we have put it here, the normalize your efficiency, but if someone is interested to look into this more data, so it is already available in the publication. So you can look it here. So we find that these devices, even with the MAPBI3, we were talking about like MAPBI3 is that much stable under ideal conditions. So we find that even the stability is close to the normalized one or the 100%. And after the 500 hours, even the small degradation, what we have found when we keep it under 24 hours under the dark condition, it went back to the initial condition level and remained stable for the next 500 hours. Okay, more focusing upon only about the 500 hours of the study when we have looked into the different temperature studies. So up to the 50 degrees centigrades, we have found that device sustain is 100% of the PCE. When we go for the 65 degree, it's sustain up to the 90% and go for the 95% when then it's sustain up to the 85%. Yeah, but obvious with the temperature, we expected this decrease in the efficiency level. But surprisingly, we found and when we look into the lower temperature on the lower hours of the operation, you find that at 65, 95, its PCE go beyond the 1 or the 100% and then start decreasing. Same way for the 95 also we have found, and then we repeat all this experiment. Almost it took 6 months to measure all this one, and then we have repeated for the second and the third time, even though huge number of data we have found. When we have taken about the VOC, fill factor, JSC of all of these temperature conditions, we found that for 50, it's fine, VOC is stable, but for the 95, 65, it's decreasing, but not that significantly. Yes, looking into basics of your semiconductor, increasing the temperature, your band gap will be reduced. At the same time, VOC expectedly going to be reduced. Fill factor response, we get something different, which is above the 100%, especially for the 95-degree. Even at present also, we don't have conclusive evidence why this is taking place. When looking into the current response at a lower time hours of the duration, when we take the data, we found that, okay, with the increase in the temperature, you expect that your current in your devices will be increased as your band gap will reduce. So higher current is expected, but as the time of the measurement or taking data logging is keep on, then you find that this current is decreased. This is something which is not defined classically on your semiconductor books. Yeah, then we have introduced something on the measurement setups. It's called in situ EIS measurement. Along with the in situ, might be when you look into more in depth of the our research article, along with the in situ EIS, we have also taken about the in situ hysteresis measurement also. Although I have not highlighted here, yes, so in situ EIS measurement means it's not we have stopped the measurement. So during the measurement of all the stability, we have fixed the intervals. So the measuring system, along with the IU measurement, it will do the impedance measurement also. So these are the curves. Some of them we have highlighted for the duration 0 to the 500 hours. So as looking the literature of the impedance of the perovskite, you find, okay, 2 circles you will get for the perovskite solar cell. 1 circle is at the high frequency, another is for the low frequency. There are lots of debates on the perovskite community, whether the acceptance of this EIS impedance responses, what the physical information it will provide. Yes, for the DSSC solar cell and for the silicon solar cell, all these concepts are well established. But for perovskite, still it is not being established in that context. But yes, all the community is agree with that. Okay, the high frequency semicircle part is related to the recombination. But if you check about the early papers, which is around 2010, 13, 14, this was not treated as a recombination, but something on the transport resistance. But now a time it's been established with other theories supported also that the high frequency part is related to the recombination, whereas the low frequency part is related to your ionic motion, as this time response goes up to the minutes scale. So this is the response overall. So with the 0 hours, you will find the 2 very well defined semicircles. With the 50 hours, high semicircle is almost the same, but the lower semicircle is suppressed. Whereas at the 400 hours, both the circles get suppressed. Looking into the capacitance response, we find that, okay, which is being established in the perovskite society, that the low frequency is due to the ionic behavior. We found that the capacitance keep on increasing as the number of hours are going up. When you keep these solar cell devices under the rest condition and then again remeasure, then they will come back again back to the initial condition, which is shown by the black in color. Yes, now this low frequency part, which is keep on increasing, then we have to find out what are the possible mechanisms. Then we have find out the time responses for the high and the low frequency, and we found that its activation energy is being come out, but we have not concluded this activation energy either from the electronic or the ionic motion, because in the literature of perovskite you will find lots of number is being assigned from 0.1 electron volt to 0.6 electron volts for the different mechanisms. But yes, this was something new for us to get insights into the perovskite stability. Next, we have done about the CLSM imaging of the perovskite structure during the stability measurement also, and then we found that on the surface some PbI2 or the lead content was there. Then as compared to the MaPbI3 structure, cesium MaPbI3 structure also we have measured, so that was retaining is almost 97% of the efficiency. These were the experiments we have done just to conclude that, okay, something not strangely we are measuring here. So conclusion from this study, we have come up that, okay, ions are the most prominent responses for the stability of the perovskites, but still the degradation mechanism of, for us, this perovskite is not still complete. Moreover, it's been reported that dynamic of the initial exponential region are sensitive to the temperature, as I've showed in the initial hours, that required more attention to go on it. Then on the same data, we have extended our studies, and then we have taken the new tools which are very new in the fancy, like machine learning, artificial intelligence. So the concept of the machine learning and artificial intelligence is we have used the machine learning. So we have taken all the data with respect to the temperature on the time scale, and then we develop a one model. We gave all of these data. So like suppose for 500 hours of stability, we have measured all the 1000 hours. So we trained our model. Let's say for 400 hours, 300 hours, we trained our model for the hysteresis, VOC, GOC, all the parameters we trained. And then we ask our model to test for this condition. So we have some data for the training and then testing. And we found that, okay, our trained model is now test very well. Now, after that, we ask our model to future predict of the stability of these devices. So it's so impressive that this technology can help where our limitations are for the measurement. So we have use here neural networks. So in the neural network, basically you will have the input layer, input features you will give it to your model, and there are some hidden layers which are statically connected between your input and the output, and then you predict the results and go for the future predictions. So we have developed here artificial neural network with the difference in the dense layers, not go much deep here, but yes, these are the some results. This is for the measurement when we have done for the 95-degree, and we ask our model to predict. So here is the experimental values you can find, and then the prediction with the model. So even we look, except for the lower measurement times, in the higher one on the longer period of operation, the model predict very well. As I mentioned previously in the previous slides, we have done the in situ impedance measurement. Also, we have done in situ hysteresis measurement. So these are the hysteresis data. So if you look into the literature of the perovskite, when you do your solar cell conventionally, even if you want to compare your devices, device A, whether it's better than B or C, like this, you always measure the hysteresis also. As I mentioned, then researchers want to suppress the hysteresis. But look into here, when we done the hysteresis measurement, when your devices was a new or in the virgin condition, its hysteresis was low, but as keep on when we measure for a longer duration, its hysteresis keep increase and then saturate. Even in our previous results, we found that ions was the responsible mechanism. If you remember my previous graph of capacitance. So here also, when we measure the hysteresis, the same something conclusively we found out. Yes, then we predict for the PCE that was close enough in the acceptable range. Then we again repeat this experiment for a different temperature with more unsystematic data, and we found that, okay, even at this condition also our machine learning program is able to predict very closely. Yeah, some variation is there, but that is on the acceptable limit. Then here is the Pearson coefficient we have done. So people who are not aware about the Pearson coefficient, is this is the table or where you can establish a mechanism between input and the output features. Suppose you'll have the features like current, voltage, VOC, fill factor, hysteresis, and then want to see which one has a more impact on the efficiency or some other factors. So surprisingly, along with the current, we found that hysteresis is also evident to be the most important feature, which is PCC value is higher than 0.3 for all the target features. So this was new for us that hysteresis has a role. Then we went for the SHAP analysis and come up with the same conclusion that hysteresis has a prominent role defining your stability of the devices on a long operations. And this is the summary plot where you will have find on this summary plot on the x-axis, you will see, okay, on the PCE, you will have higher dependence on the temperature. After the current, you'll find the hysteresis is the more prominent one, which is going to define your stability of your devices. So with this one, the ML, with the help of the ML, as this was a very initial data for the machine learning, more rigorous development is still needed. But based upon the previous or this study, we have concluded that prediction of PCE trend can't be solely determined only by the JSC, VOC, and fill factor, which we conventionally do for the other kind of solar cell like silicon, CZTS, or organic and DSCC. However, hysteresis play an important role in quantifying the degradation perovskite during the aging conditions. So this is the factor, something need a more attention. While coming hysteresis into the picture, if you look into the literature part where most of the stability data or the rigorous stability data has been reported, this factor is still lack. Only a handful of publication you will find reported the time evolution of the hysteresis, but I will say almost in a 10 one paper you will find out this kind of histories data. In ways that with the more rigorous data standard measurement protocol, the model can be made more generalized, which could apply to diverse architecture of the composition of perovskite, whether 2D, 3D, or any of NPA, PNA structure you can go. So on the development part is fine, but on the measurement part, these are something conclusive come up from our studies, like hysteresis need to be considered here. At the end, I would like to acknowledge our funding partners, nationally DST, and from the state-wise, Guj Coast, PDEU, Perovskite Society of India, which is rigorously very hard in India to develop on the perovskite community, where we can exchange our idea, we can exchange our lab outputs, and not less the organizing committee, Dr. Anurag Roy, and all the team members. Thank you, Anurag.
Thank you, Dr. Yadav. Excellent talk. And I hope that those who are working on perovskite solar cells, which is currently an emerging topic of research for solar industries, they will definitely benefit. There is a lots of aspects that you have discussed throughout your talk. Thank you so much for your time. I think we have some questions, but we will discuss after the panel, after our next speaker during the panel discussion. So please stay with us.
Sure.
So we will moving on to our, sorry?
No, fine. Stop sharing.
Yeah, thank you.
Fine.
Yeah, thank you. Thank you for joining. We will move to our next speaker, who is Dr. Sudhakar Pichaimuthu. He is currently Associate Professor, School of Engineering and Physical Sciences, Institute of Mechanical Process and Energy Engineering from Heriot-Watt University, Edinburgh, UK. Before going to Professor Sudhakar's talk, I'd like to brief introduce him. Dr. Pichaimuthu's main research areas are photochemistry, photocatalysis, nanomaterials, solar energy, and electrochemical carbon dioxide recycling. In 2016, he moved to the UK as a junior research fellow at Queen's University, Belfast, Ireland, Northern Ireland. The European Regional Development Fund awarded him the Simbru 2 Rising Star Fellowship through the Wales government in 2017, where he led the multifunctional photocatalyst and coating research group at Materials Research Centre, College of Engineering at Swansea University, Wales. He is currently a fellow of the Royal Society of Chemistry. With this, I'd like to welcome Dr. Sudhakar for his talk.
The organizer and particularly Dr. Anurag Roy for the wonderful arrangement for this conference. I'm sorry I'm not able to join today in the event. So I hope the recorded lecture will help you, and I'm happy to answer. If you have any queries, please contact me by email. I'm happy to answer your queries. Okay, this is me, Sudhakar from Heriot-Watt University. This is the content of my talk. So I start with climate change, the global issue, and then I switch over to the what is a renewable hydrogen, particularly how we can synthesize hydrogen fuel from solar energy. And then I will give you an update about what are all the recent progress and challenges in this photoelectrochemical hydrogen generation area. And then I give some modern applications like coupling the wastewater treatment with PEC water splitting and how we can push the water splitting field beyond the oxygen and hydrogen generation area. And then I will conclude my lecture with a take-home message. Okay, let me briefly discuss about the climate change. The climate change is nothing but a longer term shifts in temperature and weather patterns. Okay, so here there's a picture delivered by NASA. You can see the different color codes give you an idea about the temperature area. Okay, for example, if you compare the average temperature in between 1951 to 1980 baseline and what happened in 2011 and 2020, approximately 1 degree Celsius is increased globally. Okay, so now now many of us thinking, what's the consequences of even a small 1 degree Celsius increase? Okay, the answer is the right hand side here. So a small temperature increment globally, it produces unwanted or undesired events. For example, frequent wildfires, a longer periods of drought in some regions, and the duration and intensity of tropical storms. So these undesired calamities definitely affect the people's health as well as economy of the country and complete social life. So again, keep in mind the small 1 degree Celsius increment, this produce a huge environmental impact. Okay. Now the question is, why the climate change happen? The answer is carbon dioxide. I mean, the, the presence of carbon dioxide in the atmosphere in parts per million. Again, here, if you take a look in the picture, the x-axis is different decades or year. Y-axis is a carbon dioxide level parts per million. Okay. If you closely look at there, from until 1950, there is not much change in carbon dioxide. Okay. Here and there some increase and decrease, but when the industrial revolution started, the technology introduction to the market, the factories and followed that, so it's gradually or exponentially the carbon dioxide emission is quickly it increased from approximately 300 parts per million to 400 to 420. Okay, so this is the reason to create the climate change. Now the next question is where the carbon dioxide come from. So the left hand side you can see, second. Now you can see here the carbon dioxide greenhouse emission from different sector. Particularly the major portion is coming from the energy sector in highlighted in a red color. Okay, the energy means energy used in industry, the transport sector, as well as the energy utilization in a building, both commercial and residential building. So now this is the time we have to think about how we can control the carbon dioxide emission in terms of developing clean energy sources. That clean energy source should not emit the carbon dioxide to the atmosphere. But at the same time, the energy resource should be renewable, cost effective or affordable to all, as well as it should be abundant. Okay, so these are all very important. So keep in mind these factors. The last year United Nations Climate Change Conference COP26 held at Glasgow, UK. They suggested three major points to the community. The one is we should accelerate the transition, energy transition particularly, from coal to clean power. The second one, we need to protect and restore nature for the benefit of people and climate. And third one, we have to accelerate the transition to zero emission vehicles. So based on these initiatives, we can significantly reduce the carbon dioxide emission parts per million in atmosphere, and we have to keep the globally, keep our atmosphere, do not increase the global temperature 1.5 compared to the 1950 level. Okay, so this is a idea. Okay, what is the solution? One of the solutions is to adapt the clean energy carrier. Here, the scientists proposed the hydrogen is a clean energy carrier for the net zero environment. Net zero means the very carbon neutral environment. So why hydrogen? Okay, so the today topic is completely, we are going to talk about the hydrogen. So before getting to the topic, so we need to understand what is hydrogen and why we're running behind hydrogen. So hydrogen is the lightest and most frequent element in the universe. I think most of them are joined here. You came across the periodic table from the high school. So the hydrogen is the #1 element in the periodic table. So you can understand the atomic number is 1, very lightest. Unfortunately, hydrogen only exists in a bound form. That means you cannot see the hydrogen in a separate form. So if you want to synthesize hydrogen, definitely you have to take the bound form like a water, H2O, hydrogen is there, hydrocarbon and minerals. So you need to break the hydrogen molecules and you can get it. That's the only way. And the more important point, the most important point, why we go behind hydrogen, the gravimetric heating value of hydrogen is really high compared to other fossil fuels. For your simple understanding, I'm giving the right hand side a table, just comparing the hydrogen gas with different types of fossil fuels. The two important parameters I want to bring your kind attention. For example, hydrogen, please compare if you burn the hydrogen, how much energy per mass, that means joule per kilogram, you can get it. Okay. For example, if you burn the hydrogen gas, you can get approximately 140 joule per kilogram. Okay. The second one is gasoline is the most popular fossil fuel what we are using in our community. So if you burn it, you can get 47. It simply give you an idea that when you are burning hydrogen gas, it produces approximately 2 or 3 times, the higher the energy. But interesting point, if you look at the carbon dioxide emission to the environment, the same amount, if you burn the hydrogen gas, it doesn't produce any carbon dioxide emission. But in the case of gasoline, it produces a significantly 0.86. So that's why we running behind the hydrogen. And of course, hydrogen is a fantastic component to support the UN Sustainable Development Goals. For example, it will fit to the Affordable Clean Energy Goal #7 and Climate Action Goal #13 and some other indirect contribution to the UN Sustainable Development Goals. Okay, let's go further. How we are synthesizing hydrogen at the moment in the market. Currently, people are using the well-known and matured process called steam methane reforming process. Simply, they take the methane as a feedstock and react with steam and break the methane into hydrogen. This is a very well-matured technology, but the challenging is if you are synthesizing or developing 1 ton of hydrogen from this process, it produces 9 to 12 tons of carbon dioxide to the atmosphere. So we simply, for our understanding, we call it as a gray hydrogen. Okay, so here is a very good technology, but unfortunately, it produces a lot amount of carbon dioxide to the atmosphere. So what people are suggesting at the moment, researchers are trying to capture this carbon dioxide emitting from the sites, like industrial sites, and they store it underneath of the rocks. As usual, hydrogen is coming. Now, if you are comparing the carbon dioxide emission value in the gray hydrogen, it's approximately 83 gram of carbon dioxide equivalent if you are getting hydrogen gas. Here, once you manageable the carbon dioxide, it greatly reduced to 83 to 21. Okay, so almost 3 times it reduced, but still we can't how to synthesize the green hydrogen. That means no carbon dioxide emission involved in the atmosphere. So that is the solution is called electrolysis. Electrolysis is nothing but imagine like a battery plus and minus, that is anode and cathode. So 2 electrodes, anode and cathode, immerse in a water. And when you apply the potential in the circuit, the water is splitting hydrogen and oxygen. This is called electrolysis hydrogen generation. For example, you can obtain 1 kilogram of hydrogen generate from the 9 kilogram of water. Here, water is the major feedstock. Okay, but still, we can't say this is 100% green hydrogen because, as I said here, a small electric potential here to drive the overall process. This electric potential at the moment majorly get it from the electricity grid. So as you know very well, electricity grid is mostly come from the coal industry. When you burn the coal, it's emitting a huge amount of carbon emission to the environment. So now, though this electrolysis technology it mean for green hydrogen does not produce any carbon dioxide to the environment, but the adapting electricity is the problem. So what is the solution? Yes, the solution is renewable energy. Instead of coal industry or adapting the grid power from the fossil fuel based sources, you can adapt wind energy or solar photovoltaic energy, feed into the electrolysis cell. It absolutely doesn't provide any carbon emission to the atmosphere. So we can say it is a pure green hydrogen. Okay, so you can look at the number, it's almost null. Okay. Here for your comparison for your futuristic market, I compare the levelized cost of hydrogen in y-axis and in x-axis in a year in 2025 and 2050. So the color codes give you an idea of the different technology. For example, this is a gray hydrogen from steam methane process, and this is blue hydrogen from the carbon dioxide storing capture technology. And this is electrolysis adapt with the grid electricity from coal industry, and this is absolutely green like a renewable hydrogen. So compared to gray hydrogen, still it's going, it show a good response or tendency. We can reduce in 2025 compared to the coal industry based electrolysis. And very interesting point, in future, the high mature technology like a steam methane process cost will be go high, but in terms of renewable hydrogen will go down. So it's very well known that solar photovoltaics or wind energy, it's always it's a very high value in the beginning of the project, but in terms of in a overall life project time like a 10 or 20 years, it will go down. Okay, so that's why we strongly suggest renewable hydrogen go with renewable energy. Okay, now the another question is what is the application of hydrogen or what is the use of hydrogen? Okay, for example, here I give two cartoons. I adapted the UK hydrogen policy. For example, here is the electrolytic hydrogen is produced. We are standing here. And this hydrogen, once ready from the electrolysis cell, it can be transported to the on-site. For example, if you are producing in industrial sites like a steel factory, you can feed this to industry for a green steel fabrication. And sometimes if you want, you can extra hydrogen can transport in the pipeline and export to the national grid. And non-pipeline like a transport application, you can use it. Or in third, you can blend some quantity of hydrogen to, you can put it some different application like a heating in buildings, power, and different types of transport application. I will show you some picture in the next slide. And not only this application, the hydrogen is a good feedstock to synthesize the fertilizer like ammonia. Okay, so you can see a number of applications using hydrogen, and for your simple understanding, again, I'm giving a right hand side some picture. Okay, so now you can understand hydrogen is a central energy vector. Either you can store it or you can transport it, and you can use the on-site applications. Okay, so these are all the pictures derived from the internet, and particularly the Toyota Mirai car. They introduced already hydrogen fuel cell based car in the market, and not only passenger car. Nowadays, people are interested to adapt the hydrogen for a truck for a larger transport. UK already introduced the world first hydrogen powered bus, and now South Korea is keen on introducing the hydrogen based buses on the road. Germany already achieved a world first hydrogen powered train, and UK also transfer the technology in later this year or next year, UK. And of course, during the COVID time, few companies are trying to adapt the hydrogen fuel cell based aircrafts because the commercial aviation industry accounted approximately 2.5% of global emission of carbon dioxide. So this is a good potential market to introduce the hydrogen based aviation aircrafts. Okay. Okay, let's move to now to the introduction to the technology side. The technology side. As I mentioned, water is a feedstock for electrolysis hydrogen generation. So everyone dreaming how to develop the hydrogen from water. In 1874, a famous novelist, a French novelist, Jules, he mentioned about the water will be one of the good idea to synthesize the hydrogen. He mentioned in his one of the famous novel. Think about that. He's not a scientist. Okay, so scientists and non-scientists, everyone is thinking to how to fetch the hydrogen. Okay, that's the matter I want to convey here. So for your simple understanding, those who are attending here in a different background, okay, I will give you this cartoon adapt from internet. For example, imagine battery plus and minus, plus mean anode and minus is a cathode. Two electrodes immersed in a water and separated with the membrane. And in particular time, if you're applying a potential, that potential, electric potential comes from the renewable energy or grid power. So in particular situation, when apply the potential, it oxidizes the water into oxygen. And here it's the protons are reduced to hydrogen. Okay, so you're getting oxygen, hydrogen. So how we can understand the in a simple scientific way? Okay, for example, so most of them you came across the I versus V, I mean the voltage versus potential measurements like a diode measurements. Okay, so for example, I'm just varying the potential in the circuit and parallelly I'm measuring the current in the circuit. Okay, now if I applying a potential from 0 volt to small, I mean moving 0.1, 0.23 volt, 0.4 volt, nothing will happen in the circuit. That means no current absorbed in the circuit. It implies that there is no catalysis reaction happen in the electrode. And once I reach the 1.23 volts, suddenly I got a good amount of current induced in the circuit, and it goes exponentially, and it shows a very, very high quantity of current you can see absorbed in the circuit. So what happened in the negative potential side? Even in a small potential, it shows a very exponential trend. So what does this mean? This means the right hand side, the red color curve is indicate the oxygen generation on the anode compartment or anode surface. This cathode, this current, it's representing the hydrogen generation on the cathode compartment. Overall, 1.23 volt plus some extra volt it require to produce the oxygen and hydrogen in the tank. Okay, why 1.23 volt? Here answer is, here please understand, you are applying electricity and producing hydrogen gas. Now the point is, you are breaking a molecular bond, for example, H2O into H2 hydrogen and oxygen. So a minimum amount of requiring energy to break the molecules of H2O, I mean bond, H2O bond. Okay, so according to the Gibbs free energy, it requires approximately 237 kilojoule per mole. If you are converting to the electrical energy like a volt, it's 1.23 volt. So that's why we need 1.23 volt to break the bond of H2O to oxygen and hydrogen. I hope you can understand now what is the thermodynamic subject behind the water splitting. Okay. Now, what is the photoelectrochemistry? I can say it's a shifting from the dark catalyst to light driven catalyst. The same setup, imagine that anode and cathode, only the difference is the anode, instead of dark catalyst, we are coating the photoabsorber coating, for example, titanium dioxide. This titanium dioxide is a good light absorber. The light source may be indoor light or nature sunlight. Why nature sunlight? Because it's free of cost, it's abundant, every day you are getting. Okay, so rest of them are very similar. Now the similar IV trend I'm going to study here. I'm going to apply a small potential, but look at here, even in a small potential, you can see a good amount of current generation in the circuit. So it means the water oxidation is happening even a small amount of potential with the help of sunlight. But in the case of cathodes, so again, if you compare to the typical electrolysis, see the electrolysis it requires 1.23 volt and it produce. So this much energy we saved by the light energy. In terms of cathode, no change. So overall, in the electrolysis, 1.23 volt plus here, now we save this right hand side like a potential here. So overall, you can see the light-driven electrocatalysis process, nothing but electrocatalytic process, reduces the minimum applied potential for overall water splitting process. Again, how to understand the in a nature, I mean, how to produce the fuel from sunlight and water. For further simple understanding, take a look at the nature tree leaves, how it produce their own food. The two keywords is light and water. Okay, the light means sunlight. So the tree leaves producing their own food, that is a glucose, okay, with the help of light and water, and it emit the oxygen. As an energy scientist, I assume this oxygen as a fuel. Okay, very similarly, in 1972, Professor Fujishima and Honda, they introduced the semiconductor material like TiO2 instead of the artificial leaf. Okay, and with the sunlight and small potential, and it produced the oxygen gas on the TiO2. It's very similar to the natural photosynthesis process. Then it called artificial photosynthesis process. The one advantage here, the complementary electron getting from the circuit and it reduced in the cathode compartment, it produced the hydrogen. Okay, so here this artificial photosynthesis process produce oxygen and hydrogen. So this is a photo I took with Professor Fujishima, and I had a good opportunity to work with him during my JSPS award time. Okay, so again, for your imagination further, how the hydrogen is producing from the laboratory scale. Again, the anode compartment, the photoabsorber coating, for example, TiO2 or some other photoabsorber nanoparticle coated on the substrate. And the right hand side, a very typical platinum electrocatalyst, very robust. And in between photo anode and cathode, we fill the water with ionic conductivity support, and it's separate with a proton conducting membrane. Okay, for your semiconductor physics understanding, every semiconductors have conduction band and valency band. You can compare with electron volt scale, absolute scale I put here. Okay, for further understanding, for the electrochemical scale, I put another window here. It's called energy versus normal hydrogen electrode in terms of volt. You can look at here, I put some small window here. That means 1.23 volt difference that thermodynamically required to split the water. That's called water splitting potential window. Okay. Now, under the sunlight, every semiconductor produces charge carriers, photoelectron and photoholes. Okay. The photoholes, that means whenever the valence band portion of the semiconductor is greater than 1.23 volt of the water splitting potential, the photoholes produced from valence band is capable to oxidize the water into oxygen, and it produces one byproduct proton. So what happened about this photoelectron? It goes to the circuit, to the cathode, and these H plus protons is reduced for the hydrogen gas. Okay, so in overall, under the sunlight or light irradiation condition, with spending a small applied electric potential, you can produce the oxygen gas and hydrogen gas. Okay, for your visualization, I show you how we synthesizing the hydrogen gas in our laboratory. Okay, here, as I mentioned in the cartoon, anode and cathode compartment separated with the proton conducting membrane here. The one more provision I provide here, some quartz window to allow the sunlight. Imagine this is artificial sunlight. Okay, so the right hand side, I'm going to play a small movie. Okay, you can easily understand. One second. Okay, so look at here. The light will come from here, and particularly photoanode and platinum. Please observe or look at the platinum surface. Okay, what will happen under the sunlight? Okay, after a certain time, the bubbles are coming slowly, and getting to aggressive. So this is nothing but hydrogen gas. Okay, so this is the way we are producing the hydrogen gas in the laboratory, and you can imagine this small volume can be, further developed in a big electrolyzer or photoelectrocatalysis cell, and you can enhance the hydrogen quantity from micromole to milli level as well as a liter level. Okay, again, go back the pointer. Okay, So what we are doing in Harriet University, of course, we are developing a wide range of photoelectrocatalyst or photoabsorber material for anode purpose as well as cathode purpose. The modified TaO2 as well as alternate TaO2 structure. Some of the works are already published, some of the works are still in progress. And okay, let me go to a little bit further into the technology side. Before start any technology, we have a question, how much efficiency we can obtain from the particular technology. Similarly, one can ask the question, what is the maximum efficiency of solar to hydrogen? Okay. For example, if you are receiving 100 light photons from the nature sunlight, how many light photons can be transferred to hydrogen gas? The answer is, in terms of photoelectrochemistry, how much photocurrent you produce in the circuit, and rest of them, or if you put it in a formula, it will give you an idea. Again, I give you a picture here. It's a theoretical efficiency. I fitted with, I show you in a other way. X-axis is the wavelength in terms of nanometer. The black color solid line is the absorption spectra of the nature sunlight. Okay. The one interesting point, the maximum or major light photons or falls in a visible wavelength region, that is in between 400 to 800 nanometer, but unfortunately very poor amount of light photons received in a ultraviolet region. Okay, the first choice, if you want to go any kind of solar to hydrogen or solar to any other application, the photoabsorber band gap should be within 400 to 800. Okay, the second question, the second point, whenever you choose the, tapping the light photons in a higher wavelength, obviously the red color curve is the solar to hydrogen efficiency. It gradually increase. Okay, because according to this formula, the photocurrent is also increasing. Okay, now the question is, if we increase further above the 800 nanometer, does the tendency is continue? No. For example, if you convert it into electron volt, if you go further like a lesser than 1.23 electron volt, the electrode or the semiconductor doesn't work for a PEC water splitting property. Okay, I will explain you why in the next slide. Again here, in terms of ohmic losses and kinetic losses, the optimized band gap energy is 2.03 electron volt. Nothing but if you make it, if I make an extrapolate, it's maximum 16.8% efficiency we can derive from the solar to hydrogen technology. Okay, so the rest of them all goes to the losses. So at the moment, by using photoelectrochemical technology, you can approximately 17% of the solar energy can be transferred to hydrogen fuel. Okay. Okay, for your quick understand, I summarized the different progresses going around the world on the photoelectrochemical technology. I categorized in different category. One in the research going on material side, the research going on process side, system side, sustainability area, and how people try to find the alternate feedstock in replacing the fresh water. Okay, so I have only 10 to 12 minutes. So I will quickly explain what is the recent progress at the moment. So in terms of material, people are working on how to enhance the light harvesting. As I mentioned, the most of the solar light absorption is happening in a visible wavelength region. And second one, synthesizing the co-catalyst material and as well as to design the platinum free cathode, because platinum is very expensive. Again, someone start in this area, the first question, how to choose the semiconductor catalyst. Okay, there are plenty of semiconductor catalysts already developed in the research area. For your understanding, I give a band gap energy position of different semiconductors here. We already published this paper. If you have a time, I suggest to go through this article. Here, take in terms of electrochemical water splitting window 1.23 volt. I put the reference normal hydrogen electrode volt in a y-axis and fitted on the conduction band and valence band positions. Okay, take some example like a TiO2. It's a well-known popular material. The valency band is higher than the 1.23 volt. So this material is absolutely fantastic for water oxidation process. Okay. But in terms of this material, for example, nickel cobalt oxide, sorry, maybe I can say, okay, zinc ferrite, for example, this valency band position is lesser than 1.23 volt. It absolutely doesn't work for water oxidation. But in terms of conduction band, whenever it's higher than 0 volt, it's very good for hydrogen evolution reaction. For example, TiO2 is fantastic, and zinc ferrite is working for hydrogen evolution, not water oxidation. At the same time, some of the materials are lagging, SnO2 is perfectly fit for water oxidation, not for hydrogen evolution. So now you can understand band edge position is the key for catalytic process. So if you go for water oxidation process, you have to carefully choose the valency band should be higher than 1.23 volt. If you go for higher hydrogen evolution reaction, the conduction band position should be above 0 volt. Okay, let's move quickly. The solar light harvesting, particularly visible light band gap energy materials, are very important. For your understanding, I can say even a single system like any material, zinc oxide, TiO2, if you are altering the nanostructures, for example, instead of flat structure, if you produce a nano rods, and if you decorated the same nano rods on silicon nanowire, you can see either the optical absorption is increased like a y-axis. You can see here absorption is significantly improved from 4 to 10, or it's shifted from here to there. Okay, so either way you can increase the absorption quantity or shifting the band edge position from the UV to slightly towards the visible wavelength region. For example, TiO2, same material, but different types of synthesis process. The commercial TiO2 P25 brown color is here. It's a commercial powder, but we synthesized, I synthesized during my postdoc period and some different time. For example, hydrothermal spray coating TiO2 nanowire. See, you can significantly you can shift the bandage from UV region to slowly towards the visible wavelength region. And also WO3 bismuth vanadate. If you compare the only WO3 is here, if you coated with the partner material bismuth vanadate, you can shifting from here to there. That means you can having a lot amount of solar light photons from the natural sunlight. The other strategies, doping in a material, in a host material. One good example is nitrogen doping in TiO2. This is a TiO2 lattice image I adopted from the others report. For your understanding, I give the picture here. The doping can be in a different way. One is the substitutional nitrogen doping. That means removing one oxygen and put the nitrogen in a bond, or industrial nitrogen doping, coupled with oxygen vacancy. There are different methodology, different way you can do it. Okay, for your for simple understanding, I provided one of my previous report here. Compare the TiO2 photoelectrochemical hydrogen performance in terms of JV or IV. Compare the TiO2 is a brown color one curve is here. But if you, after the doping of nitrogen, the green one slightly increase. And further, if you coat with gold nanoparticle, it's gradually improving from here to here to here to here. Okay. So whenever you do the doping or surface modification process positively, you can get the hydrogen amount also gradually increase. The other one is called co-catalyst. That is a dark catalyst decorated on the PEC material. The green color particles, balls, are photoelectrocatalytic particle, and the dark color ones are dots or black dots are co-catalyst. Okay. Again here, I versus V curve. The one without co-catalyst, the curve is here. After coating, it's shifting the lower applied potential. In particular condition, for example, here the performance is very poor but after co-catalyst coating here, it's significantly increased. So this is the beauty of co-catalyst decoration. So I would suggest to go through this very fantastic article published by Professor Conley from China. Again, if you are developing a multi-layer as well as but careful with the band gap energy structure. Okay, so if you are go for a different multiple layers, so every layer acting as a photo absorber, it adding the more amount of light harvesting, and of course you can increase the overall performance. And in terms of process, so it's very important to accelerate the charge separation or charge collection. I will take a couple of minutes to explain to you how to enhance the charge collection and charge transport. So whether you are working in electrochemistry or photoelectrochemistry, you must understand the term electrode-electrolyte interface. What is that? Okay, so I'm going to explain you for simple one. Okay, once you fabricate the electrode, okay, so this is the substrate. This is a FTO substrate or ITO or steel substrate. For example, this is a nanoparticles of tungsten oxide and bismuth vanadate. It is a good photo absorber as well as photoelectrocatalyst for water oxidation. There's a scanning electron microscopy image for, you can see the visibly the particle size. I thank my postdoctoral fellow, Dr. Logu, for observing this picture. Okay, take the substrate. When you are coating the photoelectrocatalyst, and of course, when you immerse in a water, you can see the interface photoelectrocatalyst. That means electrode and electrolyte interface. So this line is called interface. Okay. Now the point is, as soon as you immerse the semiconductor in electrolyte, the straight band is slightly bending in order to manage the balance the energy level. Okay. This is the overall thickness of the electrode. Okay. For example, from here to there. Okay. Under the sunlight or any light irradiation on semiconductor, as I mentioned, it produced the photoelectrons on conduction band, photocols on valence band. And now the question is how the electrons are traveling from this end to the substrate, because it has to transport to the cathode area. Similarly, the photoholes should be transport from this end to the electrolyte. Be careful. So now I'm going to explain how the charge separation or charge transport from these interfaces to the substrate or from these interfaces to the electrolyte. Okay, so the Ln is called diffusion length. Every semiconductor have a two parameter. One is the diffusion, electron diffusion length and hole diffusion length. That means the maximum distance electron can travel in the particular material, or the maximum distance photoholes can travel to the electrolyte. Okay. Suppose if you are increasing this thickness from 1 micron to 2 micron, 2 micron to 3 micron, now the question is whether the electrons can effectively transport from the point of any point of injection or top of the layer to the bottom of the layer. It is similarly from bottom of the layer to the electrolyte area. Now the question is, do thickness influence the charge recombination process? Okay, I'm going to take two materials. Okay, this is the band gap, carrier mobility, and diffusion length of several non-photovoltaic grade semiconductors and photovoltaic grade semiconductors. I will explain with a identical band gap material, bismuth vanadate, non-PV grade, and PV grade cadmium sulfide. Look at closely. These both material have a 2.4 electron volt. See, both are identical band gap energy material, but in terms of diffusion length is different. Bismuth vanadate is a very poor diffusion length, only 70 nanometer, but in terms of CDS is fantastic, 3 to 8 micrometer. Even though the both semiconductors have an identical band gap, but the characteristics of diffusion length is different. That means if you prepare the very thick bismuth vanadate layer above 70 nanometer, the charge recombination will happen or poor charge transport will happen. Okay. The result is in literature you can find the bismuth vanadate can produce in photoelectrochemical current density, for example, 1 to 4 milliampere per centimeter square. Cadmium sulfide is quite good. It can go to 10 to 12 milliampere. Okay. Now you keep in mind the thickness is very, very important parameter in charge transport or charge separation process. Again, why charge separation is important? I don't have much time, only 5 to 6 minutes. I will wind up. So Professor Doman published a good article in Nature. The idea is why the charge separation is important, photocatalytic or photoelectrocatalytic, whatever it may be. Under the sunlight irradiation or any light irradiation on semiconductor, if you effectively separate the electron and hole from the surface, go to the particular like a oxygen evolution reaction or hole for a hydrogen evolution reaction, perfectly 100%. If you separate it, you can get the quantum efficiency 100%. For example, look at here, wavelength versus external quantum efficiency in percentage as well as the absorption percentage. Look at the black color solid line is absorption of this particular semiconductor material, and if you make it a very, very dedicated charge separation in a targeted sites, you can achieve the quantum efficiency of hydrogen generation 100% or near to 100%. So this is the first article proof of concept demonstrated, okay, in a why charge separation is important to achieve 100% efficiency. Of course, in terms of system side, now researchers are thinking to introduce the self-driven PEC fuel cell. as well as how we can integrate with the photovoltaic cell for producing a sparm, low cost or to avoid the energy input from the external system. One answer is a tandem cell. Tandem means a coupling with photoanode, photocathode in the circuit. Both sides, it's a photoabsorber and producing the involving the catalysis reaction. The one report we reported in 2015, we introduced the kind of quasi-artificial leaf like a front and back coating. For example, the top layer is a cadmium sulfate quantum dot sensorite TaO2. The bottom, the same one, but it coated with molybdenum sulfate catalyst material, front and back like a leaf structure. And we introduce and compare with the typical platinum counter electrode, typical PEC cell. The brown color one is the solid curve IV is a typical PEC cell, and this one is replacing the platinum with this type of leaf structure. It's quite interesting here, but keep in mind the surface area of the platinum and this one is not similar. But one point interesting, in zero applied potential in terms of RHE, that means no applied potential in the circuit, okay, these structure are quite interesting to produce small amount of hydrogen, okay. So this for spontaneous hydrogen fuel generation, this type of tandem structures are very interesting. And now a recent trend is going on to coating the water oxidation catalyst on solar cell, because here the solar cell produces a small amount of or a significant amount of electric potential to drive the catalyst process, okay. And of course a typical wired configuration of platinum. And the one good example is you can refer this Nature Communication article. So the photo absorbing by the solar cell as well as the efficiency of solar cell is always high, for example 15 to 20%. So you can top up with the water oxidation catalyst, obviously the efficiency will go high. Similarly, the one end you can coat with the water oxidation catalyst, other end you can coat with hydrogen evolution catalyst. It's called monolithic, absolutely, and it produces a significant amount of hydrogen. But keep in mind, the corrosion of the solar cell is very important because you are immersing inside. The one good example, recent days, many groups are adapting the perovskite solar cell and coating with water oxidation catalyst and hydrogen evolution catalyst. But the stability of perovskite solar cell in water is very challenging one. Okay, and finally the sustainability. Quickly I will finish it. Under the light radiation, the one problem is if your charge separation is not proper, that means either photohole or photoelectrons trapping in a surface, these charge carriers is vulnerable to damage the semiconductor itself. So charge separation is very important. Perhaps if the material itself have a lot of defects, so how we can avoid it? The one way is you can coat the passivation layer coating, for example, amorphous coating here on the top of the layer, you can avoid the charge trapping. So obviously you can protect your material, okay? And the second point, the pH is very, very important. Many of the researchers are missing the information. See, look at one example, bismuth vanadate photoanode, stability, the band gap change in the different pH. So based on the pH of the solution, the band gap change, once the band gap position change, maybe the catalysis process will affect. Okay, so keep in mind the pH of the solution during the reaction or after the reaction is very important. Okay, I don't have much time. I will come to the conclusion, almost 40 minutes. So nowadays we have to think about how to alternate utilization of the fresh water in either electrochemical cell or photoelectrocatalysis process. Because if you are using the fresh water in terms of in a large scale hydrogen generation, it will affect the food chain of the society. So there are options like biomass waste, wastewater pollutant, seawater. These are all the good remedy to replace the fresh water. So recently we published one review article how the simultaneous PEC reaction for hydrogen generation from wastewater or biomass valorization. So this is a good scheme. You can introduce the wastewater in anode compartment and it can oxidize into minerals and CO2, and right inside as usual it produces the hydrogen gas. Okay, so simply coupling the wastewater treatment and hydrogen is a good concept at the moment. So I suggest to go through our recent article published in Energies, and we give different ideas and what are the challenges and opportunities in this area. Previously, our group published how we produce the hydrogen generation from the metal mine pollutant wastewater. We collected the real-time metal mine pollution in the cathode compartment, and coupled with the photoelectrochemical process, we produce the hydrogen generation. Finally, we got some interesting point, like some of the metal elements present in the wastewater, it coated on the cathode, it's simply metal recovery. So the new ideas always appreciable, instead of a typical straightforward water splitting like a hydrogen and oxygen, you can couple with wastewater treatment or any biomass valorization or metal recovery or any other ideas. Okay, so I can say if we want to push the transition readiness level from 1 to 3, most of the photoelectrochemical process is lying in between 1 to 3. We need to go 4 to 5 and further in a pilot scale and pre-market stage. So we need to think about how we can push or couple in a different application or coupling different sectors. Okay. And finally, from the last 25 to 30 years, approximately 130 semiconductor material tested in anode and cathode. The most of the materials in a UV bandgap material shows a fantastic efficiency, like a 10% or more than 10%. But in terms of visible material, it shows less than 10%, very poor. Okay. So we need to keep in mind how to accelerating or push the visible light semiconductors performance. Why visible light semiconductors? These are all the materials good for transforming the natural sunlight to the catalysis process. Okay. Again, finally, the market demand is solar to hydrogen is 30%, but there is a positive response signal is getting. We can push our current performance to 10%. The one good reference is electrocatalysis process coupled with photovoltaics, PV integrated EC is a very, very high amount of hydrogen efficiency. But one challenge is it have a high complexity in terms of integration. In terms of photocatalysis, it's a very low complexity in system side, but it shows a very poor performance. So, but PEC can manage the PV plus EC as well as photocatalysis process. So still PEC is a good method to push the hydrogen generation towards the market need as well as to manage the system complexity. Okay, I'll come to the conclusion. Photoelectrochemical hydrogen generation is a fantastic process to support the net zero technology, clean and renewable source. But still, we need to take a lot of care to understanding the energetic structure of PEC material during the process or post-process, very important. Okay. And of course, we need to make some life cycle analysis, how this system is sustainability and affordability, techno-economic analysis are very important. And more new ideas are welcome, appreciated. And still, we need to take more care on reactor design, how the charge transfer is happening, evaluating the apparent quantum yield, how we can integrate with the renewable sources like a solar PV as well as wind stuff and alternate feedstock. So if you are working in this field, please take care of these points. Some of the new researchers, young minds, if you want to enter into this field, please keep these challenges in mind. Okay. I hope this lecture definitely will give you an idea fundamentally how the photoelectrochemical hydrogen generation is happening and what are all the opportunities and challenges in this area. I would like to thank all two persons, particularly my former PhD student Catherine Davis from Swansea University and Dr. Logu, Newton International Fellow, for providing the fantastic data for this presentation. And of course, I always my special thanks to my mentor and teachers, Professor Mercedes, Professor Pujishima, Professor James Durant, Professor Dave Osley from Swansea, and of course my colleagues in Cranford University. And of course, big acknowledgement goes to my collaborators, their constant support for our different, you can see different slides, different very good results. These are all I'm getting from my collaborators. And thank you very much for your patience to listen my lecture. And of course, if you have any question, please email me. And of course, we are most welcoming joint collaboration work. And please support the clean energy and save our environment. Thank you so much.
Thank you so much, Professor Sudhakar. It is a really nice talk, and I know you are busy, so you sent us the pre-record video yesterday. Thank you so much for your time. We are very short time for the panel discussion and Q&A, but I have a couple of questions. As I can see, we have Pankaj Yadav on board. So, Dr. Pankaj, could you mind to answer me? There is one question that what is the current challenge of fabricating perovskite solar cells? Is just the material or the environment? What exactly?
Thank you, Anurag, for your question. So if I will prioritize my problem on this fabrication of the perovskite solar cell, so I will put environment of a lab environment, or like the humidity level, it is on the higher levels. So it will be on the top. So that need to be controlled right now. You have to done most of your work, let's say 80 to 90% on the glow box condition. But I wish that in perovskite material synthesis will be come up with the solutions like open air synthesis. So that will definitely put this technology in an upfront way.
Yeah, that's really a great point. Another question for you, Dr. Yadav. How did you come up with the idea of inserting graphene in between zinc oxide and perovskite for better performance?
Yeah, so we had in this experiment, we had time like when we use the ZNO. So most of the time when we use the perovskite on top of the ZNO, it was not converting directly on perovskite phase. It will residue yellow colored phases. So that shows that perovskite is not been formed. So we thought that we can put a small graphene layer, a single layer graphene layers that can suppress the properties of the ZNO2 into the formation of perovskite. And then when we use the graphene, we found fantastic results, proper perovskite synthesis. And even though this graphene help us for perfect nucleation or the crystallization of perovskite. So this was on the graphene. Later on, we have tried different materials also, although I have not covered in these slides, but you can look into there, the fullerene structures, derivative of fullerenes also we had tried.
Yeah, I would like to jump on your point in this, that do you mean that if we use graphene, so we can stop the leakage of lead iodide?
Yeah, correct.
Okay,
Yeah.
that's interesting. Another questions for you. You're famous. So since the PSC stability influence different parameters, what's your view on having a standard testing protocol for stability analysis?
Sure. This one is a very interesting question, and it is from the Shrira. Yeah, Shrira. Well, looking into the perovskite stability, if you look, most of the perovskite community, they follow the standard which has been established for the silicon solar cell. That's going to be very harsh for the perovskite. But look the success of perovskite when people are trying for the space application. They are one of the most stable. So we have to tune our stability parameters according to this new material. We don't need to copy all of the standards for the what we had for the silicon solar cell. So I guess more attention is needed for the stability. New protocols like as this our study highlights that measurement of hysteresis is important, which was not done as systematically in the literature. So we believe that when such kind of more data will become, I guess not machine learning will be stopped here, might be more information we can get it. So I guess more data generation right now is needed. So more protocols, when more people will be find out. So I guess some perfect protocols will be formed for perovskite.
So do you think that the machine learning can help us to predict all these parameters and stability information?
Definitely.
So that gives us an advanced information before going for practical or commercialization of business. Yeah, that's great. Thank you so much. No, we don't have any more questions for you. And thanks a lot for your time and to be presented here and accepting our invitation. Thank you so much. We are glad to have time. Thanks a lot. We have a couple of questions for Professor Sudhakar, but unfortunately he is not live. So I can see Shalini M. If you have any question, you can ask him directly. He has already shared his email ID. Please go through Heriot-Watt University Professor Sudagar Pichai Muthu and just email him directly. He told me that if somebody has any question, he can ask through email. Otherwise, he will be here in between 11 to 12 UK time. So please, you can chat with him in person in Zoom so that he can address your answer and anybody has any question. Okay, thank you so much. Thanks for joining. We will stop here for a short comfort break. That's a 10 minutes comfort break. Take a cup of tea or some comfortness. We will be right back shortly after 10 minutes. And then we have Abhi Banerjee straight away from right now. He's in Bangkok. So we will hear about some battery related recent activities, what is going on there. So stay tuned with us and see you in 10 minutes, after 10 minutes.
Okay.
Welcome back, everyone. I hope you had a very good comfort break. We have our next speaker, Avik Banerjee. So before starting an official introduction with him, let's connect with him first of all, because he is in right now in Bangkok airport, what I know. So let's connect with Avik first. Dr. Avik, are we visible? Oh, thank you so much for joining. Good to see you, and thanks for connecting with us. I know you are traveling and in a messy condition, but thanks. It's an honor for us, to have you on board. We are visually all good from our side, connection, everything.
Yeah, I think everything is fine. Am I audible properly?
You are audible and also visible properly.
Oh,
Absolutely.
thank
Yeah,
you, because
yeah.
I just got stuck in Bangkok airport during my travel.
No,
So sorry. I was just worried about some kind of a noise announcing is coming around. But then if it is I'm fully audible, then I think it's totally fine.
you are
We
audible,
can.
visible perfectly, but before you start, let me introduce to the audience of yours. Ladies and gentlemen, Dr. Avik Banerjee is here for our next industry talk, and he is currently the team leader of Research Institute of Sustainable Energy, in short RISE, under the TCG Crest, India. Avik has more than 10 years experience in design, novel chemical synthesis, characterization, and structure property performance relationships of various materials, particularly materials for solid state electrochemical energy storage. At RISE, at this moment, he works on the underlying causes currently hindering the solid state batteries, silicon and lithium metal anode. He also provides practical approaches towards enabling safety, higher energy density, and fast charging batteries. Very interesting. His contribution to research in this field has been proven over 30 articles in archival journals, and he holds 5 patents. Promising. Over to you, Dr. Avik. Once you are ready, please share your screen. Thank you.
Thank you, Anurag, for the invitation, and then good morning or afternoon or evening to everyone, depending on from where you are joining. So let me share the screen. Is it visible to everyone?
Yes, it is visible. All good, all fine, please.
Okay. Thank you. So I think my talk I just condensed in mostly on solid state battery, and I think the solid state as I've been working for a long time on the solid state battery or even different kind of battery technology, I think the solid state battery is something that is a kind of a very futuristic technology. That doesn't matter whatever the areas, energy areas we're working on. These all areas are very much connected, whether there is energy generation, whether there is energy conservation or energy storage. So my expert is like energy storage, which I've been working for last 12 years. And then this is the one subject which I think is very futuristic and has a lot of potentials for future energy storage technology. Um, so yeah, so I think just to start my presentation, I must say that as we are getting more and more dependable on the renewable energy, such storage has become more important. So if you see the cost of the solar and the cost of the wind has been gone down so much for the last 10 years, right? I mean, it has drastically gone down. But the problem is like unless you store these, the renewable energy, whether it's from of the coming from the wind or coming from the solar, then this is not used because these are kind of a intermittent form of energy. I mean, nobody knows when wind blows or not. When half of the world is sunrise, half of the world is under the sunset kind of condition. So the storage is very important. And then if you consider especially for the grid, I mean the 90% of the cost goes for the storage. The cost installation for the solar is quite cheap nowadays. So that is why the storage is very important. And I think there are primarily two applications. One is something is electrification of the vehicles. So far we are still depending on this IC engine. So if we have more, I mean, at home it doesn't matter, right? I mean, you can always plug in your device and charge your or mobile or iPad or whatever. But then how can you let the electron reach to a car? I mean, you cannot just plug in your car and drive your vehicles. So the efficient storage in the car is very important for the conservation of the fuel, to reduce lot of greenhouse gases and everything. At the same time, if you are getting dependent on this renewable energy, we are, I mean, very extreme requirement of this energy storage as well. If we cannot store the energy efficiently, we cannot use this kind of a intermediate source of energy like a wind and solar in the efficient way. That is why the storage is important, and the most efficient way to store is nothing but the battery. Okay, I'm not going through all kind of battery, but I think the most important form of the battery is like a lithium-ion battery, which is the highest energy density so far. But there are many problems which I'll explain, and then I'll say how the solid state technology can solve some of these challenges. So what are the problem? The main problem rises in the battery. There are 4 problems. One is the energy, right? I mean, once you fill up your fuels in your IC engine car, you can go up to like a 600, 700 miles, but you have a restricted energy in the kind of lithium battery. For example, we cannot go like a Tesla or a typical car. If you go like a 350 mile is the driving range, you always have to increase the energy density so that in a single charge you can go more and more. The cost is very important also as well. Nowadays, the electric vehicles are very expensive. I mean, the same specification of the IC engine car, if you get electric vehicles, it is more than double of the price. So whoever has like a 3-4 cars, they can only buy the electric cars. But then this has to be like, the price has to be go down so that more and more people can buy this car. That is also very important. Third thing is the safety. I mean, you can see a lot of news are there, right? I mean, Tesla car has like a 80 kilowatt hour car, like a 10,000 cylindrical cell, 10,000 cylindrical cell equivalent to like, kind of a 10 dynamite. So basically you are driving a vehicles with the 10 dynamite. So it's a huge safety problem. And the other is the sustainability. I mean, see in this graph, if you are using this kind of a, the battery for very long year for different kind of application. And then, I mean, once this battery will die, what is the fate of this battery? Okay, so how can we use this battery in the more efficient way and recycle this battery in the better way so that we can use it in the next, the application as well. So the recyclability in terms of the sustainability is also equally important for the battery. Now, whether solid state battery can solve the problem. Okay, I mean, solid state battery can solve a lot of different problems. For example, if you can replace the graphite with the lithium metal has like a 10 times higher energy density compared to graphite. So the thickness amount of the graphite you need and the thickness of the graphite you need, you can just put like a 1/10 volume of this lithium metal, we can solve the purpose of the graphite. Okay, and also in the same volume of the lithium-ion battery, you can able to put the 2 lithium metal. So normally what happens, like we cannot use the lithium metal in the liquid electrolyte because it's very reactive with the liquids as well as it spoons to form the dendrite, and then it fails first and the thermal runaway happens and fire hazard. So if you have the solid, you can use the lithium metal, which you cannot use the lithium and liquid electrolyte. And the same way the energy density can be increased because the lithium has the less mass compared to the graphite. So at the same time you are enhancing the voltage a little bit, but then at the same time you are reducing the mass. So enabling the lithium metal by solid state battery can enhance the energy density of the all solid state, the lithium battery. Other advantage of the solid state battery is that the technology doesn't need an extra cell line. So whatever the conventional cell lines have been established for fabrication of the lithium-ion battery, same cell lines can be established to fabrication of the solid state battery. So in terms of the implementation in the pilot scale, you do not need any extra investment in the solid state battery technology. That is also an advantage. And the other advantage is that whenever you have to have kind of a high voltage battery out, you always have lots of batteries and you have to put into the series, right? But then that actually lot of weight mass is also included in your battery. For example, separators, for example, your AC, your connections, your wiring and everything. Solid state battery has an advantage that in a single module, you can stack as much as possible, and whatever the voltage output you need, you can get it back. So you can get rid of the lot of dead masses in your conventional liquid ion battery, and you can enhance the the volumetric energy density is very higher compared to conventional lithium battery. Okay, the most important is like any kind of solid state battery is a solid electrolyte. There are basically three kinds are normally used: polymer based solid electrolyte, sulfide based, and the oxide based. Okay, and there are many properties. For example, you can see the cost, electrochemical stability, chemical stability, thermal stability, ionic conductivity. But the most importantly, if you see that none of this material can satisfy all the parameters. I mean, for example, what oxide electrolyte, the electrochemical stability is higher. The mechanical property is so poor, you cannot really make a nice processing, high dense pellet at room temperature. Again, if you see the sulfide electrolyte, when you have like very high ionic conductivity, transference number, and but the electrochemical stability is poor, it decomposes very low voltage, so it doesn't suitable at all. And but then what is more important is that not really the the conductivity. I mean, most of the people always say like conductivity is something more important, but what we have realized is not about the conductivity, which is more important. The more important is like the interface. I mean, even see the advantage of the solid compared to liquid is that when the liquid decomposed, it will form some kind of ACI or CEI. Okay, but if there is a crack in your ACI or CEI, then the liquid electrolyte can still infiltrate and decompose again. But in the case of solid state battery, solid is not a fluid. So if you control the decomposition and the proper way, solid doesn't decompose again and again. So if you can passivate the interface proper way, you can run a solid state battery very long. So the main I would say the advantage of the solid state battery is that if you can able to make your interface properly, it will run really very well. It is not like a typical liquid where the decomposition is continuously happening with your cycle. So let's go to a bit deeper about the anode interface. For example, in a solid state battery, the solid electrolyte, you have a lithium metal anode, but lithium metal anode is not stable thermodynamically with any material solid electrolyte. So what happens? It decomposes at the this contact with your solid electrolyte, and it will form like a SCI. Now, depending on the electrochemical stability window, the various materials will decompose and the various decomposition product will happen. But I want to say one more thing that it is not about like the composition of the solid electrolyte is very important rather than like kind of ionic conductivity. For example, here you can see there is a electrolyte, very common electrolyte, which is Li6PS5Cl. And when it is contact with lithium metal, it decomposes to Li2sp2, Li3p, and LiCl. But among these three materials, the two of the material is insulator, one of the material is ionic conductor. So once it is formed, it is basically passivate the interface. There is no, the other content is there which can help decompose this interface again and again. And the other way, if you see, there is another material which has one order higher conductivity compared to your LPSCl, which is LGPS. But when it's contact with the lithium metal, many products form. But one of the products, lithium germanium alloy, is the electronically conductor. So if you have an electronic conductor in your interface, then your interface is the growing interface. It is not like a passivating interface. And once it's growing, it's finally short the cell. So the key message is that even there is a higher ionic conductivity, you cannot use every solid electrolyte. Conductivity doesn't matter much. The most important thing matters in the solid state battery is like how the passivation happens at the interface. That is the most critical things in the solid state battery. Okay, and for the cathode also have the same kind of problem. For example, suppose there is the NCA molecule and you have a sulfide solid electrolyte. Okay, now there is a intrinsic side reaction happens, and you have some kind of a layer on top of the the NCA molecule, and then when the NCA molecule is fully charged, then your metals and at the high oxidation state, then it's more reactive, and then it reacts with the sulfide electrolyte to some much more thicker kind of a the layer on the on top of the interface. For example, here you can see like a black graph. This is a typical solid state battery performance. The black one is the transistors of the bare NCA. Now what we can do, we can, because the NCA is very reactive with the sulfide electrolyte, solid electrolyte. Now what we can do a very thin layer of coating up to 5 to 10 nanometer on top of the NCA particle, which is a lithium niobate coating. Lithium niobate coating is something which doesn't allow to NCA to react with the solid electrolyte. And if we have this kind of very thin coating, then you can see your performance has become drastically, improved. So the NC is getting one of the, the close to its theoretical capacity with having the such a thin coating. And here we also want to mention the same point is the interface and this passivation is very important. Bare NCA doesn't work with the solid electrolyte, but if you passivate the interface, it's a very thin layer of the lithium niobate, which is not reactive with the sulfide electrolyte, your battery performance goes very well. Okay, this is the same slide, yeah. And now I will come to another aspect is the contact resistance. So if you see there is a solid state battery has been, one is the, so the left graph is like liquid electrolyte with the lithium titanium oxide performance. So lithium titanium oxide is like one of the anode which is widely used for the very fast charging. But when you use the liquid electrolyte, you see the, the hysteresis. So the charging and discharging voltage difference is almost negligible. But when you have a solid electrolyte, you have a hysteresis. You see there is a difference in the charging and the discharging. So this is mainly because of this contact resistance between solid. I mean, as I mentioned, liquid, the contact resistance doesn't matter because if you put a liquid always infiltrate and contact every surface. But in solid state battery, once you have to contact between the solid and the, if you have to give a contact between the two solid by grinding together. But once you grinding to them together, there is always a porosity up to 10 to 30%. And whether there is a porosity, you always have like the contact resistance. And from this contact resistance, it can actually give you like the hysteresis in the solid state battery performance. So the giving conformal contact of the materials in solid state battery is also equally challenging. So what we tried a different process. We derived a, the solid state electrolyte, which is solution processable. For example, there is a solid state electrolyte called Na3SbS4. You can dissolve in methanol and water, it fully dissolves. And then what you can do, you can put your cathode material, for example, sodium chromium oxides, and you evaporate the liquid like a water and methanol slowly. Once the evaporation starts, all the solid electrolyte will get attached on top of the cathode materials. Okay, and then if you see, this is the top picture is the the image of the cross section image when there is a slowly controlled evaporation happens and the coating happens. And this is the typical mixture. In the mixture, you can see the contrast difference where the cathode and solid electrolytes are scattered. It is not properly contact. But for example, top picture, you can see there is a more and there's a much more, the conformal contact happens. And you see the difference in the electrochemical performance. The black one, the dotted black one is the just hand mix, but you cannot get any capacity at all. But once you coat it with this process, you can have the capacity of very high capacity and close to theoretical capacity of the sodium chromium oxide. And the same thing reflects on the impedance spectra as well, where the charge transfer impedance drastically reduced in the presence of this, this process where you can, the conformally coat your cathode material with a solid electrolyte. The next part I just want to mention about, the anode part. So the cathode part I mentioned, anode part is mentioned because there is a, the dendritic problem. So for example, here you can see there is one charge discharge profile of one solid state battery. The blue one is something where you can use, this is the charge discharge profile of the NCA, nickel, cobalt, aluminum oxide. This is the cathode. But then the blue one is something where you can use the lithium indium alloy. And the red one, you use the lithium metal. Now, in the blue one, you can see you can charge this solid state battery very well. I mean, you can get the charge and discharge properly. But once you use the red one, you can the lithium metal. You can use the red graph. It started charging, and after some time, the voltage declines, and then it goes to zero. This is what we call the soft shortening, and this is very the common problem in the solid state battery technology. I mean, the solid state battery concept came to enable the lithium metal, but then people realize the lithium metal enabling in solid state battery even more difficult than kind of a liquid. But it is equally challenging. But if you can solve this problem, this is like a $1 billion problem. Now, what we did one very controlled experiment. We tried to understand how the mechanics works for the preventing the dendrite. So this is our typical solid state battery cells that we put a kind of a load cell to check the pressure of this our solid state battery and see how does the stack pressure the influences the the dendrite formations. For examples, once we this is a typical fabrication process. You have a solid state the electrolyte which you put a pressure of 370 megapascal, and then you put both side lithium and give a 25 megapascal pressure, and with the stack pressure you run the cells. But with this 25 megapascal pressure, if you put like a very high pressure of 75 megapascal, cell short immediately. I mean, you do not have to bias it with current. Without having any current, the cell just short. Okay, now if you reduce the pressure from 25, 20, 15, 5, if you see the cyclic performance of the lithium metal in the symmetric cells is getting better and better. So from this experiment, what we have learned, the lower stack pressure is very important compared to higher stack pressure when you considering the lithium metal cycling in the solid state battery. And then we try to analyze why does it happen. So this is a typical, we did a, the tomography, X-ray tomography, and then find out what happens. For example, 5 megapascal, before and after, we don't see any difference on the tomography image. But when you use the 25 megapascal, what we have seen, there is a voids. You can see there is a cracks happening and the contrast difference is happening. And we believe this kind of a voids or our formation happening because of the lithium dendrite formations. We cannot really distinguish whether lithium dendrite or not, is because lithium is so light that you cannot really detect with the X-ray. But we find some voids, and we believe that these voids are coming because of lithium dendrites, lithium metal going inside as a dendritic form. And when you use the 75 megapascal pressure, you can see the whole pellet broke. So without any kind of external biasing, the cell short. Okay, so the lower stack pressure is very important for the cell cycling. Now, whatever the cell which was we didn't able to run at the high stack pressure, in the NCSL, the same cells run at the 5 megapascal pressure with the lowest.
Sorry, everyone. I think Dr. Avik has lost his internet connection because he is presenting from Bangkok airport. We will try to reconnect him. Please allow us some time to connect with him. We are very sorry for this inconvenience.
He lost the connection. Can you join again?
Yeah, we just realized he lost the connection due as he is presenting from Bangkok airport. So we can understand how unstable internet there is, but please allow us some time, and I sincerely apologize for this disturbance. I think he is back. Hello, Dr. Avik. You are on mute.
Am I audible now?
Yeah, you are audible and visible. Both. I lost your connection. We can understand.
So,
yeah.
Yeah.
Yeah. Please restart or resume your presentation.
Yeah.
Thank you.
Yeah, so I was just mentioning that we have to reduce from the thickness of the solid state pellet to increase the energy density. Currently, the kind of thickness we are using, which is close to like a the 1 mm of 700 micron, we have very limited energy density. So if we can reduce down the thickness up to like the close to 15 or 10 micron, then we can have the energy density what we are expecting, like around 400 watt per kg or beyond that. So that reducing the thickness of the solid electrolyte is very important for the solid state battery. Now, and now whenever you consider the reduce of the the thickness of the electrolyte, you have to consider also many things. For example, the mechanical, I would say, like the strength of the membrane, how does the uniform of the solid electrolyte has been formed, and the slurry's viscosity, and but the most important thing what I had to want to mention is that normally whenever we make a battery, we use the NMP, we use the PVDF binder, mix together, make a slurry and coat them. But in solid state battery, you cannot use them like these some of these materials which are commonly used for fabrication of this slurry and the coating. Choosing how to choose the binder and the solvent to process the solid electrolyte in a thin membrane is extremely challenging. I just want to say one example here is that, I mean, once you have this is a solid electrolyte called Li7P3S11, which is very high conductivity, close to liquid, right? But then once you put into different kind of solvent like water, THF, NMP, acetonitrile, DMC, toluene, and xylene, all kind of solvent. These solvent have a different polarity index as well as the dielectric constant. I mean, you see this. Most of the cases, the color changes as it dissolves. I mean, it is only stable in the toluene and the xylene. So none of this, the kind of a, the material, other solvent we can use to process this material. And then you can correlate it with this kind of a dielectric constant. The higher dielectric constant reacts much more, but the lowest dielectric constant you can see about this 2.4 and 2.3. What is the toluene and the xylene? They are actually stable with this kind of a electrolyte. So what kind of solvent you are choosing to process is extremely important. Same thing. So the other thing, whenever you choose the solvent, you have to also think what kind of binder also you have to choose, which is also compatible with your solid electrolyte, as well as it should dissolve in your solvent as well. For example, there are 4 different kinds: PO, PVDF, NBR, and ACBS, or the butyl rubber. And among them, you can see ACBS is something which is getting dissolved in toluene and the xylene. So logically, when you make a solid state battery, then there is the only possibility for this particular solid electrolyte to use the toluene and xylene kind of solvent and ACDS kind of binder to make a solid state electrolyte like a membrane. And then here what we did, we made a very thin membrane of 55 micron, which is very flexible and rollable kind of a thing. And with that one, we should able to, and conductivity has reduced a bit from 1 millisiemens to 0.7 millisiemens, but it has not reduced that much that we cannot run the cells. And with this kind of membrane, we are able to run this lithium plating splitting for very long cycle life. And additionally, there is an advantage is that some of the sulfide solid electrolytes, they are prone to produce a lot of sulfide gas. Okay, if you keep it at room temperature, coating of this kind of polymeric materials, it will reduce to to emit all those gases as well. But we have found that the H2S generation has been reduced a lot if you use this kind of low, the polarity or less functional group polymer into for processing of your solid electrolyte. And then this is something very interesting. I want to show you that why really solid state battery is so important. Here you can see there is a solid state battery pouch cell. You cannot do this experiment in the typical, the liquid ion battery, where even you do it, either depending on the capacity of the FED, either it will catch fire or it will immediately turn off the light. But here you can see, if you even you cut the solid state battery, you can still, the LED is still glowing. And the second experiment, you can see the temperature of the hot plate is almost close to 200. There is no swelling, nothing is happening on this kind of a solid state battery. But you don't really dare to put any kind of liquid and battery there. I mean, that is the advantage of the solid state battery technology compared to the lithium ion battery, conventional lithium ion battery technology. So that is my slide. So thank you, everyone. I just tried to give a very general, the information about the solid state battery and how it is really important and what are the critical challenges, and if some of these challenges can be really solved, then this is going to be very future of the energy storage technology. Okay. So if anyone has any questions, feel free to ask me.
Thank you so much, Dr. Abhi, and really much appreciated that you have connected in this situation in airport. It's one a great experience for us also. Thank you. Thanks a lot. We have a few questions I can have. I have
Yeah,
a
sure,
question if you
sure,
are
sure,
with connections that
sure.
what is the current challenge that you are facing right now with the solid state battery? I mean that it's just only the lithium scarcity or it's the durability.
So I think the biggest challenge of the challenge of the solid state battery is the lithium metal dendrite. I mean, there is reports where you can make your solid state battery cycling at 45, 50 degrees Celsius, but room temperature cycling of solid state battery with the lithium metal, there is not a single report, and this is a $1 trillion problem. Whoever can solve the problem will run, with win the race. So there have been so many startups, so many companies, so many fundings. You can see the Toyota is pushing his roadmap every year. It was supposed they are supposed to, kind of bring their solid state battery car on 2020. Now they have pushed their goal into 2025. So it is not that easy, I would say. It is a time-consuming process, but this is what our researchers do. I mean, they try to understand the fundamental aspect of this. Why does it form? How to mitigate this to really solve this challenge? So I think this is the biggest problem. I mean, this problem, cathode is not that much, I would say nowadays. Even the membrane, there is a process. More and more, new process are coming where you can reduce down the thickness. But the main problem is like energy density and power density, which is basically limitation come from the anode side and the lithium metal. That is, I think, the biggest challenge.
Okay, you can stop sharing your screen. That consumes more
Sure.
data.
Sure.
So, yeah, no problem. One last question for you that regarding this is the R&D part, that's fine. But when it comes to the policy, considerations that we have to make the energy policies and all this administrative board level discussions, there is a high point of the recycle things. How we can recycle that? It's not only the lithium or the parts also. So how do you define all this? How you can tackle solid state batteries?
So I think it is a very good question. So recycling is a big problem. Lithium metal and cobalt, I think nickel has been solved a lot in the conventional battery, and then battery baking, pack, module, and everything has been future designing and proposing such a way it will be better way to recycle. So that is one of the challenge. I think recycling is very important. Nowadays, the cost of the recycling materials is more expensive than the raw material if you get from the normal vendors. That is the problem. But then in solid state battery, actually, I had one data I have not shown you here, which is also been published that recycling is much easier, much easier than the typical the lithium ion battery. And then you can recycle every single material individually, which is very cost effective compared to your pyrometallurgy or hydrometallurgy in the conventional battery, where you have to dissolve everything or you have to burn everything. So there is the paper I can share with you that that paper says the solid state battery recycling actually recycling aspect, there's a much, it is already is kind of established, protocols are there, and it's much more cheaper and greener compared to conventional lithium battery.
And as you are here, we don't want to leave you soon. So just one last question. What do you think? Okay, there is another question from an audience. So hello, hope you're online. Yeah. So what's the major factors behind the durability of solid state batteries?
See, as I mentioned, the major factor is the lithium metal anode. That is the major factors. And I think the next factor is the interface, cathode interface. But then cathode interface, there are many ways that you can mitigate the challenges or the bottlenecks of the cathode interface. So that is not a problem. The main key points is coming from the anode interface. One is the reactivity of the lithium metal with the solid electrolyte. And the other is that whenever you go for the high current density, it's always prone to form dendrite. These two are the problems where the battery mostly fails. Degradation happens in solid technology.
So here is one point that is there any alternative of lithium or no?
Yeah. Yes.
Yeah. Okay, can we go for sodium and batteries? I can see
Yeah,
there is.
yeah. So sodium, you can see, is more reactive than the lithium, of course. So in terms of the anode stability, the reactivity part, for reactivity issue, see, even in lithium solid state battery, you have solid electrolyte, which are a bit stabilized in the anode side. I would call the self passivation layer happens. But in solid state sodium ion, there is not a single electrolyte in the whole world where it can passivate the interface and you can run with the sodium. So nowadays people are using like sodium tin alloy, sodium antimony alloy, all those kind of material as the anode side. But then it's, of course, I mean, you can reduce the energy density will be compromised. But if you want to go for a grid storage, doesn't matter, right? The energy density. You want something very safe and low cost. So all solid state sodium ion battery is has a prospect, but I don't say that it has a prospect on the the high energy density application, for example, the electrification of car, but it has a prospect on the grid side where you have lower cost, safe, and very long cycle life with not sodium metal, rather than sodium metal like a sodium tin or sodium antimony kind of alloys.
That's incredible. Thank you so much. I think the discussion is worthy to all the participants and hope we have benefited from your talk. Thank you so much, Dr. Ravi.
Thank you.
And a big thank you. Thanks a lot.
Thank you. Thank you.
See you. Yeah, take care. We will move to our next speaker, who is Dr. Al-Zahrani Musad from Imam Abdul Rahman bin Faisal University, which is in the Kingdom of Saudi Arabia. So before moving to Musad's talk, let's have a quick introduction. So Musad received his PhD in renewable energy from the University of Exeter in 2022 under the supervision of Professor Tapas Malik, and his work focuses on research into ultra-high level concentrations of photovoltaics. So he is one of the leading experts in energy modeling and concentrated photovoltaic systems. Before undertaking his PhD, he worked as an energy engineer at the Industrial Assessment Center at the University of Dayton, USA, from 2015 to 2017. With this, I would like to invite Dr. Musad Muhammad Al-Zahrani. He is currently a lecturer at Imam Abdul Rahman bin Faisal University, Saudi Arabia. Over to you, Musad.
Assalamu alaikum wa rahmatullahi wa barakatuh. Good morning and good afternoon from Kingdom of Saudi Arabia. It is my immense pleasure to be in International Energy Conference on Solar Material and Technology. My name is Musa'ad Al-Zahrani. I am Assistant Professor in Mechanical and Energy Engineering Department at Imam Abdul Rahman bin Faisal University in Kingdom of Saudi Arabia. I'm really happy to be part of this. I enjoyed all the talks from yesterday, and thank you for all the speakers, and I'm very excited for the rest of the day. Briefly, I have conducted and earned my PhD degree from University of Exeter Environmental Sustainability Institute, Solar Energy Group, under supervision of Professor Tabas, Professor Asif, and Professor Senthil. So today I'll be briefing out my project and what has been developed through my time in ESI, and my speech will be about developing and demonstrating an ultra-high concentrated photovoltaic system beyond 3,000 sun. So I'll start my talk through those agenda. I will be starting with the introduction and limitation of the concept of CBV and BVT system, limitation and concept of CBVT system. To develop an ultra high concentration ratio, we have a key question we need to answer, like why we are aiming for ultra high concentration ratio. What is ultra high concentration ratio? The system design is based on a Fresnel lens. We need to know why it's based on a Fresnel lens. And what are the challenges to address this an ultra high concentrator? Then we'll go through the research methodology, how we have tackled those problem and challenges, how we have generated data, and how we feed in those data into simulation, and we use the preliminary result to design and develop a system. And then we will show the conducted outdoor experimentation, and we'll end up by the result. So to understand first and to build the bases, we need to have an idea about the classification of concentration ratio. So it's classified as low, medium, high, and ultra high in those range of suns. And clearly we are targeting an ultra high concentration ratio. So the system will be aiming to have, as in the title, more than 3,000 sun. So we are aiming for more than 1,000 sun here in this category. And once we say 1 sun, we mean 1,000 watt per meter square of energy. So to start with, there is we look into the two common systems, CBV and BVT. So we have CBV, which is concentrated photovoltaic system. It's mainly coming to replace, the silicon materials, with inexpensive optics, imaging and non-imaging optics. The idea of this, it's very simple and well known. It's just to be more efficient in terms of landing and in terms of resources and silicon materials. But using those optics to increase solar irradiance will increase temperature, and once we increase temperature, we drop electrical efficiency, and we will generate heat. So we have two problems, at the same time. We are dropping electrical efficiency and we are generating heat. On the other hand, we are generating heat that is not utilized. On the other hand, there is photovoltaic thermal, and photovoltaic thermal, it's work to generate both electricity and heat. But the level of heat, the intensity of heat and electricity is very low, and that will limit the end use application. So to improve that, we need to increase the high thermal energy through large number of PV, photovoltaic thermal, and through which we will increase the capital investment cost. So the idea came through developing, one system. That system is capable to generate electricity, and at the same time is capable to extract heat. So it's starting with the same idea of CBV. It's going with increasing solar radiance, using imaging, non-imaging optics that will increase temperature, drop electrical efficiency. And to enhance those electrical efficiency, we add a cooling mechanism arrangement to extract and utilize thermal energy. But we need to take in consideration, if that cooling mechanism is an active cooling mechanism, then we are adding, we need to take part of the generated load within the system to operate that active mechanism. Still, CBVT, it's a solution for CBV and PVT individually, but it has its own limitation in terms of a chromatic aberration with increasing concentration ratio. Complexity of the system is very high, and illumination and temperature non-uniformity is one of the challenges, and risk of excited temperature on solar cells and subsequent optics to the primary optical system. So, to increase the concentration ratio, and to have an idea of, what's the way to increase the concentration ratio, by taking in consideration the limitation and advances, there is two common options. There is one to maximize the primary optics surface area, or by adding a secondary optics, a compact, concentrator system. So if we maximize the primary optics, then we will have those challenges through capital costs. We will minimize acceptance angle, increase tracking load. But there is a solution like adding a homogenizer to enhance the excuse me, to enhance the uniformity of irradiance, enlarge the acceptance angle. On the other hand, adding secondary optics will reduce load in the tracking system, but it has high thermal stresses and due to high temperature excitation, system tolerance and alignment, one of the challenges, and that will drop the optical efficiency. But the uniformity of irradiance is much better in comparison with primary and larger primary optics. So why ultra high concentration ratio? We are seeing in the literature that the progression of developing solar cells is very high, and we need to develop a system that is capable to tackle out this. Increasing concentration ratio will help to minimize the solar cell, and even with having high concentration ratio, and if with high concentration ratio, if we face any drop in the cell efficiency, the system will be still able to produce more power and be cost effective. It's based on Fresnel lens. Fresnel lens is an excellent for acceptance angle and optical efficiency. But we need to take in consideration that ultra high concentration ratio system is challenged by multiple optics in one system, alignment and tolerance, temperature excitation, not only on the cell but also on the subsequent optics to the solar cell. To start this project, we started with in the research methodology, we started with preliminary experimental analysis. And this aided our ultra high CBV system through defining the optical length, to design a mechanical frame to host the optics, defining the focal spot to help the selection of the solar cell size, surface area, defining the performance limits indoor for the Fresnel lens thermally and electrically, helps to design, scale up for heat sink, help the material selection. So we started, those experimentation indoor. This is the Fresnel lens, that we have selected for the design, and this is analytical studies and measurements based on the performance of the Fresnel lens, giving different scenario of losses. We also have considered, what if one of the optics is cracked, it having some micro crack in the system, will the losses will be significant to affect the performance if we integrate it within the ultra high system. And we have studied that, taken in consideration the recycling of optics, less waste to environment. Moving forward, the level of temperature, it's very high, and it's coming approach to reduce that temperature is through using a pulsed illumination cooling techniques. But we have tried to come up with a new idea, developing a system cooling arrangement based on pre-illumination cooling techniques based on a graphene. So we have developed what's called a neutral density filter fabricated utilizing graphene material to attenuate evenly the transmittance of solar radiance. So this graphene will help to drop the temperature and dissipate it horizontally and keep the cell operated. It's one of the idea that we came up as a solution. Graphene has been characterized, has been tested chemically, morphologically, optically, experimentally, and thermally, and we have seen that graphene has shown very excellent result and outcomes. and has improved the efficiency of the solar cell. We moved forward. We used that, preliminary data to feed into a simulation software, and those data helped to design for to set up the numerical tool and to understand the system thermally and optically. And we can see here, this is the Fresnel lens, and this is the focal length, focal spot in the numerical tool, and this is boundary condition geometry, and we were able to validate that we have used the experimental data to validate the model, so we can extend the model for the more complicated ultra high CBV system. Moving forward for quarter of the system, where we have the primary, the secondary, and the tertiary optic. We have done numerical, analytical, and experimental analysis for the system. We try to define the losses, the optical performance, considering different solar cell surface area. We have, used a quarter of the system to do optical and thermal analysis. We have generated the ray trajectory within the numerical tool. We have studied the irradiance distribution as well, and through which we can define the level and temperature excitation. And we have observed and defined the optical concentration ratio based on the simulation tool, and we can see here the angular focal spot image due to the secondary optical stage. After having all these data and analysis, we moved into the design. We feed in the inputs from the design, like the focal length, focal spot, and other aspects, temperature. That's helped to select material. You can see here, this is the designed system in the SolidWorks software. This is the actual built in-house solar energy lab and ESI building. We moved forward to study, aspects and mechanical components to host the system. And we have fabricated, supporting arms. This is an image for solar simulator, sun tracker for outdoor experimentation. This is counterbalance weight for moments and equilibrium of the mechanical structure. We have designed this equilibrium and arm to host both the system on the sun tracker and the counterbalance. We have done stress analysis. We have done displacement analysis. We have done windage load impact to make sure that the system is safe on the roof, and it's not affected by the windage, and it's within the specification and the limitation design of torque and so on. We can see this is the wind simulation analysis through different directions on the system. Has been simulated using SolidWorks software. We can see this is more visualization for the optics and image of the secondary optics as well. This is outdoor experimentation, and this is the setup outside on the roof of the ESI building. Different secondary optics has been used in the experimentation just to see potential and outcomes. This is the results. Finally, I'm almost finishing. This is the result. I know I'm running out of time. I have given only 15 minutes, so I'll be there. So this is, this is the results, which has been collected quarterly. So basically, we have 4 Fresnels and 1 system. So we have opened one and shaded the rest, and then we have opened 2 and shaded 2, and then we have open 3 and shaded 1, and then we have open the 4 system. So we need to see the built-in power and the power and current and voltage quarterly in the system, and we need to see the power output of every system. And this is the A is at the PNC identifying 3 type of secondary mirror types. Those figures showing optical current, correlations, efficiency, power. But most importantly here is that this system has achieved the highest effective concentration ratio for a compact design and in outdoor experimentation. We have reached the highest result by far in literature for such a design, where we have reached 1,300 sun effectively outdoor on an actual sun tracker, continuous sun tracker. And this is have seen through the literature for similar designs and compact CPV system for researcher trying to achieve higher ultra high concentration ratio. And we can see exactly that our study for has achieved the highest by far in terms of geometrical concentration ratio and in terms of effective concentration ratio for this particular design. But thank you for listening, and it is my great pleasure to be part of this. I was rushing through the slides, but I'm limited with time. If there is any particular questions, ideas, collaboration, I'm more than happy to support and to communicate. This is my email and my phone number to reach. Thank you so much. It's my great pleasure, and I'm very excited for the rest of the day. Take care all, and thank you so much. Rest well.
Thanks a lot, Musad. It was a wonderful talk that how high concentrated photovoltaics can be a supermodel for photovoltaic industry in upcoming days. I think people have a few questions for you, but that we can try to address during the panel discussion if our time allows. So don't waste more time, and as looks like we are on schedule perfectly. So let's moving on to our next guest speaker. Dr. Asma Reddy Ahmed. She is currently an assistant professor of renewable energy, the Faculty of Engineering Department, Port Said University, straight away from Egypt. So before hand over to Asma, let's have a quick introduction. So Dr. Asma Reddy Ahmed was a renewable energy PhD researcher from 2018 to 2021 at the Environment and Sustainability Institute, University of Exeter, UK. Supervised by Professor Tapas Malik. Her PhD was funded by the Newton Mosharrafa Fund, sorry if I mispronounced, a UK-Egypt partnership program for postgraduate scholarships. Her PhD focused on high concentrating photovoltaic research, and she is currently working on several projects in the area of renewable energy application for climate change mitigations. She is a part of team working on Egyptian offshore wind to produce green hydrogen to mitigate the effects of climate change. At the same time, this project is run in cooperation with Port Said University, Egypt, and University of Strathclyde, UK. It is funded by British Council, Egypt, according to climate grants in the run-up to COP27 as a part of the Climate Connection Program. Wonderful Asma's biography, and with this, I'd like to invite and welcome on board Asma. Over to you.
Thank you, Anurag. Can you see my screen?
Yes, I can see your screen and your voice is also clear, so please.
Thank you. Thank you. Hello, everyone. First of all, let me thank you all for coming here today. I am Dr. Asma Radi Ahmed from Fahd University in Egypt, and I will deliver this talk with the title of Renewable Energy Applications for Climate Change Mitigation. Let me start by saying just a few words about my own background. I'm an assistant professor in Mechanical Power Engineering Department and Fahd University, Egypt. I obtained my PhD last year under the supervision of Professor Tabas Malik in renewable energy from University of Exeter. This PhD was funded by Newton Musharrafa Fund. I will skip this slide as Dr. Anurag has introduced me, but for more information, please scan this QR code. Let me start by introducing the city where I come from. Fahd city is a coastal city where it is located in the northeastern of Egypt, where it is surrounded by the Mediterranean Sea and Suez Canal. The main campus of Fahd University is located in Fahd suburb, the Asian side of the Suez Canal. Fahd University was established in 2010. However, there are some faculties that are older than this, like the Faculty of Engineering. One of the important groups in the University of Fahd is the Renewable Energy Group, which deals with important issues in the area of renewable energy resources and their applications. The group deals with several kinds of renewable energy resources, such as solar energy, wind energy, and geothermal energy, and their applications like seawater desalination, heating, ventilation, and air conditioning, HVAC systems, and recently green hydrogen production. The second important thing I would like to talk about today is the global energy situation. According to the Energy Information Administration report in 2019, there was an increase in the use of renewable energy resources, which represented about 13% of the world energy consumption was by using renewable energy resource. Wind and solar resources represent about 1%. According to the Egyptian New and Renewable Energy Authority report, about 20% of the produced electrical power was by using renewable energy resources this year. And photovoltaics represents about 2% of the electricity production, while wind and hydro reaches 12% and 6% respectively. These figures are expected to increase in Egypt in 2035. Egypt expects to depend more on renewable energy, as it will represent 42% of the total electricity production by 2035, and it will increase also to 61% by 2040. Okay. Egypt's solar atlas states that Egypt is considered a sun-belt country with 2,000 to 3,000 kilowatt per meter square per year of direct solar radiation. About 9 to 11 hours of solar sunshine every day from north to south. Therefore, Egypt has an excellent location with estimated annual of 2,400 hours of solar operation compared to maximum European figures like in Greece or Spain, which is only about 1,900 hours in 1 year. There is, if we talk about the current solar energy projects in Egypt, there is a total of 32 solar power plants strategically distributed across Egyptian lands. The first solar thermal power plant was built in 2011 in Krimet. This plant is based on parabolic trough technology. And also there is a 37 square kilometer Benban PV solar park in the western desert of Egypt, which composed of 32 individual plants each producing 20 to 50 megawatt. Also, there is a Kumombo PV plant. Sorry. Regarding current wind energy projects in Egypt in terms of the wind energy, as you see here from the wind resource map of Egypt, there is high wind velocities are achieved in most areas of Egypt, which gives it another advantage for onshore and offshore wind projects. The average speed in the Gulf of Suez is almost about 10 to 10.5 meter per second at a height of 50 meters. And the average speed in the eastern and western parts of the Nile is about 7.5 meter per second at a height of 80 meters. Regarding the current wind energy projects in Egypt, there are several active wind projects, but unfortunately, all of them are onshore wind projects, like Al Za'farana, Gulf of Zayt, Ras Gharib, and West Bakr. The highest installed capacity is about 545 megawatt is being produced from Al Za'farana, according to the Egyptian New and Renewable Energy Authority. So what about offshore wind energy potential in Egypt? As I said, due to the geographical location of Egypt, it has the largest offshore and wind potential in the world, as the Red Sea region has the best wind resource with mean power density at 50 meter height in the range of 300 to 800 watt per meter square at mean wind speed from 6 to 10 meter per second, which is a very high wind velocity. Egypt's offshore wind potential in the Mediterranean Sea is estimated to be around 13 gigawatt, which is excellent for offshore projects. So let's talk about solar energy research that I did through my PhD. I focused my research on high concentration photovoltaics. Solar photovoltaics is one of the most rapidly growing renewable energy resources. The power generated using solar photovoltaics technology increasing by 600,000 megawatt from 2010 to 2020. Up to now, common photovoltaic panels available in the market convert only between 23 to 27% of the incident energy into electricity. Concentrating solar photovoltaics suffers from several obstacles, such as increasing the temperature due to the increase in the solar concentration. This can cause some hotspots or cracks on the solar cell. Therefore, in that research, I focused on studying several innovative solutions to manage their temperatures. One of the studied topics was by using IR filter on the silicon solar cell. Characterization of the filter and the solar cell were conducted, as you see here. Also, the main aim was to protect the solar cell from cracking, which appeared at the beginning of the experiment due to its fragility. When it was tested at solar intensity of 1000 watt per meter square. Successfully, at the end of the experiment, the IR filter protected the solar cell from cracking, which reduced its temperature to 50 degrees Celsius. Although the optical efficiency of the system dropped as expected by using the IR filter, the solar cell efficiency was enhanced by 183%. Also, 3D simulations of different heatsink configurations were studied, such as the finned mini-channel heatsink, straight serpentine center inlet serpentine, and side inlet serpentine, besides the use of different cooling media, including nanofluid. From the study, the heat transfer, we found that the heat transfer effectiveness of the nanofluids reached 1.15 in the case of aluminum aluminum oxide with water at 5% concentration. And also maximum solar cell temperature decreased significantly by using a nanofluid at concentration ratio as the concentration of 2000 sun. In terms of heat sink design, straight channel was not recommended for concentration ratio higher than 10,000, 1,000 suns, as the temperature exceeded the temperature limit by the manufacturer, specified by the manufacturer. As the center inlet serpentine showed the best performance until the concentration ratio of 2000 sun. The work also involved several experimental methods, such as analysis of the analysis of the focal spot area for different working scenarios. Also, the thermal characterization of the nanofluids used in the experimental investigations, and in addition to building 3D simulations, TFD models for studied heat sink test sections. This is for a verification of the results. Good agreement was achieved between the experimental and simulation results. In terms of the running or current research projects at Bursaid University, I'm a member in Climate Connection Project, which is funded by the British Council in cooperation with Bursaid University and the University of Strathclyde in the UK. The project investigates the potential of the Egyptian offshore wind for the production of green hydrogen. Worth it to mention that the renewable energy group next step is to generate hydrogen from solar PV technology. So let's talk about hydrogen. Hydrogen is the most abundant chemical substance in the universe, represent about 74%, and it is the first element of the periodic table. Comparing similar volumes of hydrogen, hydrogen contains approximately 3 times more energy than oil or natural gas. This enables hydrogen fuel cells to be 2 to 3 times more efficient than internal combustion engines. Regarding its applications, there are several applications for hydrogen, like hydrogen can be used for chemical production. Majority of hydrogen is used in industry to produce ammonia, about 55%, and methanol, about 10%. Most of ammonia produced is going to fertilizing, which sustain food for production for billions of people. The second application is electricity production using fuel cells. Electricity is produced using hydrogen fuel cells by combining hydrogen atoms and oxygen atoms. Large fuel cells can be power supply electricity to buildings, but small fuel cells can be power maybe laptops or cell phones. Hydrogen can be used also to power engines. Using hydrogen and oxygen creates electrical charge, allowing a vehicle or an engine to be powered. It is a zero emission technology, but it has some challenges, like containing the hydrogen at high pressure, maybe reach to 350 to 700 bar, which is very high pressure. Another application is storing the renewable energy, energy from renewable energy renewable resources is stored by electrolyzing the excess energy produced during low energy demand periods. In this process, hydrogen is separated from chemical solution by passing an electric current through it. As you see here in the next picture, hydrogen can be used once it has been created using electrolysis of for chemical industry, energy storage, mobility, etc. How hydrogen can be produced? Firstly, we need a primary energy, which can be a renewable energy resource like solar or wind, or conventional power, conventional energy resource like natural gas, coal, and so on. These primary energy forms will be converted into hydrogen using different conversion processes to produce hydrogen. like direct water splitting, electrolysis, biological conversion, or thermochemical conversion. Regarding direct solar water splitting process, this process uses a light energy to split water into hydrogen and oxygen. These processes are currently in various early stages of research, but offer long-term potential for sustainable hydrogen production. Electrolytic process use electrolyzers to generate electricity to split water into hydrogen and oxygen. This technology is well developed and available commercially. Also, the systems these systems can efficiently use intermittent renewable power to produce hydrogen. Biological process use microorganisms such as bacteria and algae, which to produce hydrogen through biological processes. Thermochemical processes use heat and chemical reactions to release hydrogen from organic materials such as fossil fuels and biomass. So what are the types of hydrogen? Actually, there are three main types. First, black or gray hydrogen is produced from coal, natural gas, or lignite. There is CO2 emissions from this one. Blue hydrogen is produced from fossil fuels with reduced CO2 emissions. The CO2 here is stored and or used. But green hydrogen, the hydrogen here is produced from renewable energy resources. This type offers several advantages, like new use of fossil fuels, no emissions of CO2, and high purity of hydrogen, and a valuable byproduct of oxygen. Electrolysis is a leading hydrogen production pathway to produce hydrogen. To reduce the clean hydrogen cost, about $1. It is expected to be reduced to $1 per kilogram by 2030, but now it is still expensive. Hydrogen produced via electrolysis can result in zero greenhouse gas emissions, depending on the resource. The electrolysis here, maybe the efficiency can reach from 60 to 80%. The important question now is, how can we produce the green hydrogen? This is a schematic diagram to describe the production process, which starts by the existence of renewable energy resources such as solar or wind, for example. Some of the produced electricity is used to power the electrolyzer, which I will be talking in the next slide. After that, after the hydrogen is produced, can be used in maybe mobility or chemical production or any other usage. In order to produce green hydrogen, we need to know about the water electrolysis. It is a process that uses electricity to split water into hydrogen and oxygen. Let me here talk about the two available commercial types, alkaline water electrolyzer and polymer electrolyte membrane electrolyzer. Both of them are commercial. Alkaline water electrolyzer uses electrolyte solutions such as sodium hydroxide or potassium hydroxide. It can work with temperature and pressure of 120 degrees Celsius and the pressure up to 200 bar. Regarding the polymer electrolyte membrane, the operating temperature can reach to 80 degrees Celsius, while the pressure varies from 1 to 350 bar. This is a video that is created by Siemens Energy in order to show the impact of hydrogen production on power demand. So let's watch it. I think I'm running of time. Sorry for that. So I had to finish. This is only the last point I would like to share with you. Green hydrogen projects in Egypt. On 29 of August this year, Saudi Arabian company Al Fanar is said to it has signed a memorandum of understanding to build $3.5 billion of green hydrogen production in project in Egypt. Also, there is cooperation between India and Egypt. India and Egypt have signed a memorandum of understanding for a project of $8 billion to produce green hydrogen in the Suez Canal Economic Zone. Several also projects have been planned now in Egypt after the COP27 in the Suez Canal Economic Zone. The electrolyzers. Egypt will host 3.6 gigawatt of electrolyzers in the Suez Canal and to produce green hydrogen and will be exported to several countries. Thank you, and I'm sorry because I think I took a lot of time. Thank you, Anurag. And for more information, you can maybe send me an email. This is my email, or scan this QR code. Thank you so much.
Thank you so much, Asma, for your talk. It is wonderful, plenty of information, and especially I like the last slides where you have informed the speakers, the audiences about that, how we can collaborate. There is a plenty of opportunity of hydrogen. Fuel production, I think. Thank you so much for your time. We don't have any questions for you particularly, but I am interested to know about that, how the current government, Egypt research field is actually looking for the hydrogen, particularly when this renewable sector, how the renewable sector and hydrogen research is important currently in Egypt, because I'm sure after this conference, many people will be interested to collaborate with you. So any message for them that how you can connect?
Yeah, we are open and we are happy to collaborate with international universities, maybe University of Exeter or any other universities in Arabian or in the UK, all over the world. We are now working on renewable energy resources, as I said. As I said, on maybe solar energy or wind energy projects to maybe produce water from desalination or green hydrogen productions. So feel free to contact me using my email. Thank you.
That's great. Thank you so much, Asma, for your time and wonderful talk. I hope if anyone has a question, feel free to contact with Asma directly. Thank you. Thank you so much. We will pause here for our lunch break, and we will resume after 45 minutes. So there is a 45 minutes lunch break from now, and we will continue the conference in the second half after the lunch. And we have solar coaster ride after this, so please stay tuned with us, and we have a 45 minutes lunch break now. See you soon. Thank you. Welcome back, everyone. We have just finished our lunch break, and let's jump on our next program. So let's move on our next session, where we have a fantastic speaker from one of the emerging solar industry in the UK, Gabriel on Rost. If I mispronounce Gabriel, please excuse me. Who is the director and founder of SunGift Solar UK, based in Exeter. And before jump to Gabriel's talk, let's have a quick introduction. So Gabriel has worked in renewable energy since long before it was mainstream. Hence, he is an established figure within the industry. He initially qualified as a renewable installer, but quickly felt that there was a gap in the market for a better quality offering. Gabriel realized the industry needed a pioneer to provide top quality energy installations that were suited to customers' needs. So in 2005, he founded SunGift Solar. So SunGift installed solar PV, EV chargers, and solar storage for homes and businesses, as well as maintaining existing systems. Within the last 4 years, SunGift Solar won their first award and have won so many more since. Gabriel's professional and personal achievements have also been recognized, including when he was named Environmental Entrepreneur of the Year at 2013 by Devon Environmental and Business Initiative Awards. As an industry pioneer and leader, Gabriel has an in-depth knowledge and understanding of both commercial solar PV and the wider renewable energy sector. So with this, let's ride the solar coaster. Interestingly, solar coaster for 17 years. That's ups and downs of the solar industry. And yes, that's the title of Gabriel's today's talk. So with this, I would like to invite Gabriel, over to you.
Good afternoon, and thank you very much for inviting me to talk this afternoon. First of all, I'd like to apologize. I very much love this industry, but giving presentations isn't always my strong point. I've got a little bit of an echo. Can everyone else hear me okay?
Yes, you are perfectly audible and your screen is also visible. If you don't mind to go for the slide share. Or if you're happy to present like this way, that's fine, no problem.
There you go.
Yes, it's coming. Yeah, it's
Okay.
there. Yeah, thank you. Thank you.
That's good. So yeah, apologies. I can hear my own voice back at me, which is really quite frustrating. So apologies if that puts me off a little bit. I might just ask one of my colleagues to see if he can come and sort that out for me, because that's going to be a bit frustrating. So sorry, give me 2 seconds. It was working fine a minute ago. But I will get started whilst he's coming down. So who are we? What do we do? We, SunGift Solar, we design and install renewable energy systems. We're based just in Exeter, in the southwest of the UK. Sorry, give me 2 seconds. Owen, could you possibly pop down and put a problem with my sound? Cheers. Right, sorry. So been going since 2005. So back in 2005, the industry was an incredibly different place than it is today. So when I started, I think there was roughly about 30 different companies in the UK, whereas now, you know, there's thousands. So it was a really very different place. It was very interesting, very exciting. It was definitely alternative technology back then. But yeah, things have moved on. If you just give me 2 seconds, I'm going to see if my colleague Owen might be able to sort out my sound for me.
Yes, please, no problem. Yeah.
Okay. Hello. No, sorry, we're still having problems with the sound.
Gabriel, are you completely fine with your voice?
Okay. It's annoying. The problem is I've got my voice coming back at me. So
Okay.
that's putting
Yeah,
me off.
but we can hear you clearly.
Okay, fine. I will carry on.
Oh.
Hello, good afternoon. Can you?
Yes, Gabriel, we can hear you.
Right, okay. I'm really sorry about that. That
No
is now
problem.
sorted. That was, yeah, it was difficult to do it whilst talking to myself. We've now sorted it out. So apologies, back on track. Okay, so yeah, so basically I was just saying a little bit about SunGift, who we are and the journey that we've been on so far. There's obviously been some very, very interesting presentations so far regarding the technology that we work with. So what I'm trying to do is just give you a bit of a insight into what happens at the sharp end, as it were. We take these technologies and we put them into the places where they're going to be and generating clean energy for years to come. So really, what I started the company with the basis of trying to deliver systems that are going to produce the best amounts of energy over the longest period of time. So that's always been our sort of key focus, is longevity and sustainability. So luckily that approach has enabled us to, we've been recognized over the years a few times with winning some awards and some national awards as well with some of the projects that we've won. And the technologies that we work with has changed over the years. So the first technology is one that's not actually that deployable in the UK at the moment. Solar thermal was the first technology that we have first ever installed. And we used to do quite a lot of different heating technologies. We don't do any of those anymore. So we focus just purely on the electrical side. So it's solar photovoltaic for generating electricity, energy storage for storing that energy and lots of other different uses for energy storage, and electric vehicle charging infrastructure. And so what we do as a company is we work with clients from the very beginning of projects. So we initial consultations to find out what it is that they're trying to achieve, look at the characteristics of their site, of their energy consumption, and then we basically carry out a full design of the different systems that may be suitable for them. And we have then our own installation teams that carry out the installation work. And then we have a after sales department that then makes sure that those systems are working as they're supposed to be for the long term. And as I said, our focus has always been very much on the quality, high quality, to ensure that these systems last, because I feel we're not making any progress if systems don't deliver that they're supposed to. We have to have, be in a positive position in regards to, sort of carbon, if nothing else, with the work that we're doing. As I said, we're based in Exeter, just outside Exeter in the UK, but we cover the whole of the UK. So just an example, a couple of projects we've worked on, it's called the LEM, the Local Energy Marketplace project down in Cornwall, where this was a combination of over 100 individual installations of solar energy and battery storage, which is working in combination with as a microgrid to actually alleviate issues on grid infrastructure in the local area. So that was a project that was run by Centrica, one of the sort of big energy suppliers in the UK, and we essentially carried out all the installation work there. And then at the other end of the scale, or the end of the UK, we recently did a project for Edinburgh Royal Observatory, as you can see on the right of the screen there. So again, the whole sort of breadth of the UK and some very interesting projects, which, we'll have a look at a few more slightly later as well, but based in Exeter, but cover the whole of the UK. So just give you a kind of rough idea of what we've been up to over the years. As they all started in 2005. I previously actually worked for another company very briefly. I got into the industry. I didn't have any relevant experience, and I actually sort of picked up the yellow pages, the telephone directory, and phoned all the companies that were in there, which there was 4 at the time in the local area, and asked them all for a job, and they all said no, apart from one company gave me a go. I started out sort of installation work with them. I kind of learned mostly how not to do things. It was an interesting experience, but they weren't a brilliant company. So that really, sort of spurred me on to show that, better could be done. So I set up the company Sungift Solar and working initially from the house, spare room in the house. We sort of soon went on and sort of grew the company. We got our first accreditation. We actually got our first Clear Skies accreditation, I think in 2007, and then that changed to MCS, which is still the current sort of certification body in the UK, in 2008. And we're also very lucky to pick up our first award of Installer of the Year in 2007. In 2009, a feed-in tariff scheme was introduced in the UK, and this paid people to generate energy, and that had a huge impact on the deployment. And again, I'll show you some graphs shortly of why we call it the solar coaster. So there was rapid growth, especially in 2010 and 11. And it's a very interesting time, difficult but interesting time. We also had a distribution business, so we attended a few exhibitions, and really key, we introduced quite a few new technologies to the UK, as the UK was an emerging market for solar technology. It was a very good opportunity for us to look at what technologies were available around the world and bring them to the UK, ones that we thought would be beneficial. And we still work with a lot of those companies that we first introduced into the UK market. We moved on from 2012 onwards. We started getting involved in commercial projects. There was very little commercial solar deployed up until then. And I'll talk about it in a bit more detail in a minute, but one of the ones that we won was for the Met Office, which was a very nice installation because it was a large installation and we were up against lots of quite serious competition. So for essentially a small company in the Southwest to win that versus some of the other sort of national big energy companies was very interesting. And 2018 onwards, we carried on growing despite some very interesting times with a global pandemic. Solar energy is continued to prove very attractive for many reasons. So we've, even during those difficult times, we've managed to continue to grow the company, and we're working a lot more with local authorities and stuff as well. So big sort of rollouts of multi-properties or multiple commercial scale projects. And the number of installations that we're carrying out is increased massively. The kilowatts that we're deploying on a daily basis, is increasing massively. We've been getting a few bits of recognition in sort of some local papers and stuff, and national papers, which I always think is really important for the industry as a whole, is providing that positive story to allow other people to get familiarized with renewable energy. So it's an easier journey, an easier sort of step in for anyone to get involved, whether it's to join the industry as an installer or to purchase the equipment to make the change to clean energy themselves. So I mentioned that we call it the solar coaster. So these are graphs showing the deployment on residential solar and commercial rooftop solar over the last 12 years. So if you can see the massive differences, if you can imagine from a company's point of view, when we are, we're employing people, we are trying to deliver a stable work essentially for all our staff and pay all the bills. You can see it can be incredibly difficult when the market changes so dramatically, sort of from year to year and from quarter to quarter. And previously, up until 2019, That was all very much driven, from up till 2016, that was very much driven by the feed-in tariff. And these were the government interventions that essentially paid people to install and generate clean energy. The idea with any sort of subsidy scheme like that is generally to stimulate a market and then remove the subsidies slowly to allow the market to carry on. Unfortunately, our government did not get it very well at all. That they introduced the scheme and it was basically far too generous, and then they removed it in a very ad hoc way, which caused huge damage and basically the collapse of the industry. We were very lucky to survive. Most of our competitors and the vast majority of solar installers in the UK went out of business in sort of 2016. But then you can obviously see on the slides towards the right hand side, 2022, 21, 22 have seen incredible deployment. We've deployed more in the first few weeks of 2022, than we did in the whole of 2018. So demand has gone, absolutely through the roof, and I've never known anything like it. And for quite a lot of this year, we've actually had to close our phone lines because the demand is just so high. We're not able to keep up with it. There's just not enough of us available to answer the phone calls, to design the systems and to deploy them. So it's really gone stepped up. Again, this just sort of shows you the three different areas. The commercial rooftop is starting to come alive. The yellow bars, the residential has always been quite a strong market in the UK, but the commercial rooftop is very underutilized in the UK compared to how long the market's been valid. But that's really making a change now. We're deploying more on the rooftop market than we ever have done before, and we're pretty much booked up for the next 12 months. All the installs we're going to be doing over the next 12 months are pretty much already signed up and just waiting to be finalised. You can see the ground mount, and when we talk about ground mount, we're generally talking about standalone. So all the projects that we do at SunGift are connected to where there's an energy demand. So we do ground mount projects, but they are generally directly connected to a high intensity energy user. So we don't do systems which are generally just fed directly back into the grid. That's a different marketplace. And again, you can see the huge different levels of deployment, essentially on a month by month basis. But it's all moving in the right direction. Still, the UK's target for solar is still pretty low. It's not the most ambitious at all. Our current government, unfortunately, are not. Whenever they do their energy strategies, solar seems to get completely ignored. We still, if anything, at the moment, they're making it harder to deploy solar. It's a bit of an uphill battle. We're hoping that any change in the next general election might make things a little bit easier for the industry as a whole. But you can see the UK sort of the deployment per capita population, we are right down at the very bottom of ambition, which is a bit sad because the UK could do an awful lot better, but hopefully that will change over the next coming years. So what I really want to do is just talk to you a bit more about some of our projects, how we take projects from conception to build and tell you a little bit more about them. So I've just picked a couple of sort of local ones. So this is Exeter Science Park, just on the outskirts of Exeter. There's some new build projects. So we have over 80 kilowatts of solar PV. They also have 9 Tesla Powerwalls, which are energy storage, battery storage devices, lithium ion energy storage. So that gives them 120 kilowatt hours, just over 120 kilowatt hours of energy storage capacity. And they also, on this particular project, have 20 electric vehicle chargers. And so that for us is a really nice combination of 3 technologies that work seamlessly together. So being able to deploy these on a new build project where everything is designed right from the beginning of the project, with the solar and the batteries and the EV charging being part of the project from the start. It's fantastic. I mentioned the Met Office earlier. So at the time, this is one of the biggest installations in the UK and certainly in the Southwest. It was a competitive tender where we read the tender documentation, and we actually went back with quite a few revisions. We thought we could actually improve on what they were asking, and I think that's what put us in a position to win it. We were up against lots of big multinational sort of energy companies, and we won it because of our kind of technical response. The roof that the solar panels are deployed on is where their supercomputers are housed. There is 3 supercomputers under that roof, and the peak output of the PV panels is enough to power just one of those 3 supercomputers. So a very energy intensive business, but yeah, great one for us to work on. One of the things I love about this industry is repeat business. So we tend to, a lot of people, once they have their first taste of renewable energy, they tend to come back for more. So this is Pneumatic, who actually make the Henry vacuum cleaners. We've now done 3 projects for them of varying sizes over 8 years, and just started deploying electric vehicle charging as well. And then one just up the road from some of you, I don't know where we were based, but this is Exeter University up in the Sportsfield car park. So this is a 400 kilowatt solar carport project that we worked on a couple of years ago. There's also electric vehicle charging there. We didn't actually do the electric vehicle charging, but that's a project that some of you might get to see at some point. We've done 3 different projects for Exeter University, so we've got it on the sports hall and one of the other buildings as well somewhere. So this is a project that is in motion at the moment. So what you can see being lifted up there by the crane is a Tesla Megapack, which is the name for their large energy storage device. This is a 595 kilowatt, 1.6 megawatt hour battery system. What's really unique about this project is it is supplying energy to a new build housing development. So the whole housing development gets its energy from essentially what's called an ESCO, an energy supply company, and that energy supply company is using solar and a battery to be able to supply energy to the new build housing development in the most cost-effective and low carbon way. So it's a really interesting and unique way of using a battery in a new build project from concept. And this is the sort of thing that we would expect to see happening more and more. And then this is what it looks like on the inside. So we've got the panels on the roof. This is the electrical setup. So these are 4 separate 100 kilowatt inverters on a 400 kilowatt peak system. So you can see the inverters there, and then below them is all the DC isolation protection, and then the AC isolators below. This is a project that is just being completed, which very difficult grid connection issues associated with it, but it's we're very proud of the workmanship of our guys who carry out the work. And this is a lovely Danny. This is one of our apprentices who's currently in the 2nd year of his training, and this is the first job that he's been able to lead, with supervisor working with him on a daily basis. But this is his handiwork after sort of in his 2nd year. So again, as you can see, very kind of proud of the aesthetics of how the installation looks. Neatness and quality go hand in hand. And so just onto a couple of guys who sort of work in the office. So Farouk, who was the one who introduced me to this conference, so we can thank Farouk for you having to listen to me. So he's one of our design engineers. He's been with us a little under a year. So he's actually comes from, did his training with the University of Exeter. He's just completed his and got a distinction, I understand. So he works office-based, carrying out CAD designs, electrical schematics, and system designs, which is a very integral part of what we do. And Argel has recently joined us, Portuguese, and he is in the commercial design department. Again, electrical engineering background, and I'll show you a few examples of the work that these guys are doing. So this is just a typical project, just some of the stages it goes through. Client comes to us, we look at what the building is suitable, what the characteristics of the building allow us to do from a deployment point of view. We do 3D modeling, we do a layout of the solar panels. We look at the different inverter and string configurations to basically make sure that the system is going to produce the best with any sort of shading elements or anything that may have an impact on the output. I understand I'm getting close to the end of my time. Do you want me to hurry up, or should I carry on?
No problem. You have 10 more minutes.
I have 10 more minutes. Okay, sorry. I thought I was at half an hour.
Up to you.
I'll keep going. Brilliant. Yeah. So these are the different sort of levels of a project goes through before we can actually start building it. So we then go to the sort of CAD drawing layout. So this allows us to ensure the system is going to fit when the guys are actually being sent to site, do the installations, making sure that all the components are able to fit in and are being installed in the right locations. And this is basically the job packs that go out with every installation. So incredibly important design work to ensure that the systems are put in correctly. And Argel, again, he does a similar job, slightly different. And there's just a few bits of work that are live at the moment. So top left is a new solar carport that we're working on with Plymouth Marine Labs. That's just going through planning at the moment. Exciting project. And on the right is Charlie Bigham's, which is a very interesting building, a really challenging building for us to work on due to the size and shape of it and the access restrictions. So you can see that there's quite a lot of sort of detailed design work that goes into sort of every stage of projects. So the thing that's really kind of interesting and kind of exciting at the moment is things are moving on at quite a pace, and that is the more deployment of renewable energy, the more challenges we have with connecting that to the grid. So solar has a habit of all the solar panels in an area, they all generate the energy at the same time. And that causes quite a lot of issues to the national grid, the electricity grid, because it was not designed to have essentially reverse power fed back into the grid. So every time we design and install a system, we have to do applications with the grid, and the complexity that we are facing with some of those grid applications is getting harder and harder. So we're having to deploy different design methods and different technologies to essentially allow us to comply with those grid connections, as the grid is essentially getting overwhelmed with the amount of renewable energy that's being connected to it. And that's also, we are also combining multiple technologies, and it's getting incredibly and ever more complex of how those different technologies are integrating together, and essentially ensuring that we're getting a sort of smooth flow of energy and combination of those technologies working together is essentially getting more and more complicated. So the real challenge we have is recruiting the right people and keeping the level of technical ability where it needs to be to ensure that these projects sort of go smoothly. And that's been a challenge, for our whole history. We very rarely are able to recruit people with previous experience, just because there isn't that many people with experience of renewable energy in the UK. So we have a constant training program going, and it's just very difficult recruiting, training, and scaling at the same time. We're now up over 50 people work for the company full time, and then we have some contractors who work with us as well. So we've grown quite a lot over the years, and keeping that level of technical ability is really key. But we're really excited about the reasons why the industry is growing and the possibilities going forward. So we obviously get to speak to lots of clients who are making these decisions. And I personally am in this industry mainly for sustainability reasons. I have 2 young children. I'm very concerned about what's happening to the planet, and I want to do everything possible to reduce any impacts of climate change. That's been quite a hard sell over the years. Most of our clients are generally more financially driven. But I'm very pleased to say that actually now a lot of decisions and a lot of money is being spent also for sustainability reasons. And there's a lot of people with zero carbon goals, which are very, very hard to meet, and generally can be very expensive to meet as well. But they are putting their money where their mouth is, and they are deploying projects to make that happen. But also, there's, as I said, the financial returns have increased massively. So obviously the rising cost of energy has basically reduced the payback time on solar systems and battery systems massively. So we're in a position now where we've seen payback times on some commercial projects go from 5 to 6 years down to 1 to 2 years in some cases. So these are some very, very large energy bills that are and capital projects which are now making really good financial sense. And on the other side, the cost of energy is now a severe threat to lots of businesses, so they generally potentially have to do something to ensure that they're viable going forward. What really excites me is the technology, as the conference has been showing so far, is the improvements in technology and advancements in the longevity and efficiency of solar panels and battery technology. Basically enables us who essentially are designing and installing the technology to do more in more difficult locations. So the more efficient solar panels get, the more we can deploy per square meter, the lower cost they get, the more attractive they are to clients, and the more improvements in battery technology. Essentially, it just unlocks projects that maybe weren't viable a few years ago. So it's a really exciting industry to work in because of the constant improvements in technology. And then just finally, it's the rollout of electric vehicles. If you can imagine all the money that was being spent on petrol and diesel essentially is being spent on electricity, and if you can generate that energy locally, essentially just that alone opens up a huge market for solar energy on its own. So when all this is happening at the same time, there is an awful lot of activity in the sector, and we are expecting to be busy for a good amount of time into the future. So we're all very excited. So I will wrap up there. Thank you for watching. I hope it's been of interest, and I'm happy to answer any questions.
Thanks a lot, Gabriel. It's a wonderful talk, and I hope the listeners are, benefits whatever the technology, what you have described, and you have installed many things in Exeter, across the Exeter. It looks nice. I think we have a couple of questions for you, but can we discuss during the panel discussions if you are on board? Yes, thank you so much. Thanks for joining us. We can, from Exeter now, we can go to directly Edinburgh, Scotland. So we have our next speaker, Dr. Senthilarasu Sundaram, who is an associate professor, School of Computing, Engineering and Built Environment, Edinburgh, Napier University, Scotland, UK. So before hand over to Dr. Senthilarasu, let's have a quick introduction of him. So before joining Edinburgh, Napier University, Dr. Sundaram was a senior lecturer at the University of Exeter, UK. Prior to this, he worked as a postdoctoral research associate at Loughborough University and followed by Heriot-Watt University. He is currently working on sustainable energy technologies to create environmentally sustainable materials for energy generation, storage, building integrated application, thermal storage, water remediation, and low carbon heating applications. He is involved in various EPSRC, EU, and innovative UK funded projects. Dr. Sundaram has published articles in over 150 journals. At the same time, he is also associated with many editorial contributions to the including Nature publication scientific reports. With this, he is going to talk about the energy. Are we in the right track? Really? Let's listen from Senthilarasu Sundaram directly. Over to you.
Thank you, Anurag. Thanks for the kind introduction, but I'm struggling to open because the Zoom is not allowing me to open the PPT.
Okay, we'll check this. Stay with us.
Yeah, so
He's co-host.
PowerPoint, it says unknown actually.
Your screen share button is green, right?
Yes, share button is green, green actually, but the portion of the screen, I'll try. It is asking me to add. Okay, anyway, so can I send it to you then?
Yeah, no problem. Yeah.
I'll just give me a moment. I'll forward. Is that to your email or what?
Yeah, you can send me anywhere. Yeah.
I'm sorry, actually. So sorry for this one. I didn't expect this actually. No, we can't share. Okay, so give me a moment. I'll just go and.
Yes, no problem. Take your time and apologies to all the attendees for this technical reason. Yeah, it happens. Don't worry.
Just give me a moment. I'll leave and then join again. Yeah.
Okay, no problem.
Sorry.
I apologize to all the attendees here. We have some technical problem sharing a screen by Dr. Senthilarasu Sundaram, who is our next speaker. So very sorry about this. This is a technical problem, so we can't do anything at this moment. So please bear with us and stay with us. Thank you. Okay, Gabriel, are you there? So whether Senthil is sharing his screen and his presentation, we can go for a quick question with you if you're on board.
Yeah, sure, no problem at all.
Yeah, thank you so much. First of all, thanks for accepting our request. I know how busy you are, and SunGift Solar. And that's a gift for us even. Thanks a lot. I'm just wondering that what's the current scenario of climate energy, climate emergency in terms of your solar industry? How pressurized now solar industry, to address the climate emergency or net zero carbon emission?
Yeah, so I mean, it's how pressurized is the whole industry. I mean, I've been a member of a few different organizations, such as the CBI, the Confederation of Business. And when the first zero carbon sort of goals started being announced by government and then separate organizations, good to 2-3 years ago, when they sort of started coming out with actual dates, I have been feeding back to them to say that the industry is nowhere near able to cope with those sorts of deployment. It's just that the gulf is huge between what you're trying to achieve and what the industry is capable of deploying. Unfortunately, what happened sort of many years ago is when the feed-in tariffs and stuff were first announced, a lot of training academies and colleges and Exeter University were one of the first to come with a specific renewable energy degree. And so we started training and recruiting, and the industry was growing. But when they started removing all the subsidies, pretty much all those training courses stopped. So Exeter University very luckily carried on with their renewable energy degree, and I think we've probably worked with 7 or 8 different graduates now who have been through that program. But all the colleges, all the practical skills that were teaching the people to actually deploy these technologies disappeared. So there is still a massive gulf in the ability to deploy these technologies with the requirements to meet these climate targets. As I kind of alluded to earlier, we actually just had to turn off our phone lines because we just physically, couldn't cope with the amount of inquiries that we were getting. Our biggest barrier to growth, the reason we can't do what we want to do, is still essentially engineers out in the field. Essentially roofers and electricians are our #1 barrier to growth. So pretty much our whole marketing department, that's all they do is recruitment at the moment. They are trying to help us find colleagues to help us deliver and train new people. So in short answer to your question, we are under a lot of pressure as an industry, and it will take an awful lot to be able to deploy what's required. And the thing is, this is I'm talking from a kind of UK perspective. This is happening globally at the same time. So there's demand on supply chains throughout the whole industry, and globally as well.
That's fantastic. Really, we are also struggling, and we also appreciate that if the universities are come across with different renewable courses, that also nowadays is really needed. Especially, we have our renewable energy masters and bachelor courses here are available, but I find except UK or a few industries are given that particular designated renewable energy degree. So that's a very good point, that we need more practitioners, more stream students for industries. Those as you mentioned, that it can be a probable solution to for future this climate energy purposes. Anyway, thank you so much, Gabriel. Maybe if time allows, I will catch up with a few more questions, but let's focus on our next speaker. I think he is ready. And yes, Dr. Senthil, are you there? I think he's can't able to share his screen. Can someone please take care? Is he a co-host? I can see he's still not the co-host.
I can't see him in my list of participants. One moment, please.
He's there.
Yeah. I'm sorry. I'm doing it now. I think that the same. It says same kind of asking you.
If you don't mind, you can email me your presentation.
No, it's a big file. That's why. More than 100 MB. Now I got it.
No problem. Yeah, it is coming. It is coming. Yeah. Oh, cool. Yeah, we can see some hearts. Good. Okay, please go ahead.
Yeah. Thank you. Thank you very much, Anurag. I'm very sorry for this technical trouble. I have to switch 2-3 computers in between actually, so to find out how to share the slides in Zoom. Yeah, thank you very much, Anurag, and the ESI team, Solar team, for inviting me to give a talk in their conference actually. So, so a couple of months ago, I was part of that team as well actually. So you might be heard from few of the speakers telling our names actually here and there. So I'm still, in my heart, I'm part of that team anyway. So what I wanted to talk to you today are give you a bit of light on different aspects of the energy. So previously, from yesterday and then today, lots of talks on the technology advancements and other stuff. And then the last one from Gabriel. So he gave a very, very good kind of an outlook about the, the how energy can be used and then why he is in this business. And then what is very important to him, whether it is a climate change or the, the money, something like that. And then the obvious side for Gabriel is go with the, listening to his heart actually. Okay, so that in that aspect, I'm going to give you a little bit of a background about the what is the energy scenario at the moment, and then is that right one? Are we in the right track for the future generation? Something like that. Okay, so we can start with this figure. Picture what you are seeing here actually. So you have a car, but it's not driven by the petrol; it is driven by the heart actually. Okay, so that's the situation we are heading towards. So most of the time actually, so it's not in the negative sense I'm telling, but mostly so you are you have to find a fast power from somewhere, not from the petrol and diesel and something like that actually. So the climate emergency, so we all know, and then we are experiencing it. I have seen a documentary a few days ago. There is a country in the Pacific Ocean. So they are the first nation or the first country to disappear from our actually. So maybe in a couple of decades from now onwards actually. So using our energy is very important in terms of the climate emergency as well actually. So most of our energy at the moment, what we are generating, we are using 30% or more than 30% in the built environment, especially for the heating and cooling as well as for the lighting arrangements. And then the 20% we are using in the transport. So if you take the building and then our transportation take almost like a 50% of the energy generated in the world. The other 50% comes from all type of industries, starting from food industry, textile industry, and then car industry. You put any industry there actually, so that will take the 50% of our energy consumption. So apart from that actually, so when you are taking, there is an energy what we got, and then we will be using somewhere, and then in the buildings, in the transportation, or based on your the industries to make your life happier and then be comfortable. But most of the time we forgot to notice about what is going on globally, and then how we are part of those kind of changes, whether it's a big change or the small change, something like that. So we were part of the bigger changes which happened last 15, 20 years, very, very rapidly happened actually. So the global warming, and then the global temperature rise, and then the carbon dioxide, what we have put onto the atmosphere is a huge actually. So if you are taking the earth with the health checkup, and then you will see what I meant to see actually. So a couple of weeks ago there was a documentary in Blue Planet or in the BBC. So they showed quite a lot of ice melted, and then the sea level rises and that stuff. As I mentioned before, there is a scenario of few countries we are going to lose in this aspect as well actually. Aspect, and then the other one is, so we produce electricity, and then most of the people are using it, but still about 1 billion people, they never ever see electricity, or they have no idea how to where the electricity is generated, how that can be used for the betterment of their life and that stuff. Almost like 1 billion people, they never see any electricity, and then almost like 500 million people, so they are living in the African countries where the electrification rate is less than 14% in those countries actually. So at the same time, so where 1 billion people are more than 1 billion people, they are under the energy stress. So but at the same time, we the developed countries or developing countries actually, we use huge amount of energy in that scenario. So you can see there actually, so this is some of the data you can get from the internet, but you can see this changes here actually. The Bitcoin miners actually, you can see some of the Bitcoin industry is going down last 2 weeks or 3 weeks actually. Still the more and more energy can be spent, or the people are spending energy to mining the Bitcoins actually. They are using like what they are using in the entire year. So the Bitcoin miners in a very minor portion in the world. So they are also using that type of that much amount of electricity there actually. Okay, so how to deal with it? And then the only solution I will put forward are the most of the time it maybe looks very weird. Somebody is talking the solar is the only way to go forward, something like that. but you can see from these images and then from these the fact what is given in this slide. So you can see how much energy we are getting every year, and then how much we will be using it every single year. So in 2018, so we have used 628 joules of energy, and then that went down a little bit in 2020, where the lockdown was happening, a couple of times, and then after that it increased again actually. So we are almost like increasing more than what you did in 2018. We have started using in the last quarter of the 2022. Almost if you can have a technology which can able to convert or taking the energy from sun for 6 hours from desert or wherever it is possible on the earth, so then we can able to meet out the entire energy need of the earth or for us for an year actually. Okay, so that much amount of energy we'll be having. So how to harness this energy? There are 2 ways to do that from solar. One is the PV, another one is the thermal side actually. So I'll be concentrating only on the PV side today. And then the PV started in 1950s actually, and that starts with the silicon coming from the electronics industry waste. So then that can be generated some kind of an electricity there. So that's how the PV started using as the first generation. Second generation, they have a focus of having the less material usage and then trying to have a higher efficiency, and at the same time they wanted to reduce the cost of the first generation materials as well. So that's how the thin film solar cells or thin film PV came into the picture. And then third generation is having a more kind of an approach towards the environmental friendliness actually. So and then the higher efficiency as well as the low cost actually. But these 3 technologies, they have their own kind of advantage and then disadvantages. The most of the disadvantages from the first and second generation is coming from their material usage as well as the cost of those technologies. The third generation is having a completely different kind of an problem, comes from the low stability as well as the scaling up challenges. When you are scaling up the devices, then you drastically will lose your energy conversion. So this is a solar cell efficiency chart actually. So you can see plenty of technologies available, plenty of materials are there. They can able to convert the sunlight into the electricity. So we have a few technologies here, but I'm going to focus on third generation solar cells hereafter. So third generation solar cell is nothing but dye-sensitive solar cells, organic PV, or perovskite type solar cells. So these technologies started in 1990s actually. So and then the dye cells take the inspiration from the nature. So how does the photosynthesis work? Then that's how the dye-sensitive solar cells has been assembled, and so it is completely, we call them as a kitchen type solar cells. You can take the completely environmentally friendly materials and you can able to generate some electricity from there. And then the organic PV, so they one step ahead from the dye-sensitive solar cells, because dye-sensitive solar cells, they're using the liquid inside actually. So they try to avoid the liquid in their junction, and then they will have the lots of organic material instead of dye and other stuff actually. That's called the organic PV. The perovskite PV is the combination of these organic and then inorganic materials. So it is based on the perovskite structure of material, so that can be able to convert the sunlight into the electricity, something like that actually. But these cells actually having a lot of advantages, like they are very flexible, and then it can be applied to any type of climate conditions, and then it can absorb the maximum sunlight possible from the sun, and it can able to give you a low cost and then low energy production cost, and then the payback time will be very, very quick for these ones. Apart from these advantages, they are environmentally friendly materials as well. The challenges for the type of third generation solar cells are lies in the three categories. One is the efficiency, and if you take the efficiency of these solar cells, so the die cells, so they achieved almost like a 14.5 nowadays. The organic PV always give you a 10 or 12% efficiency, and the perovskite PV, almost reaching the 26% efficiency, which is very, very close, or I think in some cases it beat the silicon solar cells as well. But at the same time, when you are scaling it up, so these are all you can one way or the other from that chart, and then you can take the efficiency in a very, very smaller scale. It's not in the bigger scale. So when a smaller scale, behaving like a 20%, 25% is not making any sense actually. So you need to have a bigger ones, like at least a meter by meter, or which is used in the commercial scale applications. So you need to have a decent kind of an efficiency. So for that, you need to have at least 10% efficiency in a large scale systems, and these die cells can able to give you a 10% efficiency, and then the organic PV can able to give you a 13%. The perovskite solar cells at the moment, so they can give you almost like an 18% in the panel, but they struggle with the reliability and the stability issues. So so this is the one aspect of the story. So you can take the solar cells, and then some of them are very costly, and some of them are not able to apply in all the part of the world. Some of them are will not work in a certain type of condition, something like that. So third generation solar cells will hit all type of dots very clearly, and then it can able to connect, except the stability and then reliability issues, or the scaling up issues sometimes will happen in the perovskite solar cells as well. So, I will focus on two aspects from here. So how our research, joining with ESI back in Exeter actually. So I was there for 9 years. So I just moved here to Edinburgh University. So before that, we tried to work on quite a lot of things actually. So the first aspect of these third generation solar cells, whether can we able to use them in the building. So if you want to use them in the building, certain criteria you need to meet actually. So for that, your solar cell has to be flexible, and then it can be adapted within the building anywhere. So the Gabriel, our industrial speaker, he can give you a very clear picture on these aspects. So how the building can take the solar cells easily, and then so what are the clear kind of criteria you need to have. But some of the criteria I want to lay out here actually. So if you wanted to have them in a certain southwest portion, then you may have the irradiation of 100% from that type of solar panel. So for if you take the silicon thin film or any type of solar cells, you need to have the more sunlight for them to perform better in the day. So if the direction of your solar panel changes, then you will be losing the sunlight throughout the year actually. So you will get maximum like 50% if it is facing the east. If you are putting them towards north, then you may lose almost like most of the sunlight you will be losing it. So apart from that, so if your roof is on the solar panels, so if you are planning to put them on your windows or something like that, so then so the biggest issue what we will have might be the shading issues actually. So how the shading will be happening every day, and then during the morning time, midday, and then afternoon. So then your panels have to be wired in a way to do that actually. So some of these things you can able to overcome by having a different type of technology. This is one of our projects. One of our PhD student, Dr. Hamid Al-Rasibi, he has performed this work in the ESI. So he has created several boxes with different types of transparent cadmium telluride solar cell in there actually, and then he tried to measure, what is the performance of the solar cells in a different conditions, and then how much heat it can able to generate within those rooms, and then what is the cooling effect you need to provide, and then how much can able to save, something like that. So it is very important for you to calculate all these aspects. So how much you are going to generate, how much you are going to spend, and then how much you can able to left out with that one, and how much heat during the day you are going to generate, and then how whether you can able to use it wisely inside your rooms or some other purposes. That's also another kind of issue. So the other one is when you have a window, the window is very plain, so you don't want to put a something on top and then block your sunlight coming inside the house. So to avoid these kind of problems, so we use concentrating optics on the solar cell, and then try to reduce the size of the solar cell, and then you will have a more sunlight will be coming inside. At the same time, you can able to generate the electricity there. The build solar, as Tapas yesterday mentioned in his opening talk. So the build solar, the spin-off from the ESI, so they are exactly doing the similar kind of things, which they can able to create the glass blocks, which can able to allow the light as well as generate the electricity there. So what we thought actually, so if we are enlarging the surface area of the perovskite solar cell, so tend to degrade faster, as well as they will lose their efficiency faster as well actually. So what we thought actually, so plugging the concentrating optics as well as the perovskite solar cell can able to make some changes to these aspects. So that's what we tried with the perovskite solar cell, and the results are very encouraging actually. So the paper, you can see a full paper maybe a couple of months time actually. So that's the one aspect of doing it, and then other things actually. So you will try to make your houses as much as possible heat can able to withstand within the buildings actually. So we have done some work on these ones as well actually. So the conference organizer Anurag Roy actually, he has done quite a bit of work on the passive cooling of the building, especially for the cow shed. So taking the graphene material and then use the sun radiation, how to space cool those type of research also we try to do there actually. Apart from that actually, so we try to focus on the stability and the longevity of these perovskite solar cells. For that, so we do quite a lot of modifications on, and then temperature, instead of having a sophisticated arrangements to make the perovskite solar cells, and then we change the architecture of the solar cells, with quite a lot of materials input like inorganic materials or mixed perovskite, or having a carbon materials inside, something like that, as well as we want to see how big we can able to make. So we try to make them through the screen printers mostly, and then one of our students now he started working on the 3D printing, and then the inkjet printing also. This kind of a mixture we try to achieve the large scale depositions as well actually. So in terms of the going forward, we try to utilize this material better within the buildings actually. So and then we use them room temperature as well. So that's if we achieve quite a good efficiency, the number wise, like more than 15% in a large scale solar panel. So then that's the way forward for most of these kind of applications, like building integrated applications. With the perovskite solar cell, it's not far from there to achieve those kind of things. So these are all some of the works we have done. We try to tune our morphology of some of the perovskite materials, not only the organic and inorganic mix. So we try to use some of the other type of perovskite materials here, and then try to see the stability of those materials as well. And then we introduce some buffer layers like so some of the buffer layers will be the architecture, and try to see how the efficiency changes and the stability changing actually. So as I mentioned before, we try to the ambient temperature, Indian temperature, and then these are all, so we try to study very clearly. So what is the effect on the different types of temperature when you are increasing the temperature from 5 degrees to 70 degrees, and then you're lowering the temperature to 0 degrees. So what will happen to this type of solar cells? Also, we have done quite a bit of work. So apart from these building applications, so I strongly believe the transportation sector is the biggest area for solar to concentrate. So as I mentioned before, there are two ways to utilize it actually. So one is the heat, another one is the light. So, but in the transport sector, mostly the light can be utilized in a proper way. So you can use them as an electricity. You can directly generate it, like the Gabriel solar wall and or something like that. So you can use them, store that energy, and then using it to charge your car, or you can just make the artificial photosynthesis route and trying to make the solar energy energy as well actually. So these are some of the solar kind of vehicles in the then and there people can be tested. Nowadays my group is trying to work on the fuel cells actually, so trying to connect the solar cells and fuel cells and trying to create a extra mileage for the bikes actually. So we developed a hybrid system for battery and fuel cell based system to develop these type of vehicles as well actually. So for the future, so this is a kind of what happened before 2010, after 2010, what is happening in the solar, and then after 2035 or after 10 years down the line. So what solar can be achieved actually? So like 80% electricity can be able to get from from solar actually, at least for the US, and many things we can able to do that actually. So and on hopefully I'm sure you have heard about from person of within yesterday, and then we were talking about the how solar can be able to achieve with a less price actually. So those kind of things also looking forward, and then the better grid integration and solar factories. Like you will have the centralized part to make your energy, and then you can distribute locally. So those type of things, and then increase efficiency, not only based on the not on the solar cell efficiency, but the system level efficiency can be also. And then thank you very much for listening to me. And then this is our who are part of the works actually. So whatever I have presented there, this is the team when I left from ESI actually there. Yeah. So thank you very much, and I'm sure it may be a little bit of useful to you. And then last but not least, so we have only 1 year, and then it's our duty to make it clean, and then keep it clean and leave the earth, whatever the situation you have it, and then leave to the next generation as much clean as possible. Thank you.
Thank you very much, Dr. Senthil. It's nice to hear from you. And if anyone has any questions, please, we have time, so we can take a couple of quick question. Gabriel, do you have any question from Senthil, for Senthil?
No, I'm okay. Thank you. Sorry, very interesting, but I didn't note any questions down at that moment. Sorry.
Senthil, do you have any question for Gabriel?
Yeah, for Gabriel, actually, so you mentioned you have a huge amount of calls, and then the designs and other design aspects you can't able to cope up with the volume of the inquiry and other stuff. So is there a way forward, or do you think this trend will continue for some years, or it may goes down after the our new central elections and other stuff? Maybe if we get a better kind of a policy and other stuff, will this trend goes down, or it will continue to follow?
Yeah, well, I'm very much hoping that the capability of the installer base will continue to increase. We are doing as much as we can, recruiting as basically as quickly as we can, whilst keeping the training, basically the technical competence of the company as high as it needs to be. And we're also working with our industry bodies, the Solar Energy UK, which is the trade association. We are working with other local installers, as we have networks to try and help each other with essentially training. And we're also working with the local sort of colleges as well to try and help them with their kind of training programs. But it's just it's a slow progress. One of the problems we face is, I mentioned earlier, we have a operations and maintenance department which basically looks after existing systems. Because of the nature of the solar coaster, a huge amount of the solar that's been deployed has been deployed by people who are not skilled to deploy it. And if you design it and install systems incorrectly, they can be dangerous. There's live DC on roofs and stuff. So it's very tricky getting the balance right between being able to deploy, stopping climate change, and getting the training, getting the right people up to the right levels. But again, yes, we are. We were 30 people, sort of 18 months ago. We're now over 50. We are investing heavily in IT as well as systems and processes to not only help us train more people, but to enable us to deploy more with the same people we have. So we're getting more efficient. I think we are, we're basically able, today's run rate, we're installing roughly sort of 50 panels per day, every day of the year. That's kind of on average where we are at the moment. And we're expecting growth of about, 30 to 35% per year. We see as kind of sustainable growth. If we had trained, qualified people, the demand, we could triple, every year without a problem, but it's impossible to do that without the right people.
Thank you, David.
Okay.
That's it, Anurag, from me.
Yeah. Thank you so much, both of you. I know how busy you are, and thank you for accepting our invitation. I can see one quick question for Senthil. Is CDT, cadmium telluride, make semi-transparent cell?
Absolutely. Yeah. So transparent, semi-transparent, everything we can able to make actually. So like a 500 nanometer of thickness of cadmium telluride. So that can make almost like a 9% efficiency in a cell level, like a 1 centimeter per 1 centimeter. So in a module level also, so you can get more than 11 or 12% efficiency for like 70 or 80% transparency.
Yeah, thank you very much. I think Dr. Paresh you have received your answer. Anyway, if you have any question, just check with those. Yeah, thank you. He says thank you. Anyway, very, thank you so much again, once again, all the speakers, Gabriel and Senthil, for your time. I know how busy you are, and we are giving your valuable time with us for this conference. We must appreciate it. Thank you so much. And
then all the best for the rest of the day. And it's a wonderful conference. I'm coming and going actually. So last 2 days, yeah.
I know the Edinburgh cooling.
You can see, yeah.
yeah, I can see you.
Yeah. Okay.
Take care. Thank you so much, Gabriel, for joining. Thanks a lot. So we will stop here for actually 20 minutes comfort break now, because we are a bit ahead of time. So the next speaker is the next session is our ECR session. So the early career researcher sessions will be start after 20 minutes. So we will pause here for 20 minutes as a comfort break. So grab a coffee or something. So we will be right back after 20 minutes, and we have 4 emerging ECR speakers. And believe me, they are doing excellent research in their field. So from battery, and we will go to perovskite, then we will jump to solar thermal, and then again battery, and straight away we have across the globe. So stay with us. We will stop here for 20 minutes comfort break, and we'll be right back. Thank you. Welcome back, everyone. Once again, thank you so much for joining with us and stay with us. We are now moving to our last session of this conference, which is designated for the ECRs, the early career researchers. So we have 4 speakers from 4 different universities across the globe. So the first speaker of this session is Dr. David Trudgian. Sorry, David, if I mispronounce your surname, excuse me. So David is from the University of Exeter, UK. He is expertise in the batteries and the membrane development field. So we will see that how David's research is impacted in energy sectors. So over to you, David.
Thank you very much, Anurag, and hello everyone. Let me just share my screen. Okay. Sorry. Okay, is my screen visible there?
Yes, it is visible.
Excellent.
Yeah,
Thanks, Anurag. Okay, yeah, thank you, Anurag, for the great introduction, and hello everyone. So today I'm going to present some of the work that we've done on carbon cathodes for the hydrogen bromine redox flow battery. So I'll give a brief overview of redox flow batteries and then go into a little more detail on the hydrogen bromine system, and then I'll present some of the research work that we've done in this area. So many of you are probably aware of redox flow batteries, but so just a quick overview of what they are. So redox flow batteries utilize a pair of reduction oxidation reactions, one at each electrode, hence the redox term. And in contrast to more traditional batteries, in redox flow batteries, the electrolyte is stored in external tanks rather than in the cell itself, and then it's pumped through the cell during operation, thus the flow term. So the advantages of redox flow batteries, well, for most redox flow batteries, capacity and power are decoupled, so that gives us some design flexibility. So the capacity is normally determined by the volume and concentration of the electrolyte, and the power is defined by the size and number of electrodes. So that allows us to tailor systems for specific applications. So we could have a high capacity, low power system, or a low power, high capacity system. There are, of course, disadvantages associated with redox flow batteries. So the main one of these is that they have a relatively low energy density compared to other battery systems such as lithium ion. So they're not really suitable for portable applications. So they're not really for EVs or portable devices, but they are more suitable for large scale grid applications. So grid reinforcement, supply and demand management, and coupling with renewable energy installations such as solar. The other disadvantage of RFBs is that they have a high cost, particularly the currently commercialized systems such as vanadium and zinc bromine systems have a high cost. And that's due to 2 main factors, really. The first is most RFBs need an ion exchange membrane, which they're quite fragile and quite expensive. So a large proportion, up to sometimes it's quoted 15 or 20% of the upfront cost of these systems can be ion exchange membranes. And also, particularly in terms of the vanadium flow battery, the vanadium active materials are very expensive. And yeah, for vanadium, actually, the majority of the upfront cost is associated with the actual cost of that active material. So looking at the hydrogen bromine system in a bit more detail. So as the name suggests, it has a hydrogen electrode and a bromine electrode. And the electrode reactions are shown there at the top of the slide, and the overall cell reaction as well. So the charge reactions are shown in the left to right direction, and the discharge reactions are shown in the right to left direction. So the advantages of this particular system, well, it has a potential for a very low cost compared to existing systems, due to the abundance and inexpensive hydrogen and bromine active materials, and also it has the potential to be operated without a membrane, so that further reduces the cost. Also, the hydrogen and bromine reactions have quite rapid kinetics, and that allows for the system to be operated at a high power density. And power densities up to 1.5 watts per centimeter squared have already been demonstrated at the laboratory scale. So the aim is to increase that further. So of course, as with any system, there are challenges associated with the hydrogen bromine system. One of these is the stability of the hydrogen catalyst. So that can be poisoned by bromine crossover between the electrodes. So bromine can cross over from the bromine electrode to the hydrogen electrode, and that then can poison the hydrogen catalyst. And that's a particular issue, of course, if we operate the system without a membrane. So crossover can occur much more readily. And the other challenge, and this is more relevant to what I'm going to present today, is in order to achieve the high power density capabilities of the system, we need to reduce the cell resistance and also develop high current density cathodes. So that's high current density bromine electrodes. And that's what I'm going to focus on today. So what's the target? So the target of this research is to develop bromine electrodes capable of charging and discharging at current densities in excess of 1 amp per centimeter squared, and thus facilitating higher power density operation. And in order to do this, we need highly conductive materials with high surface areas and good activity for the bromine reaction. And why do we use carbon materials? Well, the hydrogen bromine system uses a hydrobromic acid bromine electrolyte, and that's highly corrosive. So even platinum-based materials aren't stable in that environment over extended periods of time. So that leads us towards using carbon materials. But that's not a bad thing, because carbon is, of course, it's highly conductive, and it's easily modified to enhance the surface area and the catalytic ability. So in order to improve the performance of these cathode materials, we've taken a dual approach. The first of these is to improve the catalytic ability of the bromine electrodes by surface functionalization. And there's two approaches we've taken to that. And the first is through thermal oxidation and acid etching, and that introduces oxygen-containing functional groups to the surface of the electrode. So that work is actually completed by my predecessor in the project, Dr. Yaksh Popat. So I'll give an overview of that work, and more detail is available in our recently published paper, details of which are there. And also we've looked at surface functionalization through hydrothermal amination. So that introduces nitrogen-containing functional groups to the surface of the electrode. And then the other approach is to increase the surface area of the electrode. And we've done this by application of nanomaterials to the electrode through a very simple process, which I'll discuss further shortly. So firstly, to look at surface functionalization by thermal acid oxidation. So this is the work conducted by my predecessor. So many thanks to Dr. Yaksh Popat for that. So what we've done is we've subjected a number of commercially available materials, so carbon papers, felts, and cloths, to thermal acid treatment. So the thermal treatment just involves heating the materials in air for 5 hours at varying temperatures, and the acid treatment is simply immersing the material in sulfuric acid for 24 hours. And so before we discuss results, just to clarify what we're looking at here in this figure in the top right. So these are polarization curves that just look at the relationship between the potential applied to the electrode and the current density. So what we're looking for here is to increase these current density figures within this potential range. And as I said, the target ultimately is to achieve 1 amp per centimeter squared for these values. And then here we have the potential response with respect to time during oxidation reduction cycling of the electrode. So here we've applied a specific current density. In this case, it's 300 milliamps per centimeter squared. And then we observe the potential response with respect to time. And you can see we have alternating current potential responses, during this period. So we've got the higher potential plateaus here, and that's related to the charge of the electrode, and then the lower potential values are related to the discharge of the electrode. And what we're looking for is a narrower band gap between these two potentials, and that translates to reduced overpotentials applied to the electrodes, which improves the voltaic efficiency and therefore the energy efficiency of the electrode. So you can see that we've taken the oxidation or the charging current densities and the discharge current densities from part A of the figure in this table, and then the ratio of the reduction in oxidation potentials, which is analogous to voltaic efficiency from part B. And what we can see is that increasing the temperature improves the performance in terms of the achievable current density of the electrodes. And once the temperature passes 500 degrees centigrade, the thermally oxidized electrodes outperform the acid etched materials. And the best performance is achieved on materials oxidized at 600 degrees centigrade. But what we find is that the electrodes after treatment at that temperature become very fragile and mechanically unstable. And that's due to carbon dioxide evolution from the electrodes. So when you heat the electrodes at these high temperatures, you actually oxidize the carbon to the point where carbon dioxide is produced and released from the electrodes. And you can see the result of that in these SEM images. So this is for a different carbon paper actually, but you can see the as received material on the left, and then after it's been thermally oxidized at 550 degrees centigrade on the right. And you can see the increased pitting and surface roughness is due to the evolution and the escape of carbon dioxide. So in one regard, that might be beneficial to performance because it increases the actual surface area available for the reaction. But beyond 550 degrees, the degradation of the material itself is so much that it compromises the mechanical stability. So the main takeaway from this is to show that we do have good improvements in the performance of these electrodes using these techniques, but we haven't yet reached our 1 amp per centimeter squared target. And I haven't shown it here, but XPS analysis has confirmed that after thermal oxidation, we get an increase in phenolic carbonyl and carboxyl functional groups on the surface of these electrodes, and that increases the hydrophilicity of the material and increases their catalytic ability for the bromine reaction, and that's why we see the improvements in performance shown here. So moving on to hydrothermal lamination. So we've hydrothermally laminated the materials by immersing them in ammonium hydroxide in a pressure vessel, and then we heated them at various temperatures for various treatment lengths. And again, we've got polarization curves here in part A of the figure. Part B is oxidation, reduction, and cycling results. And we can see that increasing the length of the treatment improves the performance. But what we see in part C, which plots the achievable current density against the treatment time for the 3 different temperatures we've tested, is that while higher temperatures produce better performing electrodes for shorter treatment times, as we extend the treatment time, the lower temperatures actually produce better performing electrodes. And I won't get into too much detail as to why that is, but it's to do with the type of nitrogen functional group that we're introducing to the material. So we could introduce pyridinic, pyrrolic, or graphitic nitrogen to the carbon materials, and which type of functional group we introduce is defined by the time and the length of the treatment. So what we find is carbon cloth hydrothermally laminated at 120 degrees for 16 hours produces the best performance. And we've got current densities here between 800 and 900 milliamps per centimeter squared. So we're getting closer to the 1 amp target that we originally set, but we're still not there quite yet. So moving on to the second approach that we've taken is to enhance the surface area of materials, and we've used carbon cloth and carbon paper to do this. And we've just a very simple and cost-effective technique in order to keep the cost down. We've just applied carbon black or graphene nanoplatelets to this using a drop casting method. So what we've done is taken a 9:1 mass ratio of the active material, the carbon black or the graphene nanoplates to a Nathium binder, and then we've ultrasonicated that and homogenized that to produce a dispersion. And then at lab scale, we just drop cast that onto the carbon cloth or carbon paper. At larger scale, we would spray coat it, and then just allowed that to dry. So the SEM images in the top right there, you can see the top row shows this is carbon cloth, and the top row shows the pristine material. The second row shows the material modified with carbon black, and then the third row shows the material modified with graphene nanoplatelets. So in order to quantify the increase in surface area of these materials, we've used cyclic voltammetry to obtain double layer capacitance values for the material, and from that we can calculate the electrochemically active surface area and the roughness factor. So we've taken the roughness factor of the materials compared to the as received materials, and this shows that in terms of the graphene nanoplatelet materials, we've increased the surface area by a factor of 8 roughly, and with the carbon black we've increased the surface area by a factor of over 10. And that's not surprising if you look at the bottom right here. We've got the BET surface area of the 2 materials. So the carbon black actually has a surface area roughly double of that of the graphene nanoplatelet. So it's no surprise that these produce materials with higher surface areas. So moving on to the electrochemical performance of these materials. So again, we've got the polarization curves and the cycling responses here with the numerical values taken from there in this table. And what we see is that the the graphene nanoplatelet electrodes actually, under these conditions, outperforms the carbon black electrodes, in spite of the carbon black electrodes having a higher surface area. So that was a little bit of a surprise, and I'll go into more detail on the next slide as to why that is. But for the graphene nanoplatelet modified materials, we've increased the reduction oxidation potential ratio. So that's analogous to the voltaic efficiency of the electrode by around 62%. And in this case, we have achieved a targeted performance of at least 1 amp/cm² within this potential range. So for the graphene nanoplatelet electrodes, we've got current densities of between 1.1 and 1.2 amp/cm². So we have achieved the target. So why do the graphene nanoplatelet electrodes outperform the carbon black electrodes, despite the fact that the carbon black electrodes have a higher surface area? Well, as I alluded to earlier, the surface area is only one factor that affects the performance of the electrode, the other being the sort of kinetic ability of the material towards the bromine reaction. So in order to assess that, we've conducted some linear sweep voltammetry. So we just scan the potential of the electrode and observe the current response. And then we've adjusted the current response for the surface area values that we calculated, that I presented in a previous slide. And then from there, we can calculate some very commonly used kinetic parameters. So the charge transfer resistance, exchange current density, and rate constants of the materials, using these quite simple relationships here. And what that shows is that the graphene nanoplatelets actually have a much lower charge transfer resistance. So that's essentially the resistance caused by the reaction, so the resistance to the reaction, and it has higher exchange current densities and rate constants. So the catalytic ability of the graphene nanoplatelet electrodes, even taking into account the surface area, is higher than the carbon black electrodes, and that's why we see the improved performance of these electrodes that I presented on the previous slide. However, when we go on to look at the effect of varying electrolyte concentration on the comparative performance of these electrodes, that the case sort of changes a little. So the first thing to note is that as we increase the electrolyte concentration, the performance improves, and that's to be expected really, because the conductivity of the electrolyte increases as we increase the concentration, and also the availability of the reactant obviously increases as well. But what we see is that in a 3 molar hydrobromic acid, 1 molar bromine electrolyte, which is electrolyte used in the data I presented previously, we see that the graphene nanoplatelet electrode does outperform the carbon black electrode. But as we increase the electrolyte concentration to 4.5 molar hydrobromic acid, 1.5 molar bromine, the two electrodes perform almost identically. And then as we increase the electrolyte concentration even further to 6 molar hydrobromic acid, 2 molar bromine, then the carbon black electrode actually outperforms the graphene nanoplatelet electrode. So that's interesting, and what it suggests is that the carbon black electrodes with the higher surface area may be better in the early stages of charge-discharge of the battery, while the graphene nanoplatelet electrodes may be preferable towards the end of discharge when the reactant is less available. So mass transport of the reactant becomes more of an issue. So the best performance we've achieved so far is actually on a carbon cloth modified with carbon black in the high concentration 6 molar hydrobromic acid, 2 molar bromine electrolyte. And we've reached current densities of almost 1.6 amp/cm² there. And we can cycle that electrode at 1.5 amp/cm² with over potentials of plus or minus 350 millivolts. So that's well in excess of the original targets, but we still feel that there there's more potential for further gains. And in order to achieve that, we're currently synthesizing nitrogen-doped carbon nanofiber electrodes, employing an electropolymerization pyrolysis technique. So that's a 2-step technique. The first step is the simultaneous electrodeposition and electropolymerization of, in this case, we're using aniline to produce nanofibers that already contain nitrogen as a carbon precursor, and then we pyrolyze and carbonize those polymer nanofibers to produce nitrogen-doped carbon nanofiber electrodes. And what we believe is that this will produce very high surface area electrodes that are also very active for the bromine reaction. And we're hopeful that this will push the performance of electrodes even further. And I'm optimistic that we can achieve current densities in excess of 2 amp/cm² using this method. So finally, just to acknowledge the Melody project, which funded this work. So this is an EU-funded project under the Horizon 2020 scheme. And I'd just like to thank all of our project partners. You can see our project partners there at the bottom of the slide. And if you're interested in this project, we have a website and a LinkedIn page and a Twitter account, which will provide regular updates to the progress and outcomes of the project. So please do follow them if you're interested. So thank you very much for listening, and I'll be happy to field any questions if we have time or in the chat afterwards.
Thanks, David. Wonderful talk. I just have a very quick question. Do you think the morphology has a big impact on this membrane performance?
Yes, that's a good question. So yes, the morphology will have an impact in terms of the surface area. So, the surface roughness will increase the surface area, and that should, in theory, increase performance. But also, and we haven't gone as far as to study this yet, the porosity of the material will be very important, particularly in a flow cell. So there will be an optimal pore size of the materials as well, in terms of making sure that we can flow the electrolyte effectively through the material to make sure that the mass transport to the surface is consistent. So yes, the morphology will be important. Yes.
Yeah, that's it. Thank you very much, David. Please stay with us. If we have any questions for you, we will take it if the time allows. So thank you for your time. Next, moving on to our next ECR speaker from Exeter straight away to Oxford. So we have Dr. Shantanu Shah from the University of Oxford, UK. Shantanu, over to you.
Thank you very much, Anurag. Okay, so I want to share my screen. Okay, I can see. So I'm visible, audible?
Yes, you are visible and audible both. Go ahead.
Okay, great. Okay, so thank you, ESI team, for inviting me for this event. So I am Shantanu Shah, working in the Department of Physics, primarily on finding new materials for energies, for energy applications using DFT or first principles, not doing experiments. So what I'll do is today I'll talk about how we can use first principles to understand existing materials or experiments, and also see beyond the experiment and try to find new materials. So before I start my talk, I want to thank all the financial, the computing and the funding resources to support my work in the department. So here's my outline. So I will start a brief description of what is the basic theory which we're using. It's not just a black box. And then I'll give an example of how this has been used recently on experimental studies, and then a priori, that means before experiment, if you can use this kind of approach to find new materials, particularly which is beyond perovskites. So coming to what we generally use is known as the typically Kohn-Sham theory or density functional theory. So this was given by Kohn and Sham in 1960s. The basic idea is this, that to describe any experimental system, you have atoms and molecules. So in atoms, you have the ions and the electrons moving around. And to describe the electrons, you write a wave function, which depends on the position of the individual electrons. And typically, if you write something like in a Schrödinger format, you have something like this, which is function of all the coordinates. So this is what you call as a correlated wave function. But these are very hard to solve in real life. So what Kohn-Sham came with is, okay, we can break down these wave functions into individual particles, and they become kind of independent, or what you call like a free particle idea or independent particle. And these electrons talk with each other through what you call as through a mean potential approach. So they get Nobel Prize, Sham and Popel in 1998 because of this work. And once you have this picture or the Kohn-Sham picture, which you say, then rest comes down to writing the Hamiltonian or the energy term. So you have a kinetic energy, which is in red, the second derivative term, and then you have the interactions between electron and the nucleus, electron, and then you have this what you call as exchange correlation to take care of the approximations which you introduced in the Kohn-Sham theory. And once you solve these equations, you have the bands and the energies and everything which you need to understand and correlate with the experiments. So moving over to the first example, a posteriori, which means like you do the experiment, you come to us and we try to understand the experiments and try to come up with reasoning why it's happening from an electronic structure point of view. So this work was done in collaboration with Professor Hemamala Kamunadasa, which has just been accepted in JAX. So the idea was that they managed to synthesize chalco halide perovskite through the use of deuteronic cysteamine. So the idea goes like this, that in a typical perovskite, you have the cation Ma, cesium, or Fa, which is inside this cube formed by the octahedra. And then they introduce this cysteamine molecule where one end of the chain has the sulfur ion and the other end has the NS3+, the plus side and the minus side. And they somehow managed to come up with a reaction where the sulfur sits on the halide side and the other end of the chain goes to the middle of the cube, satisfying the cationic requirement. And they could do this synthesis at 150 degrees Celsius, which is very small compared to the typical chalcogenides, which needs very high heating of something about 800 to 1000 degrees Celsius. And the more interesting aspect of this study is that irrespective of what kind of halide you use, chlorine or bromine, you come up with a band gap which is very, very similar. So here you see 2.31 or 2.16, and the band gap difference is 0.15 compared to standard chlorides or bromides, which has something of 0.70. And we are interested to understand why it's happening. So before we start the calculations, we need to build up the structure for this modeling. So they came up with the data and said that, okay, sulfur has 1/3 occupancy and the halide has 2/3 occupancy. And we needed to arrange the sulfur and the chlorine in a way so that it satisfies this site occupancy. The problem with DFT is you cannot have a fractional occupancy. You always have to have a site occupancy. You can rearrange the number of atoms around the structure. And the additional constant is you can have one cis molecule inside the cube, which is formed by this octahedra. So we came up with this arrangement, which kind of satisfies this basic requirement. And once you have the sulfur decided at which site it will sit, then the rest of the game is just to arrange the chain of the cysteamine molecule and get the relaxed structure. So once we have this structure built up for chlorine and bromine, we did some advanced calculations of looking at the band structure and the distribution of the orbital contribution among the bands. So here you can see the contribution of lead, chlorine and sulfur, where the colored dots represents the percentage of contribution of that corresponding element at that given bands at that given K point. So if you look at this purple highlight part, so that is the gamma point, which is mainly contributing the band gap and the band edges, or what you know as the homonumo gap. You can see at the valence part, the lead has a contribution of roughly 68%, which is very similar to the typical cesium lead chloride in orthorhombic phase. If you come to the chlorine part, you can see the amount of chlorine content is drastically reduced to 3% in comparison to the cesium lead chloride. And for sulfur, you have something of the order of 35-36%. So you're effectively increasing the contribution of sulfur just by doping the sulfur in this to the cysteamine molecule. And the same story repeats for the bromine, and you can see an equivalent contribution for bromine. And what we did again is to really understand that it is a chemical effect and not a structural effect. We took up this rhombohedral structure and replaced all the sulfur with chlorine and removed the cis and put the cesium and look up the band structure. So if you look at the band edges, so here I what we call calibrated the conduction band at the same level on the top, which is shown by the 0 line. And at the bottom top, you can see the valence band edges. You can see the gap between the two edges reduces from 1.5 to 0.8 eV. For the bromine, you can see the reduction in the band edges. So sulfur is kind of acting as a knob to tune the range of the gap between the band edges. So moving further, we wanted to see if there's any influence on the arrangement of the sulfur on the electronic structure. So what we call as order and disorder. So what we created was ordered structure. You can see the sulfur lies along a chain or diagonal chain. And what we also, like in a typical, I think, chemistry is called trans arrangement of sulfur, where two opposite diagonal bonds. In the octahedra, then we created what we call for the disorder cis and trans, where in one octahedra we put two sulfur atoms side by side in the octahedra, and we calculated the band structure. And here you can see for different cases the band structure remains more or less very similar, so you don't have a big influence of the order and disorder on the band structure. So here is the list of different properties which we calculated on top of this. So the take-home message for this work is that with deuterionic cysteamine acts as both satisfying the cationic site and the anionic site, and hence it stabilizes the chalco halides. There's a dominant contribution of sulfur and the valence band, and this kind of reduces the gap irrespective of different kind of halides. And on top of that, we see that the sulfur disorder does not really influence the electronic structure of this new family of materials. So moving over to the next work, which I am pursuing at the moment in different direction, is to like what we call a priori, like before experiment using DFT and other tools like structure prediction and high throughput to look for new materials, particularly which is beyond perovskite, which has not been studied or not known. And we are all aware perovskite. There are a lot of talks. I'll not repeat. We know what are the typical problems of perovskite. And what generally one does in my field is they do a high throughput where they take the structural template, like in this case perovskite, take different combination of elements and put up different criteria like thermodynamic stability, band gap, etc., etc. And based on this, they filter out the new candidates. And what I know from now, like there's been very few papers which says that you can make a stable perovskite with copper and zinc. There are very, very few. So we thought that, okay, maybe there's something inherent with the elements which is not happy in the perovskite or the octahedra. So let's look for compounds where copper and zinc is happy. I mean, tetrahedra or some other kind of combination. So we started looking up different material databases. And then we looked for structural templates where these elements are frequently found. And then we do a high throughput scanning on those specific templates and kind of find out new candidates or look for materials which are not perovskites. So for a test case, we started with copper and zinc. It's just because they're very popular, they're abundant, they're inexpensive and toxic. And we look for templates in different material databases, like say, if they have been synthesized in nature, if they have a band gap, and if they're highly symmetric. Symmetry is very important, which gives rise to interesting optical properties relevant for energy applications. And through this search, we came up with this non-perovskite templates. An interesting feature of this is all of them have a tetrahedral arrangement, which is very frequent in copper and zinc, I assume. And then they are either corner shared or edge shared or face shared. In this case, you can see over here. And the A atom or the A site acts as a binder of this tetrahedral arrangements. So moving over on playing with these templates for the B site, like you have A, B, and X. So the B site, you have the copper and zinc, and to satisfy A and X, we found alkali, earth alkali for the copper and zinc, and halite and chalcogenites. For both these cases, we wanted to go more because we did not find much literature in this family of compounds. So we went down the periodic table for the big B site, like I mean 3D, 4D, and 5D. And these are the settings we used for calculation. If anybody is interested, they can have a look here. And to make it relevant in terms of experiment, that is, you start with some binary precursors to start your synthesis. So we kind of calculated their decomposition energy against these binaries to really see if they're stable or not. And we use hybrid functionals to estimate the band gap, which is more close to the experiment. So here is the trend which we found in general. So here you can see the gray area, which has a negative energy or the negative binary decomposition energy. That means the formed compound is going to be stable against those binary precursors. And they have the orange zone, which you call the metastable. So they have they are stable with a certain lifetime. So like diamond, they have a certain life. If you heat diamond enough at room temperature, it will break down to graphite. And with this idea, you have the decomposition energy along the x-axis and the band gap along the y-axis, which is the hybrid gap. You can see the different arrangements of these dots. So the colored are mostly the halides with different elements on the B side, and the open are the chalcogenous with different elements. So a general feature is you have the high band gap for halides and relatively small gaps for the chalcogenides. And chalcogenous are not very happy on the AB to X3 phase, but you can find something for A to BX3 and ABX2. And among these 162 compounds, we screened or we found 80 compounds which there's a possibility that you can make in the lab, and they will be stable in real life. And what interesting we found is most of them have a direct gap, I think, which is very interesting for energy applications, I guess. I think that also makes perovskite very popular, I assume, and which have a gap between 1 to 5 EV. And among these 80 compounds, only 22 compounds has been formed, which are shown by the black dots. So looking up the literature. So this is kind of very promising that our calculations kind of goes hand in hand with the experiment. It's not like a busier claim we are making. And among these compounds, I just showed a simple like a case which we found interesting. So this is one of the compounds which has almost 3, maybe a bit higher for photovoltaics. Maybe it's useful for other applications like LEDs and everything else, which has a direct gap, and the effective masses are not very huge, so with the level. And along the band edges, you can see the contribution is mainly coming from the chalcogen and not from the other elements. But the take-home message from this is, with this kind of process, you can really screen out compounds and find new interesting cases. And here you can see a band gap which is large for halides and small for chalcogenides. And this kind of ideas is more adaptable and applicable to a wide class of materials. So what I want to say, or a brief outlook from this, is you can use or adapt first principle methods to understand experiments, which is very popular in this field, I assume, but also you can take a step back and take help from this kind of methods to really like fix the domain or find new hunting grounds for new materials which has not been explored. There are a lot of compounds, I think millions and trillions of compounds which have not been searched. So there are a lot of areas which can take help of these methods to jump in and explore more. Yeah. So here's my email, and if you are interested to discuss or contact me, I'm happy to talk. Thank you very much.
Thank you so much, Shantanu. It's a wonderful talk, and I think everybody should appreciate Shantanu's presentation. Lots of information. Due to running out of time, I'm sorry that I can't have many questions for you, but please, if you can stay online, and once we finish the session, and if you have time, so we maybe go for a couple of questions with you.
Okay, sure. Yeah.
Thank you so much for your time. Okay, moving on to our next speaker, straight away to India. So we have Dr. Amrit Kumar Thakur. He's a postdoctoral researcher at Indian Institute of Technology, Bombay, India. So he's going to talk about the solar desalinations units for sustainable water purification. That's quite interesting. So I will share his slides on behalf of him. So Amrit, are you online?
Yeah. Hi, Anurag.
Yeah, hi, Amrit. Good to see you. So I'm going to share your screen. Just let me know whenever I
need to stop. Sure.
Yeah.
Yeah, I think it is perfectly fine. So thank you so much, Anurag, and the whole team of Exeter for giving me the opportunity to present my research. This is Dr. Amrit, from postdoctoral researcher from IIT Bombay. My major research is related to solar desalination, water purification using novel material, 2D materials, and battery thermal management. So today the talk is related to nanomaterials in form of coating as well as in form of phase change material for improving the overall desalination performance for sustainable water purifications. Next slide, please. So the major reason for choosing the solar-based desalination basically on the South Asian countries, specifically India, is that we have abundant availability of the solar radiation throughout the year, and the other existing methods are high in energy. That is, most of them consume supreme amount of energy, and with the availability of solar energy, it could be a sustainable option for using such. The demand of water is increasing with increasing population, and we are expecting to have a even more worsen scenario with progressing year, because the major sources of water are like getting excessively exhausted due to the excessive rise in population. So we must need to have this sustainable method for water purification based on the increasing demand. Next slide, please. So there are already wide availability of purification methods for cleaning the brackish water and the other contaminated water for drinking purpose, but all of them consumes huge initial cost, and they need the high intensive method for purification. Solar desalination is one of the most robust method, and it is most sustainable method for purifying the waste and brackish water using the solar energy in form of evaporation condensation, which can be taken place throughout the year if the availability of solar radiation is there. So among the available method, the solar radiation could be easily entrapped in different forms such as nanofluid, nanocoating, or phase change material for overall increasing the rate of evaporation condensation mechanism so as to increase the water generation potential. The bottleneck of this technology in many years are the overall thermal efficiency and the amount of water generated using these technologies, because most of them uses passive methods. So different methods have been incorporated in past several years to improve the overall output. So I will show a few of my research carried out in area of sustainable water purification using different material modifications for improving the rate of evaporation as well as condensation. Next, please. So I have divided in three categories. Like firstly, I have used the thermal energy storage material for trapping the excessive available thermal energy, and then later it has been retrieved to improve the overall performance of solar desalination for water purification. So we have synthesized a new material, that is candle soot derived carbon nanoparticle. It is a low cost material, and owing to its excellent conductivity and pore size, it could be easily used to improve the overall phase change characteristics of the paraffin wax, which is used as the energy storage material. So that's how we have collected the soot, and it was functionalized to get the nano size soot particle. Next, please. So that's how we have did the morphological study to check the structure of our derived candle soot carbon nanoparticle, and the structures are on-random structures which can be clearly seen through SEM and TEM image. Next, please. After this, we have prepared the energy storage material in form of latent heat using paraffin wax as the base material with different dopings of candle soot, and the preparation method is depicted in image. Next. So that's how we have used. This is our desalination unit, where different three structures in form of tubes are used to collect the fresh water. Initially, in the tray, we have filled the contaminated water. Even we have used seawater also for purification. And with the closed chamber and entrapment of solar radiation, our water got heated, and later with the evaporation condensation, we have achieved the fresh water. To increase the overall operational hour of the the whole unit, we have used the thermal energy storage material, which was filled in the cylindrical tube, and it was placed in the chamber for improving the overall performance. Next, please. So this was the phase change material morphological. So basically the conventional PCM has shown the waxy color, whereas the red color is clearly shown the entrapped carbon inside the paraffin wax. It's formed the chain structure which help in conducting the heat for longer duration, and it will improve the overall performance of the unit. Next, please. Moving further, we have measured the thermal conductivity using the Tempos device to check that what is the effect in heat transfer in terms of storing and discharging the heat with repetitive cycles. So we have measured the thermal conductivity. Next, please. So with doping 0.1 and 0.38% of candle soot, significant amount of thermal conductivity, we have increased the thermal conductivity by almost 41% with doping 0.38% in paraffin wax as phase change material. It was achieved only due to the faster conductive network of candle soot carbon nanoparticle offered with improved thermal conductivity. Next, please. Later, we have also checked the thermal stability of the phase change material and then DSC. So there was a meager reduction in latent heat, which is quite obvious with the doping of carbon-based particle. So it was comparatively lower than the other other carbon-based particles, and it would have the much effect on storage potential. So it was found to be suitable for using in the inside the tube for storage applications. And after that, we have conducted the experiments. Next, please. So that's how we 3 sets of experiment has been conducted. One was the conventional desalination unit without any phase change material. So the peak temperature of water was around 53 degrees C. And the other 2 cases after doping only phase change material and then phase change material with 3.3% candle soot, there was significant increase in the temperature of water. Next. So there we go. We have only used paraffin wax without any doping of soot particles. So the peak temperature has increased and reached. And after that, when we have further added the candle soot in PCM, the temperature has further increased and reached. Drug, next, please. So this was the final experiment conducted. So there was a significant shift in temperature if we see the throughout profile of the experiment, which was conducted from morning till the evening. And as can be seen that now we have a higher temperature throughout the junction from morning till the evening, and after the sunset with the storage potential of phase change material, there was a shift in temperature, even though there was a very less available radiation. So this is the nature of storage material, that it has stored the energy, and later when the radiation has dropped, it has provided the heat to the water, which has maintained the optimum temperature, even though there was a very meager radiation. So with this, we have checked that what is the overall generated water using these 3 different techniques. Next. So this was the overall output. We have also used to measure instantly hourly basis output generated, and then the cumulative output generated. So using 0.38% candle soot with paraffin wax inside the tubular desalination unit, the overall full day water output has increased by 87% as compared to the conventional desalination unit without any storage material. It has only been achieved due to the excellent thermophysical property of developed phase change material with prolonged energy storage potential, which has helped in increasing the overall temperature, even though there was a meager solar radiation after the peak hours. So this device can be used for scaling up the water purification technology in a passive mode, and it could be an alternate for the existing high intensive purification method if the radiation is available in a good availability. So this was the first part of using storage material. Next, please. So this was the publication which we have achieved using this soup particle. It was published this year. Next, please. Moving on to the next part, then we have also developed the interfacial heating material, which can entrap the falling solar radiation in the porous structure, and it could increase the overall evaporation rate when placed inside the water for generating the steam as well as for improving the overall water output. Next, please. So this is how we have deposited the candle soot in our cellulose form, and the deposited soot inside the fibers of cellulose form is clearly visible in our SEM image. Next. So the foam, even after modifying, has still the supreme hydrophilic nature, which promotes the faster capillary effect, which can take the water from bottom side, and it will expose it to the interface layer where the evaporation can be increased. So we have tried to have the localized heating using these modified foam and conventional foam. And with this, we have seen that there was significant increase in rate of evaporation and the water generation via evaporation condensation mechanism. Next, please. Here we have also checked that what is the effect of solar absorption after modifying the surface with candle soot. So conventional cellulose foam has only absorption of 25.21 in the entire range of 250 to 2500 nanometer, whereas it has increased to 92.18 in wet condition of cellulose foam with coated surface of candle soot, whereas in dry form it was 89.59%. Next, please. So that's how we have got the enhancement of absorbability in wet stage more as compared to dry stage, which has been derived using the well-established Fresnel equation. Next, please. So this was the device, and that's how we have placed the foam inside the structure. So 8 foam without any coating, and 8 foam with candle soot coating was placed inside the chamber where evaporation condensation has taken place, and we have achieved the enhanced fresh water using the evaporation condensation. Next, please. So that's how the experiment was carried out, and you can see that how the formation of vapor has started. Then later the droplet size is increased, and we could able to achieve more amount of condensate using such foams. Next, please. You can skip 3 or 4 slide, and next, please. Next. 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 Yeah, so I will come to the end part of before this one. So that's how we have concluded this experiment, that without any modifications and with candle soot modified cellulose fiber, there was a overall performance improvement, and the cumulative yield has increased by 170% as compared to the conventional unit without any modifications. So it was achieved only due to the excellent solar absorption property of the modified cellulose foam with the capillary effect, which has promoted the interfacial heating along with the localized form of solar heating, which has leads to excellent evaporation, leading to improved freshwater generation as compared to other units. So these were the part where we have focused on the interfacial, and then next part will be related to the coatings Next, please. So with this, we have published this work in RSC Nano last year. And next, please. This was also selected as the cover art for April issue of RSC Nano this year. Next. So later, after moving from the energy storage material and interfacial material, there is also an
Sorry to interrupt you, Amrit. You have 2 more minutes. Please try.
Yeah, sure. Thanks for reminder. I will be packing up. After this particular modifications, which was made in terms of evaporation, we have moved it to improve the overall output of the unit in terms of condensation. So in conventional desalination unit, mostly glass are used for the condensation, and it has the behavior of hydrophilic, which promote the film-wise condensation. So if we can alter the hydrophilic nature to hydrophobic by changing the wettability, we could increase the overall condensation generation. And this is attempted by using the nanosilicon coating, where the structural morphology has been shown using SEM and TEM images, and the changed kind of spherical structure is clearly visible for nanosilicon. Next. So that's how we have coated our nanosilicon paste on the glass using a spray technique, and then later it has been dried out for more than 80 hours to achieve the uniform deposition of the coated layer on the glass. One more feature was that there was no change in behavior of glass after coating, and there was same transparency maintained. Next, please. So that's how our device was there. So we have this conventional type of desalination unit, where one was bare without any coating, and second one we have coated using nanosilicon. Next, please. So that's how the morphology has changed. In a conventional unit, there was hydrophilic nature with the contact angle of 62, and after coating, the contact angle is significantly increased and reach 120 degree. Even in the later image, we can see that in one side there is a film-wise condensation, whereas in the next side there is a drop-wise condensation, which can increase the rate of condensation via heat transfer significantly. So by this, next please. We have also explored that what will be the effect if we are changing and flowing the droplet from top to bottom of the glass, and how much time it is taking. So without any modifications, the time taken was around 120 seconds for a conventional glass without any modifications, whereas after modification, next please. So here you can see that after the before that.
Amrit, sorry, you have to conclude soon.
Yeah. This one, I think I will be concluding. By this, we have next. Next. Yeah. So this will be the last slide. So here, before. So so that's how our overall output using the nanosilicon coated condenser has shown here. So almost 16% increase in overall output was achieved using the hydrophobic coating of nanosilicon. So these were the experiment which we have carried out in terms of condenser coating, in terms of improving the rate of evaporation, either using thermal energy storage or either using the phase change material. So that's how these things happen, and we are on the verge of scaling these technologies using more advanced energy storage material in form of MaxSean and in form of reduced graphene oxide for further increasing the output of our devices. So I think, I have taken few extra minutes. Sorry for the thing, and that's it from my side.
Very Amrit, and I'm very sorry I have to stop you because other speakers waiting for their
No
talk.
issues. No
And
issues,
thank you
no
very
issues.
much for joining us. If someone has any questions, please get in touch directly with Amrit, because due to time constraint, we have to we have to stop for Amrit's session here. So we will go straight away from India to US now. So we have Dr. Atin Pramanik from Rice University, USA. Dr. Atin, welcome. Hope you are on board. And yes, I can see you are going to share your screen. So welcome and thank you for accepting our request. Please, whenever you are ready, go ahead. Thank you.
Thank you, Anurag, for inviting me. Yes. Can you see my slides? Hi,
Yes,
everyone.
yes, I can see you. Yeah.
Okay. And to say thank you and Anurag for inviting me to present my work in this conference. So I'm Atin Pramanik, working as a postdoctoral fellow at Rice University. Today I'll speak on anion and redox chemistry on polyanionic cathode materials. Before going to the main talk, I want to discuss the points which I'll discuss throughout my talk. Introduction about lithium and sodium ion battery cathodes, and we used oxalate as a polyanion. So why we used that I will discuss elaborately, and further potassium iron oxalate and lithium iron oxalate as a polyanionic cathode for lithium ion battery and sodium ion battery applications. Finding of anion redox in polyanionic system is the main goal of our job, and further conclusion. So here we can see there is a 4 different types of battery cathode materials are presently available for lithium ion battery and sodium ion battery. Mostly layer oxide based material like lithium iron phosphate, lithium cobalt oxide, lithium manganese oxide based material was used as a battery, lithium ion battery commercial application as well. Those are under the layer oxide cathode materials. Further, people are also using Prussian blue analog and organic based compound material. So for as a cathode material, but those compounds have some issue because of stability and long-term stability of the material and long-term cycling performance as well. But on the other hand, polyanionic compounds are very stable, and within the polyanionic compounds, there is a sulfate, phosphate, silicate, mixed polyanions and acetone type materials as commonly used. So if we see the voltage versus capacity plot for the polyanionic compounds, mostly you can see that iron and vanadium based material are used as a polyanionic compound. Why iron and vanadium based materials are used? Because we know for battery those element has multiple variable oxidation states are useful. In that case, we will get more higher capacity because of variable oxidation state. And if we see the potential range, it's mostly 3.5 to 4 volt potential window for most of the phosphate based polyanionic compounds, and with the average capacity at around 120 to 130 milliampere hour per gram. But oxalate is a very new system and people haven't used that much as a polyanionic system. So we thought it should be useful to use as a polyanionic system. So why we oxalate use as a polyanionic system? We know that oxalic acid is a relatively stronger acid. It has pKa value at around 1.41 to 4.24. And it lies in between phosphoric acid and sulfuric acid. So it should be useful as a polyanion. On the other hand, we know that oxalate ligand has 4 oxygen atoms, and we know that oxygen atoms are electronegative. So it can bind to their metal center through their oxygen atom, and simultaneously it can form mono, bi and tetradentate ligand to form mono, bi and polynuclear complexes, and it is very much versatile. So we need the reversible versatile and reversible compound to use as a battery application. So inspired by this usefulness of oxalate anion, we we tried to synthesize potassium iron oxalate and lithium iron oxalate as the polyanionic system. Here we can see that the crystal structure of potassium iron oxalate and the lithium iron oxalate. So both the crystal structure is the monoclinic and crystal space with P21 oversee the phase group. And if you see the crystal structure of potassium iron oxalate, we can see that iron octahedra is connected through the oxalate anion. That I said in the previous slide. And for the one unit cell crystal structure, we can see there is a 3 potassium ion is available. So that means 3 potassium channel is available in the potassium iron oxalate. Similarly, if we see the crystal structure of lithium iron oxalate, we can see the Fe2O10 octahedral system is connected through the oxalic acid. And from that crystal structure, we can see there is a 2 different blue and pink. There is a 2 lithium site is present. So it should be useful for a battery cathode application. So let's do the electrochemistry. So when we did the electrochemistry, initially we know these materials are in crystalline material, and that's why its conductivity is not good. So before doing the electrochemistry, we did the ball milling of that material with the conductive carbon, and we make the pellet electrodes. After that, we run that cell with respect to sodium at 1.7 to 4.3 potential window, 10 milliampere per gram current density. And from the differential capacity plot, we can see there is a 4 pair of oxidation and reduction peak present during oxidation and reduction. And similarly, it corresponds to its charge discharge plot as well. And when we did the cycling performance at the same potential window at 10 milliampere per gram current density, we can see the initial capacity is around 70 milliampere hour per gram. But after a couple of cycles, when the electrode gets activated, we can see the capacity is gradually increases and it reaches to around 115 milliampere per gram specific capacity after 350 cycles. So it shows very stable and long-term cycling stability. So to understand the in situ electrochemical behavior, we compared the differential capacity plot for cycle number 5 and cycle number 200. And if you see the differential capacity plot for cycle number 5 and cycle number 200, you can see for the black one, cycle number 5, there is a 4 pair of oxidation and reduction peak is present. But if we go to the cycle number 200, we can see the first pair of oxidation reduction peak is missing. So that means something is going on here. That I will discuss in the next slide. So for any kind of battery material, we know it is very important to do the rate performance at different current densities. So we did from 5 milliampere per gram current density to up to 1000 milliampere per gram current density. Initially, you can see the capacity around 65 milliampere hour per gram at 5 milliampere per gram current density. And we know this is a very common nature for any kind of battery material. If you increase the current density, the capacity is gradually decreases. But still, for our case, at 1000 milliampere per gram current density, we can see the specific capacity retains around 35 milliampere hour per gram. And when we come back to its initial current density to 10 to 5 milliampere per gram, we can see that it comes back to its initial specific capacity. So that confirms that electrode is very reversible with respect to the rate performance. And it is also very important for any battery electrode to check the cycling stability, long-term cycling stability at higher current density. To check that after doing the rate performance, that same cell we used as a long-term cycling stability at 200 milliampere per gram current density. And we can see the specific capacity is written around 50 milliampere hour per gram up to 1500 cycle. So this sodium and battery data confirms that potassium iron oxalate has a very high reversible activity towards sodium as a sodium and battery cathode applications. So inspired by the data, further we did the lithium and battery half cell application using the potassium iron oxalate. So when we did the electrode preparation, we use the same procedure, and we run the cell at 1.8 to 4.5 volt potential window at 10 milliampere per gram current density. And differential capacity plot or different cycling interval, we can see here is also present for different oxidation and reduction peak that we can see for the sodium ion battery application. And that also corresponds to the charge discharge plot as well. And when we run the cycling stability, initially we can see there is a specific capacity around 60 milliampere hour per gram, but after a few cycles that capacity gradually decreases. That is due to the high polarization of the cell. But after certain cycle, when we saw the charge discharge curve, the polarization decreases and the specific capacity gradually increases. And after 300 cycle, it reaches to around 62 milliampere hour per gram specific capacity. So it also confirms that potassium iron oxalate has a reversible activity towards lithium as well. So to understand the in situ electrochemistry, we use lithium, another more lithium iron oxalate as a sodium ion battery cathode. So lithium iron oxalate as a lithium ion battery cathode is published by our group previously. So similar way, we prepared our electrolyte and we measured the cell at 1.7 to 4.3 potential window, at the same potential window we used for a potassium iron oxalate. And here we can see for differential capacity plot for cycle number 5 to cycle number 30, there is a 3 pair of oxidation and reduction peak present that we can observe after 200 cycle of potassium iron oxalate, and that corresponds to the corresponding cycle number 10 charge discharge plot. And when we run the cell at 10 milliampere per gram current density, you can see that cell shows around 80 milliampere hour per gram specific capacity at around 120 cycle with corresponding near equals to 100% of the Coulombic efficiency. So this data also confirms that lithium iron oxalate has a affinity as a sodium ion battery cathode application. So further, to understand the electrochemical mechanism, as I discussed in the previous slide, so we compared the differential capacity plot for cycle number 100 for lithium iron oxalate and potassium iron oxalate for sodium ion battery. So if we see both the cases, there is a 3 pair of oxidation and reduction peak present, and it's almost similar potential window. So that means it confirms that we can extract all that lithium from lithium iron oxalate 100 cycle and beyond that, and similarly we can extract all the potassium from potassium iron oxalate from 100 cycle and beyond that. So it confirms that there is a exchange of lithium to sodium and potassium to sodium has happened during the electrochemical mechanism. So further, to understand the redox activity of the cation, so here is the iron is the cation for both the cases. So we did the ex situ Mossbauer spectroscopy analysis. So this is a pristine sample Mossbauer spectroscopy analysis. Here the blue signal is due to for the 75% of the iron 2 present in the octahedral side, and very faint iron 3 plus is present, that is also shown in the light green. So as we use that carbon composite sample as electrode, so we also compared the carbon composite sample with the pristine sample. And we can see there is no such change during the pristine sample and carbon composite sample. So this is a very good sign. So after 10 cycle charge discharge, we compare the Mossbauer spectroscopy analysis with the pristine sample. So if you see the blue line says that presence of iron 2 plus. So during charge, iron 2 will go to iron 3. That is common in nature. So we can see that blue line decreases and the red line it increases, red curve. So that red confirms the presence of iron 3 plus. Similarly, when we did the discharge, it should be the blue curve will again increase and red will decrease. But we can see that red decrease, but not that much. So from that Mossbauer spectroscopy, we can conclude there is a partial oxidation and reduction of iron, not fully conversion of iron 2 to iron 3 and iron 3 to iron 3 during discharge time. Further also, we check KGN study. So to check our Mossbauer data, so you know from the Jane study, so we get we can get the iron 2 should be moved towards the higher binding energy during the oxidation, and iron 3 move towards the lower binding energy towards the reduction. To compare our Jane study, we took two commercial sample, iron 2 oxalate for a iron 2 source and iron 3 oxide as a iron 3 source. So we can see that from here that iron 2, that this one, it's shifted towards the lower binding energy, but not that much. And during the chart, the red one, we can see that it should be more shifted towards the higher binding energy, but it is not like that. So Jane study also confirms that it has a partial oxidation and reduction of iron 2 to iron 3 that we also got from the Mossbauer spectroscopy analysis. And then we thought something is going on apart from the iron redox. That's why we are getting near equals to its theoretical capacity. And after cycling, it exceeds the theoretical capacity as well. So we thought it could be useful to check the Raman spectroscopy analysis for both pristine sample and as well as the charge and discharge state sample. So this is the Raman spectroscopy analysis for pristine sample. And here is the three curve. The black one is the raw cathode materials Raman spectroscopy. The green one is for the charge state, and red one is the discharge state Raman spectroscopy analysis. And here you can see both all the cases, D band and G band, it's overlap each other. That is comes from the conductive carbon black. But if we see the discharge curve, the red one, there is a strong peak around 1400 to 96, and that corresponds to the stretching vibration of C double bond. That is one of the main peak for the oxalate anion. And another peak, 1420, that you can see from the discharge state and the raw material, cathode material, but we can't see in the charge state. Similarly, another two peak at 890 and 919 centimeter inverse, that's corresponding to gamma O C double bond O and mu C stretching. We can see prominent for discharge state and raw cathode, but we can't see in the charge state. So from that X-ray to Raman spectroscopy analysis, we can conclude that there is a formation of oxalate anion. So there is a stretching of the oxalate bond during charge state. So that's why we are not getting the prominent peak from the charge state Raman spectroscopy analysis, but it comes back to its discharge state like a proper oxalate. So that's why we are getting the strong peak with respect to the raw cathode material. So that confirms the presence of anion redox. So previously, Mossbauer and Jane study confirms the partial oxidation and reduction for iron redox, and the Raman spectroscopy analysis confirms the anion redox. So that means you can say the conclusion that there is a in the potassium iron oxalate, and shows that there is a combination of anion redox and cation redox. That is not very common for polyanionic system, but this is common for layered oxide cathode material. And you can say that oxalate should be a suitable choice for next generation polyanionic cathode application to get more higher energy density from the battery electrode. And as I said that X-ray2 Mossbauer and Raman spectroscopy confirms that both anion and cation redox activity, and this should be a suitable choice for lithium and sodium ion battery cathode application, and as the potassium host is there, and this could be a suitable for potassium ion battery application in future. And to thank to my previous supervisor at University of St. Andrews, UK, Dr. Robert Armstrong, Professor Philip Lightfoot, and all that room BIFMAR of ARAPL and JTSI, they helped me a lot for do this work. And I want to acknowledge my current supervisor, Professor Ojan, and the funding agency, PSRC, definitely. And thank you. If you have any question, please go ahead.
Wonderful. Thank you so much, Dr. Atin, for your nice talk. I hope people have many questions, but due to time constraint, we can't able to take any questions at this moment. Thank you so much for joining with us and accepting our invitation. And we are really privileged to get a speaker like you. Thank you so much. So we are almost end of the conference, and just a vote of thanks time now, because thank you is such a prayer that cannot be seen or touched. So we have here Professor Jane Wales, the Director of Environment and Sustainability Institute of University of Exeter. I would like to, yes, I can see Jen is here. So I would like to invite Jen, if you, could you mind to say a few words to the attendees, please?
It's a pleasure, Anurag, and I wanted obviously to start by thanking you. You've done an amazing job to pull this together, and to keep it to time. After 2 days, you're almost on your own timetable, which is fantastic. Big thanks to everybody who's still with us here on the conference call. Much appreciate you all taking part, and I can see it's been a really exciting discussion, and it's reached all over the world. Lots and lots of experts in solar materials and engineering, which is fantastic to see. You are the future for this area of engineering and energy production. So big thanks for joining us. A big thanks to Anurag. Special mention needs to go to Lou Misselbrook, who is not put her camera on, but she's been here all the way through doing lots of the organising and assistance in planning and technical support and so on. And likewise, Amrita Sharma, who you can also just see the name there on screen, who's been brilliant from the ESI end of things, helping to make sure this all runs so smoothly. So I think that's everything from me, but it's been a pleasure to be part of it. I'm very pleased we could support Anurag with the organisation as part of our 10-year celebration of successful research endeavour on environment and sustainability. If any of you are in the UK at any time and want to come and say hello, please do. We'd really love to see you in the ESI, and I know Anurag will stay in touch with you all. So many congratulations. Have a lovely weekend, and thanks for joining us.
Thank you, Professor Jen. Lovely to hear from you, and thank you so much, everyone. So before I end this session in this conference, I'd like to thank you, our beloved Professor Tapas Malik, Professor Asif Tahir, of course, the Professor Jane Wales, for their constant help and guidance that radiated a source of energy within us. At the same time, we will ever remain grateful to you, and we thank you for being with us today. We have privilege of holding our conference in the beautifully equipped Environment and Sustainability Institute building at the Penryn campus of the University of Exeter. I wish to thank Professor Jane Wales warmly, because without your support, and this is not possible. Thank you. I also express my gratitude, thanks to Professor Mark Goodwin, our Pro VC, for his valuable time. Thank you to all the plenary speakers, ECR speakers, industrial speakers, and all the attendees across the globe. I appreciate your urgency and your valuable time. Some people also deserve more than just a thank you. Definitely a big round of applause for Louis, Amrita, Sabrina, Rachel, FX Plus, ESI Tech Team, Kate, Amy, Exeter Design Team, Renewable Energy Group members, and our fantastic solar group people. They are constantly encouraging me, and without their support, it is not possible, you know. So I'm very thankful to all our solar energy research group, and especially, you know, I have to mention Katie, Yusuf, Sriram, May, Ravita, Shubhrangshu. They all the time, Fahd, yes, all the time they motivate me, and all the support, whatever, whenever I need, they are on. I feel proud, and thank you for making this event a successful one. Last but not the least, I'm very much thankful to the British Council under this global Going Global program, which support the partnership between us from UK and Saudi. At the same time, I'd like to express my gratitude, thanks to Professor Gondel from the King Fahd University of Petroleum and Minerals, Saudi Arabia, for supporting me in this program and as a fantastic co-host for this funding. It would have been impossible to organize this without their support and all various people. Sorry, I'm mumbling that to whom I should thanks, but thank you everyone, especially all the attendees. Once again, I'd like to propose a vote of thanks to all the speakers, scholars, and guests on behalf of the students and staff of the college. Thank you all for becoming a part of this program in ways we cannot recognize. If time is money, you spent millions for us today. Thank you to all for making this event successful, and see you sometime very soon. Don't forget to leave your feedback. There is a link already available in the chat box. Please click on that link. It straight away go to the Padlet form, and please, submit your feedback, bad, good, whatever. Just your feedback is very valuable and important for us. So thank you so much joining. Thank you everyone to connect with us, being with us for 2 days. Thank you so much, and we can conclude this conference now. Thank you. Bye.